Can you hear me okay? Good morning, everyone. Thanks so much for coming. We're on day 2 of CogX. I hope you are caffeinated and ready to learn. We've got some wonderful speakers on the DeepTech stage today, so feel free to stick around. But for those of you who are coming back and forth, I will be here all day. We've got a wonderful first speaker, also named Steph. Steph Van Grieken is going to be coming on in just a moment to talk to us about why generative AI will have the greatest impact in biology. Come on in. Thank you. Good luck.
Thank you. Good morning. Really great to be kicking this off today with everybody. I'm Steph. I'm the co-founder and CEO of a company called Cradle, and I'm very excited to be talking about why I believe generative AI will have the largest impact in biology. Before starting Cradle, I was on the product leadership team of Google Research and Machine Intelligence, and a couple of years ago, we were doing a lot of work on these transformer models that are making a lot of impact right now. And this is where I got to meet my co-founder, Eli, who was one of the researchers there, and during lunch said, hey, we're applying this stuff to DNA. And I was like, DNA? Why would you want to go do that? And he said, well, maybe very similarly to how we're learning about human language, we might be able to learn about organic chemistry, and there's such an incredible amount of applications out there. That really got me incredibly excited about this space. I think I interviewed about 100 biologists to learn about their world, and I'd love to share some of the learnings of my journey with you today. So let's start with the next slide. Yes, proteins. These are proteins. And I'm going to tell you a little bit about biology first, because otherwise the rest of my presentation is not going to make a lot of sense. But this is a protein. Proteins are little machines that live inside of cells, and they do many different things. They can be a cell wall, or they can be a little machine that performs a little chemical reaction. And you can have many proteins within a cell work together to do very complicated chemistry from, let's say, a starting point like a sugar, going to a much more complicated molecule that we might want to use. We've been using that as humans for a while now, so some of you might like beer. The way that beer gets made is we throw a yeast into a fermentation tank, and it takes sugar, CO2, and water, and turns it into a more complicated molecule, which is alcohol. This is an example of one of my favorite proteins, is ATP synthase. It actually grabs little molecules around it and turns it into energy for your cell. And they can be very, very complicated machines. There's a lot of companies out there today that are building really amazing products with biology, ranging from, next slide, please. Sorry, that's too far. Yes. Some that you probably are already using. So you might have wondered at some point, why do my detergents keep working at lower temperatures? This is because people have been adding enzymes, which are a sort of protein, to the mix, because they are much better at breaking down fats, for example. And there's many really amazing companies out there that are building products using biology instead of petrochemicals or animals as an input. Let me give you a couple of examples that you might be less familiar with than, for example, let's say the Moderna vaccine. So Sologen is a great company. They're based out of Texas in the United States. They're making chemicals, but they're not making it using petro. They're not trying to use petrol as a substrate, but they're using microbes. These microbes are fed sugar, water, and CO2. So this is a chemically negative, or sorry, a plant that's CO2 negative, and they turn them into precision chemicals. They can make these products cheaper than the petrochemical alternative in a way that's completely 100% sustainable. Another example is Perfect Day Foods. They're making milk, but this milk isn't been made by a cow. It's made by a fungus that's been modified to make this milk protein. And so it secretes this milk protein, and we can use it in all kinds of products. If you ever go to the Bay Area or generally to the United States, there's several products out there, including Häagen-Dazs ice cream, that is 100% chemically identical to what a cow would make, but it's made with a fungus. So 1% of the CO2 emissions, no cows were harmed in the process. Those are some of the types of companies that we are trying to enable. Next slide, please. So how do you program biology? obviously, biology was never really meant to be programmed in the first place because it evolved. But maybe to give you a little bit of a sense of how it works, you have a sequence. A sequence is encoded in DNA, and like all of us here, lots of different proteins get made at every moment in time, and they fold into a little structure, and that structure really determines what the primary function of the protein is. And then obviously that protein also has a set of properties that biologists care about engineering. And so, for example, if you're making a therapeutic, you might want it to bind very well to a certain target, like a disease that you care about. Or in cheese making, you might want to have an enzyme that turns milk into cheese a lot faster than the ones that you might find in nature. And the way that people try to program this is by changing the sequence. Now, this is a little bit for those that are computer scientists in here, like taking binaries and then comparing different binaries and then flipping bits to see what might happen, because there's no real formal programming language for these things. Next slide, please. So the way that they do this today is basically in 3 ways. One is they might use what they call a homology-based method. So they might look at what nature has done today, and they look at what are some of the safe mutations that I can make to sort of compare and contrast. The second thing that they might do is they might use these very large physics-based simulators to see how the molecule might fold and how it might interact with its environment. Or they use what they call rational design, which is basically, I did a PhD on this molecule, and I kind of know how it works by looking at it a lot. And as you're developing one of these products, and this is really the core to why I think it's really hard to program biology, is that it's really hard to make the right decision between what piece of the DNA you need to change in order to get a certain result, a certain objective met. Next slide, please. So in conventional computer programming, once you've made a change and you run your program, you get pretty quick results. And unfortunately, in biology, that is not the case, because you actually need to go try out whether the protein that you designed is better than the ones that you had before. And so the way that they do that is they'll first design this protein, so make the different types of mutations. They will then go into the laboratory and they'll order DNA. There's a couple of providers where you can just order sequences. They'll send them to you. They will put these in a cell and express, like make the proteins in the cell and then run their experiments on that. The time between, let's say, designing your candidates all the way to having an experimental result back could be 8 to 12 weeks. So if you then zoom out a little bit, when you're developing a bio-based product, you're doing many of these cycles, dozens typically, and every experiment costs around $350. And so it's quite expensive to make a bio-based product today. And that is obviously very different from writing computer software. Next slide, please. So what I've been working on with our team is very similar to some of the large language and generative models that you've seen out there today, where you can use something like ChatGPT, give it a prompt, and it will give you an answer, or generating an image where you give it a prompt and you get a really nice image. In our case, the prompt is a starting sequence. Like I have a molecule that approximately does what I want, and then your objective with it, what you would like to improve about it. And we effectively generate a set of sequences they can put into their experiments that have a much higher probability of actually reaching their design objectives. And that works better than a lot of the things that people are trying to do today when they're engineering these types of systems. Next slide, please. So this is an example of a protein that we've been working on. It's called T7 RNA polymerase. It's the little squiggly on the top left. It's a protein that's responsible for turning DNA into RNA. And so when you're making a vaccine-based therapeutic, for example, this is sort of your manufacturing workhorse that makes the actual product. You can stabilize this protein and try to make it more active, which means that it can make more RNA product, so more vaccine. And we've been running several types of lab experiments on this protein. So with some of the conventional methods that are out there, you might get 1 to 5% of your sequences coming back positively, as in being better than the ones that you had before. What we found is that with some of the generative models that we've developed, up to 95% hits on a plate, so you get a lot more sequences back that are actually a lot better than the ones that you had before. And we were able to get this thing to a target for our customer in 3 experimental rounds, where typically they might be using 8 to 10. And try to remember, it's about a quarter to run 1 experimental cycle for a lot of our customers. And so really this helps them get into the market with some of these products a lot faster. Next slide, please. So why am I excited about that? Really, because I think these types of technologies enable a lot of people that want to build products with biology a lot faster. McKinsey did some work around 60% of all of the things that we consume today, whether it's materials, foods, medicines, could be made in a fully sustainable way with help from biology. But if it costs 20, 40, several hundred millions of dollars in order to get to a working product, that is too much. I think what these technologies are going to show in the coming decade is that we can build these types of bio-based products for a fraction of the amount of money and in a lot shorter amount of time than what we can do today. A lot of the venture community and sort of the technologies that I've worked on in the past were based on bits. My sense is that a lot of the future technologies and cool companies that are going to be built are based on atoms. And this is really where I think Gen AI will have some of the largest impact. Thank you very much.
Hello.
Hello.
Well done. I was just hanging out in the back watching and observing. Time for a few questions, if we may. One of the things that I thought was so compelling about this, and I'm sure I'm not the only one in this room, was what we can learn from nature in order to use AI effectively with the things you're trying to do. To what extent is nature your inspiration, or are you ignoring it?
Very much, actually. So I think maybe to give you a little bit of a sense of how you train this type of a machine learning model compared to how you train sort of a human language machine learning model, it's actually quite simple. So the way they're trained is you do an infilling task. So in this case, for example, in natural language, you would use a sentence like Steph is a bleep, and if the model says computer scientist, it gets points. If it says butcher, it doesn't get any points. If you do that for all the text on the internet, you sort of have ChatGPT 1.5, right? We do something very similar. So we take all the protein sequences that are known out there, and we do CTAG, bleep, 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 right? And then if it fills them in correctly, it gets points. And so it sort of learns what would be reasonable from an evolutionary perspective to put in a certain position. Now, that's not everything, because just a sequence might not do something. We still have to tie that to experimental results. And then we sort of expand them to some of the things that we talked about, like do molecules bind well, or are they stable molecules? And we can sort of condition these models to then also generate proteins that have these types of capabilities.
And there was a more philosophical question that I had as well. That was
you're asking an engineer, right?
Based on what you said about, you asked the question of how do you program biology, and you mentioned, of course, that biology is something that is more about evolving. So is there a tension there? Are you playing God a bit, I guess would be my question. Or are you playing Darwin?
I think it's more Darwin on steroids than God, really. Yeah,
okay.
I'm also not religious, so.
Yes.
No, but I mean, we definitely take inspiration from evolution to basically extend our capabilities into the future. I think what we do is not new, in the sense that people have been making medicines for a very long time that are not small molecules but are protein-based. We talked about detergents. Most of your detergents that you're using at home right now will likely have enzymes in them today that are modified from their sort of original one in nature. And so, yeah, it's a little bit of a sliding scale, I guess.
And are there any areas where you would feel there's a no-go area, something you're not prepared to work on and use AI in this way?
Absolutely, yeah. I mean, this is a little bit of an emerging field, especially because we're also making software. So we had to ask ourselves the question, like, what type of companies do we want to work with, and what type of companies do we not want to work with? Anybody that wants to work on things that might encode for a viral particle, or things that might be toxic to humans or carcinogenic. We actually had to figure out, like, how do you write a terms of service for this thing? And that's quite complicated. Luckily, there are a lot of controls and safeties already built into biotech today. So for example, if you order DNA from one of these providers, they will check, are you trying to be naughty here or not? And does it look like something that we wouldn't want to have out there in the community, sort of without controls on top of it. And actually, I think, maybe in contrast to people that make large language models, biologists have figured this out before they started launching technologies.
Yes, although that always leaves the possibility of unintended consequences. So how do you control for that?
Yeah, definitely. I think part of the answer is that is already also taken care of in many cases. So the area where we show up is mostly in the research and development stages, and there are very clear regulations about when you can introduce a new sort of biological into the world. So obviously in the case of medicines, you have clinical trials, and you have controls as people are building their technology in the early stages. Similarly, for things that are food products or generally sort of genetically modified systems, the people that are using our software in the R&D department, they have an obligation under law to make sure that they're compliant.
Right. And I know I've been focusing on the negative and risky side of things, but can we turn to the more hopeful side? Where do you see this going? Like, are there any things that if we could fix A, B, and C conditions, this becomes possible? Like, sketch us through what the utopian vision looks like for you.
I think for me, the utopian vision would be to replace most of the things that we're currently using animals or oil for with these types of systems. So, this is nylon. Would be nice if we could actually degrade it when we don't use it anymore, or maybe even better, we could have materials that already have the properties that make them auto-degradable. I'm excited about. I'm sort of not a science fiction guy, so I'm pretty sure people will come up with really weird applications. I got surprised, I think, a month ago when a customer signed up. They're in the world of ore sequestration, so they're in mining. I was like, mining? Why would you want to work with biology in mining? And so what they're doing is when you're trying to separate lithium from the rest of the ore, you basically need to heat it up and put a lot of very nasty chemicals inside the mix in order to get these things to separate. And they're basically making an enzyme that can do that sort of at room temperature in a bucket of water. And I was like, wow, I had never imagined somebody would do something like that. And so I think there's lots of opportunity out there. In my career, I've mostly been a tool builder, like with TensorFlow and with Android before. And so, I'm excited to see what people are going to build with this type of technique.
That's so rad. And I guess another question that I would have is for somebody who's new to this, right, who maybe is interested in AI or is interested in biology but doesn't know how to do the synthesis, how would you advise getting started and where they would begin to explore to educate themselves, besides obviously coming to CogX?
Of course, yeah. I think there's a lot of good resources out there on the internet. An organization called SynBioBeta I would definitely recommend. They have a newsletter. They have a lot of resources. Some of it is also, with every new field, like if you want to get educated about machine learning, you have to read a few books. There's a bunch of books in the biology domain. So yeah. my biology co-founder were like, here's molecular biology of the cell, read it please. And so, but Google it really is the answer.
So start with really 101. And then you're going to have to build it up.
Yeah, exactly.
And who are the companies or countries where you feel are leading? So if we had to look at the sort of global view of the field, where are you really excited about and where you see the hot spots?
You mean from a machine learning perspective or from the products
AI
that are being
biology.
made? Okay, yeah. I mean, there's in Europe, there's a couple of really great companies here. For example, Extentia, Benevolent AI, they're in the pharmaceutical domain here in the United Kingdom. Obviously, you have some more sort of general research groups like DeepMind here with AlphaFold. That's probably familiar to a lot of the folks in the audience here. I think because biotech is historically quite big in Europe, like you have a large cluster in Denmark, in the Netherlands, in Switzerland, I think a lot of these companies are starting to adapt these types of techniques, and we have a really large talent pool. So I think this is an area where we could win
right.
as Europe, which obviously for ML, we're, the center of gravity is very much in the United States, for sure.
And do you see opportunities to collaborate, particularly on like data set sharing and setting of frameworks, et cetera, or is it a very siloed space because it's so competitive?
Yeah, I think this is actually one of the complicated problems in our space. And so, if you're training something like ChatGPT, you could download the internet and sort of train on all of that data, and you have a pretty decent data set. Obviously, for a lot of people in biotech, that sequence that they're making, that's their IP, right? Sort of if they want to go sell that and they were to publish it on the internet, they just lose that IP. And so that means a lot of sort of commercially relevant experimental data and sequences are not necessarily available. This is actually a topic, I think, where we should spend more time, because good benchmarks for these types of LLMs in this space, they do exist, but they're not great. And we could definitely do a lot more there.
Wonderful. And for a bit of information before we close this session and let you run away off the stage, the Royal Society is going to be publishing a report in November in this country, so keep an eye out. They've been having roundtables with scientists. I was emceeing the one yesterday, talking about precisely this, which is why I wanted to ask. And that's going to come out with all sorts of insights, framing of problems, pointing to resources, et cetera. So if that interests you, another area to get a heads up is the Royal Society. So keep it on. All that remains is for me to thank Stef van Grieken and all of you.
Thank you very much.
And if you stick around for the next session, we'll be starting at 10:30, and that is on tech bio trailblazers, innovations, entrepreneurship, and investments. So relax for a bit. We'll have our next group on shortly. Thank you. Welcome back for our next session. This is going to be a female power session, so just get ready to get blown away. We've got some amazing women who are about to come on stage. So we are going to be talking tech bio trailblazers, innovations, entrepreneurships, and investments. If you'd like to come onto the stage, ladies, and join me, we've got Loretta Tioila, we've got Dr. Rachel Shaw, and we've got Shakiba Kaveh. So Shakiba, you're here. Rachel's there, and Loretta here. So it's basically like a high-powered brunch. So, Loretta, we were talking behind the stage about why we are here today and what we're doing, which is going to be showcasing some incredible talent. So I'm going to let you talk for a bit to tell me what's going on and what the vision is.
Yeah, definitely. Super excited to be here with everyone and talk a little bit more about tech bio. I think the first thing that we can say is basically to start by defining what is tech bio. A lot of things is happening in biotech right now, and biotech is definitely changing. I think what is most important is biotech doesn't look the same because biotech startups now are not just all about drugs and therapeutic. They are working in fashion tech, in climate tech, in cosmetic products. They're building for the future, and this is one of the main divergences that we see right now in biotech. And the only reason why this is really possible is because there's a shift in the way that biotech startups nowadays are actually building. They are closer to platform and becoming platforms because they are basically leveraging the power of computing. So we're here today because we want to introduce and present some of the best amazing founders that I've met in this ecosystem with Rachel and Shakiba, but more than just two amazing founders that we want to feature, we also want to give a hint in the industry and what's happening in the industry.
Great. So do we want to first talk about what our two founders are doing? Who wants to go first?
Sure, I can go. So I'm Shakiba, CEO and co-founder of Mitra Bio. We started it 3 years ago, so we've developed a way to non-invasively sample the skin and extract biomarkers, looking at methylation, which is an important epigenomic mechanism that can diagnose aging as well as early cancer detection. So the problem that we faced was, you have a lot of blood tests or saliva tests or urine, but if you want to actually test the skin, the only way to see the biological data from it is to take a biopsy. So it's not really scalable, and a lot of data is hidden behind these biopsies. So we've developed a way that you can extract DNA methylation using tape. So it's just like a piece of tape that you put on your skin. And the very first people that got interested in us were skincare companies. So L'Oreal's of the world developing skincare for the age of the skin. Does it work? So now we are working with some of the top skincare or even Botox manufacturers to tell them whether their ingredients or their innovation really targets the root cause of skin aging. Thank you.
I love that, from cancer to Botox.
Yeah.
Covering the full ethical range. We're trying to save your life and also freeze you.
I think she got me there.
That's great. Rachel, over to you.
Hi, I'm Dr. Rachel Shaw. I'm CEO and one of the co-founders of Eden Bio, which is working in the space of basically the future of food and every other protein technology out there. This is a really exciting space because we're at the start of this biotech revolution where a lot of protein products that were traditionally made through animal farming, which, as we all know, climate unstable, geopolitical instabilities are causing issues with this. It's basically not going to be able to continue the way it has been for many years now. And people are looking to fermentation as an alternate technology for producing not only a lot of the products that have traditionally been made through animals, but also some of the incredibly innovative new proteins that are being made through AI and other generative tools these days. So we are at this point of inflection where we're going to see thousands of new types of protein products arriving. So proteins that are stronger or taste different, that allow us to do a whole range of make a different range of products. And this is where Eden Bio comes in, because the traditional fermentation technologies and methodologies that are out there were created in the 1980s, but haven't taken advantage of latest in AI technology and the other incredible innovations that have happened in recent years that allow us to do this fermentation much more effectively than has ever been possible before. So we use machine learning and other technologies to find ways to better optimize microorganism strains for fermentation, helping companies that are bringing these incredible proteins to market get there faster and more innovatively than ever before.
Now, for those of us who are not scientists, can we just take a step back and say, why? Why are you doing this? Yeah. What's the problem you're trying to solve? So you're making synthetic proteins, et cetera, biology, cells get mentioned, but if you had to talk about this to someone who's never done this, or it's been years since they've studied it, and I don't just mean me, how would you explain this?
Yeah, so the whole point of these proteins is to get us moving away from traditional forms of protein production, animal farming. So cows producing not only milk, chickens to produce egg whites, all sorts of food, but also industrial enzyme things, products that you get as byproducts from cows that have been traditionally, you need the cow to do. Now we're able to make these incredible proteins without animals.
So an animal welfare perspective is a great one here.
Not just that, but also to be able to allow us to produce these new proteins that couldn't be produced through animals. You've got these incredibly innovative enzymes that have all sorts of different functions. So plastic degrading enzymes, for example, not traditionally produced in cow. So you need fermentation as a technology to produce these new enzymes that have these incredible new functions.
Wonderful. Thank you for that. I will throw the same question to you. Why?
Yeah, because now if you, for example, if you feel low in energy, you go and take a blood test. You can look at a lot of biomarkers in your blood to really diagnose, but there isn't anything for skin. So skincare industry is kind of this like big marketing buzzword that they all throw in. And the more I speak with these skincare companies, even though they are not really regulated, but they are really regulated by the people who use them. And they've actually found that if you can personalize their ingredient to the need of the individual skin, they can sell more, they can retain more people because of it. Mm-hmm. So there is this whole need of, can I understand truly what your skin needs and personalize my recommendation to it, so you will buy more, you will buy bigger, and you will buy for longer. So with us, we're like, okay, how can you really understand the skin? I mean, you can take a photo of it, but it's very subjective. So how can you understand, what is the UV score of your skin is? What's the inflammation score? What is the aging score? Are you sort of someone that are aging at a faster pace than someone who does not, So trying to really leverage the biomarkers that you get from your skin to the course of treatment that you can take. And this is what we face. At the moment, there is no way to really read the skin other than looking at it. So we've developed a way to extract all these biomarkers from it, and it's really cool.
That's incredible, because I guess it kind of reminds us that the skin is an organ, right? Because we often just think of it as just our skin, right? It's a sort of surface holding all the rest of it together. But this is an organ that we need to take care of. And if we can't read it to see if it's in good health or not, we could be missing out on all sorts of health problems. I mean, I don't know if we want to call aging a health problem or just a beautiful part of being alive, but aging well. But certainly the cancer, the inflammation risk for people with eczema or psoriasis, et cetera, that would be such a help for them, and personalizing it as well.
Yeah, there's a big misdiagnosis when it comes to skin, because there's no way to directly read it. So yeah, hopefully, we see this even more. Like, you have all these preventative biomarkers like Zoe Health, Oura Ring, and I was just speaking to another female founder that now you can, when you look at your hormonal health, you can actually understand from the flow of your period, volume, regularity, you can diagnose many female, problems rather than just looking at certain hormones. So there are all these indirect biomarkers of health that I think in the next 10 years going to become very important in the preventative health, and I think people are, hungry for them.
Do you need any 47-year-old women that you want to test it on to make it better? Volunteer subject. I'm sure I speak for many people in this audience. Loretta, a question for you before we come back to you, Rachel, so don't relax. You have a mission to build the largest synthetic biology open computing community. Tell us about that mission and how that relates to the two founders that we have on stage with us.
Yeah, definitely. It's been a journey. I think the word I'm getting out of what Shakiba just said, this notion of reading human life. And I think that this is the core concept behind and what I was explaining when I was talking about tech bio. What we're seeing here is a paradigm shift where instead of approaching life as something where it's providing us its basic operating rule and we accept it, we are now reached a stage where in terms of technology maturity, we are able to influence it, we can redesign it, we can reprogram it. And that is the most important principle shift. And that means that when you start thinking about things in this perspective, anything is basically possible. But when I started, it was with a very basic issue that I was trying to address. I'm coming from a very poor background, and obviously violence is always something that comes along. And for me, the idea was the idea of rewiring the brain. So when I started, I was interested in neuroscience. I was someone who was working tech for the past 15 years, and I was trying to apply my knowledge in cloud and AI and quantum to how can I rewire the brain. And obviously, because I'm a technologist, I'm a very simple mind. I will do what I can do and what I know how to do, which is basically build, build, build. And so I was trying to tackle that issue. And so very quickly, I started to work with neuroscience startups. And I realized there's a problem here. I was never going to be able to rewire any brain as long as I'm not able to fix the data issue with biotech startups, because all of them are actually data prone. By definition, biologists, life science researchers, are the epitome of providing data. All that they do is run experiments, but for me as a computing scientist, these experiments is data. There's just tons and tons and tons of data. But what I could see was basically the data is there, but the way to approach, to manipulate it, to structure it, and to analyze it, and to shift it away is not there. So we needed a way out, but how can you actually build that? You're not going to have one-size-fits-all platform. I tried that, didn't work out, didn't get investment, so it's kind of, okay, I blew this one out, next, what can we do? So I knew that the problem was the right one. It was just a matter about how do I go about it, and so instead of focusing on building a platform, I focused on building the ecosystem. I wanted to bring together these two ecosystems, this life science research ecosystem with the computing ecosystem. And for me, it needed to be done in a safe space, a non-for-profit, a neutral space where IP will not be a subject, where we will not have war from one service provider trying to take over control over an entire market. Because what I could see is what needed to happen for us to be able to reprogram life was basically what happened in computing. 30 years ago, computing was very closed off. It was all proprietary software. But through the power of open sourcing, through the power of community, everything changed. And for me, it was kind of a perfect analogy of what I thought what needed to happen in bio. And so creating a computing foundation for bio was my way to approach this. So it was very naive, but it kind of worked because it helped me basically test out that gut feeling that I had and turn it into something that was more than just a gut feeling. Very quickly, we grew to 400 startups ranging from pre-seed stage to Series D. And this has been more than 4 years now, and we're past from the 400 startup. We are reaching out more than 2,000 startups worldwide, and all have this vision that, yeah, bio is changing, and the main component is we're thinking about things as things that we manufacture. We can reset the operating system of life to its original setting, or we can set it to something entirely different.
I mean, congratulations. That's an incredible growth story. How did you come across Rachel, and how did you come across Shakiba? What excited you about what they're both doing?
Yeah. So I think what excited me the most was the impact. And it's definitely a different kind of impact. I think I started with Rachel because as she was explaining, the impact in terms of food production is massive. All of us eat. The planet is growing, 9, 10 billion people on this planet. So we know, all of us know that we need to find a better way to manufacture. And so solving that issue was something like kind of obvious. And so hunting for startups that are trying to leverage computing to actually solve that issue was actually kind of my mission. And so there isn't that many startups actually doing what she's doing. And so it was obvious that I wanted actually to engage and really be able to understand where she was coming from, because I think coming from someone who have worked in product all my life and now investing, I think a lot of people have great ideas, but there is execution. But behind perfect execution, there is always a great founder. So I was more concerned about, okay, I love this startup, I love the idea, I love what they're doing when I'm looking at their website, but is she the one that is going to pull this off? Like, really? And so when I met her, it was like, yeah, kind of, because she's like amazing, like really, she has all the quality that a founder needs to have to be able to put through. And I think for me, the first thing is genuinely being kind enough and humble enough to know what she knows and she doesn't know. So this is how our story happened.
We had on our introductory call, I just remember us getting really excited about the potential of the technology, and it's also quite rare. You know, I speak with a lot of investors who are, or a lot of people who are in the industry who have some insight into it. But Loretta just got it. She understood the potential and the excitement in this space. You know, we were talking about how we're at such a turning point that it's not that crazy to be imagining that you can have celebrity chefs with this kind of technology designing their own proteins for their restaurant so that they can have something that you can't taste anywhere else. That's the level of innovation that fermentation can bring to where we are as a world. And I just remember us getting really excited about the potential.
Yeah, it's like branding your own protein, and so you know that nowhere in the world people would be eating that food because it's like your own particular recipe, but not even at the higher macro level, but really at the molecular level. This is so amazing.
I love this. The Michelin guide is going to be revolutionized.
Someone needs to invest in this, by the way.
So are you saying that we could have different tastes besides sweet, sour, bitter?
No, I mean, they'll be within those categories. There's also umami, which everyone always forgets about that one. But yeah, it's more a case of it could have a different variation of it. It could be something new.
Yeah.
Right. And how about Shakiba?
Yeah, like I mentioned, there is a wide range of application, and the thing is, scale is whatever the way that you're going to go at it and think about it. It's also about thinking about things that are here in your everyday life. You don't really think about it. Everyone is doing it, and yet it's occupying such a massive market. But because it has become so integrated, people don't think about it as a business opportunity. And skin is definitely an important one. And of course, like you mentioned just before, you start to think about it from a beauty aesthetic perspective, but there is so much more because, like you said, it's one of the most massive organ, actually. Its surface area is massive, and there is not just the aesthetic part, there is also the health-related part. So for me, it was like kind of, yeah, and this is a topic that is almost unexplored. And that's what I liked in the way that Shakiba was actually going about it, because it's unexplored almost. And so, like she said, there's a lot of cosmetic, like take photo, try to apply computer vision to analyzing the skin. And these are amazing. These are the first layer that we needed to go through and we need to go through still. And both are complementary. But going one step further, that one close deeper to the real, mechanism of how the skin works, that was like kind of amazing. The only thing is, I hunted her down. I was just like, okay, have you heard about me? Hello, what are you doing? And so we had the chance to connect. And so I think for me, it was like, yeah, I think she had all the quality again to bring this forth. And I think it's its uniqueness of the vision that really seduced me.
Thank you. And you've both got the vision. You've clearly got from your bios the sort of street cred and what it takes to make it happen. How do you both feel as founders, being here, particularly in the UK, where we have such a strong life sciences sector, and this moment that we're living in with AI, where we've got the data, we've got compute, we've got the financing, there's this real enthusiasm about it. What do you feel you both need? We've got about 5.5 minutes left, so I'll start with Rachel, and then I'm going to come over to you.
Yeah.
What do you feel that you need to take your vision and make it full?
Yeah. So for us, the massive challenge out there is data. Machine learning, AI technologies are nothing without the data that you use to build them. It's what it needs to be able to learn, to be able to do whatever it's going to figure out. And so this is a huge challenge, so building out that data set. But more than that, there's also the challenge of employing the right individuals who have the capability to do this, because we sit at the confluence of synthetic biology and machine learning. They are two industries that have traditionally been very separate, and that's what is allowing us to now apply these two together and come up with these incredible innovations in this space that just haven't been done before. But finding people who also have that expertise is rare. So yeah, one of the challenges is, do you grow that expertise in-house? How do you expect the UK or the global network to really, over the coming years, drive more people with this joint expertise that will help get us there, and then together working with them to build this data sets that we're going to need to improve what the machine learning can achieve.
Shakiva, does that ring bells?
Yes, for sure. I mean, I echo with the talent strongly. I mean, here in the UK, it's great to run a biotech startup, but it's still very hard to hire the right talent internally. I mean, it took us 6 months to hire computational and bioinformatician. So there is this really gap that we had to, go to other countries to even, bring people in, sponsor them. And also, I would say, pre-seed money for biotech still lacking. So, we are in a, I can speak for ourselves. We are at this, limbo state that we've proven the tech, but, there's still more commercial traction to be done. There is a bit of a vacuum here in terms of funding. So, more biotech investors at an earlier stage. So that's what
particularly in the UK. You see a lot in America that are much more willing to jump at the exciting potential of this technology, but in the UK it's just a bit more reluctance, and it's a gap, unfortunately.
Is that because they don't understand it?
No, I think they do. I think that the UK has always been quite a conserved place. We are looking for more evidence of traction before we typically jump in. But that, unfortunately, comes with the downside of sometimes then you miss out.
Right. And this piece that you've both identified about talent is really interesting to me. So if you knew that you were, being broadcast live, for instance, straight into our friends in the House of Commons, if people were in civil servants were listening, teachers, parents who are thinking about how we're going to train up the next generation of people to be able to work across disciplines. What should they be doing? Should they be studying the biology and then add AI on after, or come at it from the AI perspective and then have to do the biology? Like, where do you start? Or is there a way of doing combined degrees? Do we need to rethink how we do university education or A-levels?
Yeah, it's a great question. We're starting to see more combined degrees coming available, but they're rare. What you instead are seeing is that people, for example, one of my co-founders, Dr. Chris Reynolds, his background was in biology, and then he, through his interest, then started learning the machine learning, and then was in his own trying to apply the two together. And hopefully that's of the past. Hopefully now what we're seeing is that this cross-discipline becomes a discipline of its own, because there's so many innovations there that if we just have people focused in the space, that they'll be able to find.
Yeah. Does that ring a bell?
Yeah, and I would say, if I ever have a kid, I would get them to learn a skill, not like science, because you can read the science and learn it. I mean, I come from a non-bio background, and I had to literally learn, what the science is, what the biology is. And I was able to, pick up the science. But what I cannot pick up is, coding or these machine learning skills. This is like, there's no way I could, learn that in such a short time. So,
yeah, it's very, very funny actually, because I have a kind of a shifted perspective on this. I'm coming from a non-bio background originally either, and I spent most of my career in computing. And so I had to make that jump from computing to bio. And so retrospectively, I would say, I know coding is so impressive, and I think there's a lot of mental models sometimes that just prevent you from getting started. But in a weird way, I still want to believe that it's easier to pick up on that than actually really picking up on the entire, I would say, 5 to 10 years education that it requires to really educate someone into turning that one person into a master degree, PhD level person. And so coming from tech, I think for me it's much, much harder actually to make that jump. And I think that if I were to do things the other way around, I would definitely go for going for the bio for sure, building that. Because the thing is, what she said like about the data, the algorithm are just the extraction of the value out of these data. They are just a manifestation of that. But the real thing is the data. So, but data is, you need to have insight. We always talk about this idea of AI is going to replace everything. We have had this debate around for a long time with healthcare, where we're thinking, okay, you're not going to need a radiologist, you just need an AI that is going to tell you if there is something in your scans. I don't agree on that, because I think that it's just an enabler. It's just like siphon all the noise, but the human eye, the intelligence and the ability to track, detect is also there. And so I think it goes the same for data. Someone that is coming from computing will never be able to do anything out of any biological data, because they have no basic understanding of what's happening at the biological level. And so you have no way. You can apply basic techniques. Okay, you're going to do a random forestry. Okay, well, you know, the problem is with data is if it means nothing to you, no matter what your skill set is, you're still not going to do long with it. There is a reason why we need labeling. There is a reason why we need expert training and expert eyes to actually analyze this data. So the data in itself as a broad structure means nothing without the knowledge. That's why I'm still convinced that
Science first, add the AI after?
Yeah, science first, and then whatever, because the techniques will change. Today we're talking about transformers and LLM, and the techniques will change. They are just a manifestation, but you need that understanding first.
Loretta, I feel like we could all listen to this for a lot longer, and I have the terrible news of saying I have to get us off the stage, so we've got another fantastic panel coming on. Thank you so much. That was just wonderful. Loretta, Rachel, Shakiba, that was just educational and inspiring. Thank you.
Thank you.
we've got a next speaker with a very fascinating profile. And he's going to be talking us through synthetic biology, a new approach to computation and intelligence. Coming from Australia to our lovely, fair, rainy island is Hong Wang Shang. Hong, come on on.
Oh, it's kind of bright here. Thank you everyone for coming for my talk. Forward, if I'm a little bit aphasic, please, I apologize beforehand. Flew up from Australia, so time zone difference is still catching up with me at the moment. But yes, let's talk a little bit about context. So we've all heard a lot of talk about AI over the last day and a bit, particularly the transformer model of families, Gen AI, large language models. And that's all really interesting. But we're going to take a detour today. And the detour is going to be talking about the other intelligent machine, one that we sort of take for granted, but every one of us, you and I, dog, cat, all possess. And that is the brain. Now, why is this relevant? The reason for that is that despite the fact that we've done amazing things with our current AI technologies, they still require a significant amount of energy and also a significant amount of sample data in order to train. Whereas if we start thinking about the brain, how is it all doing this? We have this complex organ that is processing information, that is able to do abstract reasoning, cognition of what's happening, and processing of that. And if you take a few steps back and you say, well, we all have slightly different brains, animals have different brains, but what is the common thing that makes up a brain? And that is the neuron. So what does a neuron look like? And I figured it's probably best to just show it. So this is me, and we've got a Discord, so if anyone wants to chat, we're there. But this is what a neuron looks like. This here is, anyway, I'm just going to point. So that long thing there is an axon. And all the stringy bits, like melted cheese, are essentially dendrites. Dendrites that form synapses with one another. And 10 microns for scale is 1/5 the width of a human hair. So this is a scanning electron microscopy image. Now, if we zoom out a little bit further out, you can see a lattice. That lattice is a CMOS-based chip. And what this image shows is the level of integration of the neurons onto the silicon substrate. Now, I have one of these devices here actually to show, the one that's right there. And this is actually one of the chips that we've actually used to do experiments with. There were some neurons on here, but we sterilized them on the way up here. So now, if we take a few steps back and we say, so what does a neuron do? And how does it communicate with one another? A neuron fires electrical impulses from one to another when they want to send a signal. This is called an action potential. And because these neurons are sitting on a bed of electrodes, we can read this electrical activity. And we can also stimulate them by providing a reverse voltage charge. So now we have this read and write interface into a biological structure. So let's see what is required in order to turn these things into computational devices. Video, please. So because you come down to my lab, but if you ever do come down to Melbourne, you're more than welcome to visit. This is how we grow the cells. They live in an incubator that maintains homeostasis, so a set oxygen level, CO2, temperature, humidity, and so forth. And this is a glass chip, glass multi-electrode array device. And this is how we interface with the neurons. That pink fluid is a cell culture media called brain fizz that is essentially artificial cerebral spinal fluid. It's got glucose, large factor proteins that nourish and keep the cells alive. And each individual dot, little white dots, are essentially neural clusters that grow on the chip. So you must be thinking, how does this all stay alive? And that fluid essentially nourishes the cells. And the cells, being living organisms, will actually create waste. And that, over time, changes the chemical composition of the cell culture media. And cell culture media is really important to keep that in a very narrow range, because neurons are particularly sensitive to changes in osmolarity. So that's the concentration of the solutes, particularly potassium and sodium, because that's what's used to transmit that electrical impulse. And so this is a process of just taking out 50% of the fluid and replacing it. That's a very manual task that we do in order to keep these cells running and in a sort of a healthy shape. So this is what they look like under a microscope. And I think this is fascinating because you get to see the juxtaposition of a biological network growing on a silicon network. And you can see there's this, there are all these little pads, and these little pads are what picks up the electrical impulses. And that's an axon, or neural bundles that run between one cluster and another. That's sort of parallel following the actual electrode traces. So what we do once we plate those cells, and it takes about 2 to 3 weeks for maturation, is we then put them into a reader. And this takes the action potential signals from the neurons and converts it into a digital signal and provides that to a computing system, and back again we stimulate the neurons. And this is an example of the neural activity trace that runs, and each dot is an action potential that's firing, and you know, that's the way we actually interface that with the computer program. And it's really important that you have this computer program, because it turns out the neurons like structured information. So this is a paper that was published last year in Neuron. It's got all the details. I'm going to skip through a lot of this stuff, but it's very dense. It's really interesting as well if any of you are keen on the science. But essentially, how we managed to get these neurons to perform the game of Pong is a combination of various disciplines. So we had stem cell tissue culture, where we take blood, turn them into adult induced pluripotent stem cells, and from there differentiate them into neurons. That gets integrated with systems neuroscience to understand, you know, concepts like lateral inhibition. How do we encode where the position of the ball is to the paddle, and so forth. Electrical engineering to wire up all the chips and the neurons. And you know, what's really important is the software engineering, because in order to get these things to work, you need a closed loop system. The neurons need the ability to be embodied, so to speak, in an environment. They need to be able to sense stimulus, perform actions on that stimulus, and then see the outcomes of that. And this is really important as part of the free energy principle, which is a theory that's been developed by Professor Carl Friston at UCL. It's a very complicated theory of how potentially intelligence works, but to surmise, it assumes that the brain is a giant Bayesian predictive machine, that you and I right now are forming predictions ahead of time about what the world is. And our senses are confirming or disproving those predictions. And this is how we actually get the neurons to work. So if we can get video, please. Oop. So this is a visualization. And if anyone's interested, this is on spikestream.corticallabs.com. It's a 3D visualization of the electrical signal on a surface of a chip. There are tiles that represent the electrodes, and we encode the position of the ball in relationship to the paddle in 2 ways. We do it via place encoding. So you don't see our stimulus on this system because we blind ourselves to our own stimulus. But we stimulate 8 different regions on that big section there for the y-axis. And the x-axis is encoded using rate encoding. So the closer the ball gets to the paddle, the faster we stimulate them. those two bottom regions there are motor regions. And what we do, there's no magic, there's no AI or machine learning. It's a simple summing of the activity squared. More activity in one pushes the pedal up, more activity in the other one pushes the pedal down. So it turns out, what you need to do in order to get that to actually play is you need a reward and punishment process. And it turns out that based on this free energy principle, which posits that neurons want to get really good at predicting the world, if you give them a signal that has low entropy, i.e. like a sine wave, that's a rewarding thing. And if you give it a high entropy signal, like white noise, that's a punishing thing. And it turns out you really do need this push and pull reward punishment system in order for them to work. It's all detailed in the paper, so if there's more interest, please look into that. But anyway, now that we've talked about the paper, the question is why do we do all of this, right? And the reason for that is, as you all know, there is a race to do artificial generalized intelligence, but everyone is thinking about it from artificial neural networks. And as far as we know from our work and what neuroscience is now understanding of how neurons work, the artificial neural nets that we've developed are very different from how we now understand the neurons work in vitro or in vivo settings. For instance, the nonlinearity functions in artificial neural networks are mostly static and fixed, and that's how we get the speedups from matrix multiplications using GPUs and so forth. But as far as we know in biological neurons, they're a floating number, or they can change from one state to another based on neurotransmitter values. And then each of them are slightly different, which then means that if you do want to simulate a real biological neuron, you're back into CPU for loops. And so the question then becomes, why try to do artificial generalized intelligence using silicon when we can try an alternative approach, a detour, using biology? Because at the end of the day, the only truly generalized intelligent system that we know of are biological in nature. You and I, a dog, and a cat. So that's where we are, where we were. This is where we are at the moment. And we think about this as a progression. And it's great that we had Jürgen Schmidhuber talking about the history of artificial intelligence and it spanning all the way back into the 40s. And if you think about the current silicon industry that we have today, it goes all the way back to the 50s. And we think that the system that we have right now is equivalent to the IBM S360 of the 60s. And for that, you have, Brett, who's my chief scientific officer, there reference for skill for a big incubator system, and we have teams of technicians keeping the systems alive. And the thought process goes, what do you really need in order to take this to the next level? Systems that are more accessible, i.e. smaller, cheaper to run, programming interfaces, and abstractions. Because if we think about how we do our computing systems today, they're all built on levels of abstractions, right? We don't think about how assembly works, right? We write a high-level language like Python that can compile down to instruction sets that are specific to a CPU. And so this is something that we're working on as well at Cortical Labs, which is how do you take what we've learned in the computing industry and turn it into something that is more accessible and able to be used as a tool going forward. And so the Apple I, I guess, was the inspiration for building what we call the CL1, which we have right here, one of the first industrial prototypes of a biological computer. And it took 30 years from the Apple I to get to the iPhone. The question is, where are we going to go in 30 years with a technology like this? Now, what's interesting about a technology like this synthetic biological intelligence is the fact that because it's biological in nature, and the fact that we've trained it to do something, playing the game Pong, we've also done the Chrome offline jumping dinosaur game, is that it can apply to two different industries. On one hand, you have the biopharmaceutical industry, where players in that space want to control the wetware being the cells. And on the other side of the spectrum, you have software engineers, ML researchers, who don't really care so much about the wetware, but really want to control the software. And so this brings this whole notion of what is a biological computer. And our thinking internally of what a biological computer is that it's your traditional computer, hardware and software. But in addition to those two, you have a third vertex point, which is the wetware. And what's fascinating is that this gives you an extra lever to actually change the overall parameters of the system. So to give you an example, the original Pong paper was using wetware that came from mice, so those were primary rodent cultures, and also human-induced pluripotent stem cells. And what was interesting was that we showed that the human cells outperform the mice cells, which is great for humanity, right? At least we're still smarter than mice. But you can also start thinking about changing the wetware. So for instance, potentially using cells with epilepsy, seeing how they perform, and then using drugs to change the parameters of the operation of that system. Conversely, on the software side, right, you could try a different game perhaps, or a different simulation to give you a different outcome. So some other games that we've looked at was the Chroma Flying Jumping Dinosaur game, but there are many other ones, and the question becomes what happens if you start feeding in streams of information coming out from real-world sensors or from the internet. And this is something that we're working on through our APIs and SDKs to try to abstract away the complications of what an action potential is, how do you stem them, and so on and so forth. And one example that I talked about, this epilepsy flow, there's actually a poster that we had, and if anyone's interested, you're more than welcome to find me, where what we've actually done is we've taken cells from patients with intractable temporal lobe epilepsy, and we've plated them on the system, and we've seen epileptiform seizure-like activity on the cells. And to no surprise, they don't learn how to play the game, the Pong game. But what's fascinating is that if you treat those cells with the anti-seizure medications, not all of the anti-seizure medications work, but a select few do. And that reduces the seizure activity. And with that reduction in seizure activity, they start learning how to play the game again. But what an interesting observation we've seen is that not all drugs have the same effect. Some drugs actually cause a minor, or sometimes actually even a major cognitive decline in the cells. And this is actually fascinating because one of the major reasons of patient discontinuation from medications like anti-seizure medications or even chemotherapy is this brain fog or chemo brain that people talk about. And this is something that we've been looking at as a potential application, where in the future you could imagine taking blood from a patient, running an assay. So rather than going in to see a doctor and getting a prescription, coming back 6 weeks later and saying did it work or were there any side effects, you get the answer in a dish that says don't bother with drug A to D, go straight to E, because we didn't see any side effects and it had a very good response to the medication. So this is the vision of the future. This is what we call the CL1 system. And this is actually a prototype device that I brought up from our lab. And what it is essentially a system to keep these cells alive over extended periods of time. If we can get the video, please, and we can see how that kind of works. So this is a lab prototype device. And what it is that, well, this is the same thing, but in a different form factor, that has all the components to keep cells alive outside of the body. So we have triple diastolic pumps equivalent to the heart. We have a gas exchange system, filtration units, so lung, kidney, brain in the center, of course, and the ability to keep the cells at a constant 37 degrees Celsius, which is core body temperature, and a feeding and a waste mechanism. So with that in mind, we would love to start thinking about how could you scale these cells in order to start programming them, using them for drug discovery, and so on and so forth. Can we get the video off, please? Next slide. So here are some of the papers that my team and I have published. Very excited to say that the critical dynamics paper recently was published, peer-reviewed in Nature Communications. And if anyone is ever interested in what's called the critical brain theory, where neurons, or the brain is how to describe it? It's a complex theory, but I'm going to try and simplify it. Works at the edge of chaos, in the sense that it's a complex dynamical system, like water, and water has this critical point at 0 and 100 degrees Celsius, where water molecules have a 50% chance of turning into steam or remaining as a liquid. It turns out that neurons also have this critical dynamics, where in order for information processing to happen, you need to have the Goldilocks zone of just enough electrical activity and not too much. Because if you have too much, you end up causing an entire network to fire spontaneously. And that is essentially a seizure-like waveform. Or conversely, if you don't have enough baseline activity, your action potentials do not propagate far enough. So it turns out when we've examined the dynamics of the system when playing Pong and versus in rest mode, the neurons actually exhibit this criticality point while engaged in a task. And we think this is extremely fascinating as a way of looking at how we could use alternative measures for determining information processing in these biological systems. With that, that's the end of my talk, and I open it up for any questions.
Thank you very much, Han. That was completely fascinating. We've only got 3 minutes. We're going to have to be really efficient with our Q&A. So one of the things that I wanted to ask you about, having taken diligent notes in the background, there's a statement in the synopsis where it talks about the organic mind being a better learner than any digital model. Now, we keep being told that artificial general intelligence is going to be a super intelligence that's potentially going to destroy humanity. Are you making the opposite case?
Yes. And the reason for that is, it's one of the papers there, and actually was a poster at NeurIPS. You have to think about it in terms of sample efficiency. Now, what do I mean by sample efficiency? That paper compares a reinforcement learning, well, actually not a, 3 different reinforcement learning algorithms. And what we then did was we said, you're going to get the same amount of data, the same amount of frames that the biological system has, and we're going to evaluate how well you learn how to play the game in real time. And it's not surprising once you think about it. The biological systems actually outperform reinforcement learning. Now, if we think about all of this talk about the superintelligence, it's great. But we have to remember that GPT-4 or GPT-X has learned to be this good by ingesting the entirety of the internet. Right? Now, the question is, how do we, as humans, still get around, communicate effectively, problem solve, and have abstract reasoning with a fraction of the information on the internet?
I mean, we could take reassurance that most of the stuff that's on the internet is either porn or wrong, right? So
or
that's
Reddit
how
or
I sleep
4chan.
at night. Right.
Yes. So I think it's fair to say, and you know, this is also going back to the energy point of view. If there's 20 watts of energy, right, that the brain consumes, that's essentially, if we put 10 subject matter experts in a room, still cheaper to run than a single GPU in terms of energy efficiency.
Oh, I like that. So there's a climate-friendly angle to your argument.
It certainly is.
But can we outsmart superintelligence?
Very great question. And
if we're augmented in the way that you've described.
Well, I think that's what Elon believes in, and that's the reason why he's trying to even the scores by connecting us up with machines.
50-something seconds left. I'm intrigued in your training as a medical doctor and how you made the path from that to what you're doing now. How is that informing your view of what it's going to mean to be a healthy, happy human being who's flourishing in this brave new world of AI?
So I think, you know, and this is a really important thing with any technology, which is that it has to prove its reason for existence, right? It has to be a net good, just like things like fire, right? Could be used to cook your food, could be used to burn someone's house down, but we didn't outlaw fire because there was more good to be had. And this is the angle that we're taking, and my perspective of this technology, which is, sure, yes, we could do a lot of interesting AI tasks and so forth, but the more immediate good, more immediate impact that we can have is, can we use this for screening for compounds for epilepsy, for better treatment of neurological conditions? Could we use this as an in vitro model for testing for dementia? I mean, this is the brave new world, and I hope that we could be part of that journey of discovery and hopefully eradicating or curing these intractable diseases that we have today.
I mean, that's an inspiring note to end on. Thank you so much. Please join me in thanking Han.
Thank you.
Thanks a lot. It's just nonstop up here. Nerding is exhausting, but I've had enough coffee to keep us going at least until lunch, which, by the way, will be at 12:40. So at 11:35, so in 3.5 short minutes, we've got Breaking Through the Cognition Barrier to Discover Novel Therapeutics with another doctor, this time Dr. James Field. So stick around if you want to hear more about that. We'll be on in just a moment. Back in a flash. Hello. Oh, what a lovely picture of James, who's about to join us on in just a moment. Not flirty at all. In this presentation, Lab Genius's CEO and founder, Dr. James Field, is going to describe how smart robotic platforms that combine AI, synthetic biology, and robotics are being used to break through the cognition barrier, which I'm really hoping he's going to define for us, to solve some of the toughest challenges in the drug industry. So without further ado, Dr. James Field, the stage is yours.
Hi, it's great to be here. We've had some incredible talks today. the amazing complexity of biology has been sort of unleashed upon us this morning. And maybe I wanted to take a slightly different tack now. And rather than starting with something really complex, I wanted to start with something really simple. As the complexity of a problem increases, the number of people who can solve that problem decreases. Okay, it's pretty obvious, right? But let's take that to its logical conclusion. As we continue to ratchet up the complexity of the problem, the number of people who can solve it globally, I'm talking about all 8 billion people on the planet, drops off to 0. And it's at that point when nobody can solve problems because they've got so complex that we've hit up against something that we term the cognition barrier. And the cognition barrier is a massive issue, not just for me, but for you and everybody else on the planet. And the reason for that is the problems that we need to solve most, those that are most impactful in terms of our health, our prosperity, and perhaps even the survival of the species, they sit on this side of the cognition barrier, the side that we can't solve. And so the biggest challenge that we face here today is how do we break through the cognition barrier? And to do that, we actually need to reimagine what the scientific discovery process is and what it could be. And I think retrospectively, we'll almost look back at this point in history almost as a point in which humans transition from being central to the scientific discovery process to being integral to, but not essential to it. And the work that we do at Lab Genius is all about reinventing the scientific discovery process so we can autonomize the discovery of novel therapeutic proteins to treat people. Now, this idea that we can autonomize the scientific discovery process, it's not new. People have been dreaming of building a robot scientist, autonomous systems that can do science for generations. But actually, now is the time in which these novel ways, these novel smart robotic platforms that are able to run scientific processes are actually coming online. Now, I'm going to talk a little bit more around how these work and how we're using them. So the basic architecture for these systems is pretty well established, and it's actually very intuitive. And it's actually very similar to the way in which we do science today. So in this scientific discovery process, you start off by generating a hypothesis. And if you're a human scientist, of course, that happens up here in your head. And then you test that hypothesis. You test it physically in the real world. And again, if you're a human scientist, maybe you do that with your hands. But with a system like this, the hypothesis generation happens in the world of bits on a computer, and the hypothesis testing happens in the real world, but rather than being done with your hands, you can do it with robots. Now, the real challenge when it comes to building a system like this is that you've got to really tightly integrate the world of bits and the world of atoms, so information can flow seamlessly between those two worlds. And that's a real challenge. And in my view, that has been the limiting factor, that integration between these two worlds, that has stymied the development of platforms like this. Now, in the context of the drug discovery process, we can now start to go a little bit more deeper, a little bit more granular. And this is the way in which it works. So we're in the business of defining new therapeutic molecules. And the way in which that process runs is computationally, we'll design a set of molecules. Those sets of molecules will then be fabricated. They'll be made here in the real world, in the world of atoms. They then get tested, and then the information, that characterization data, is fed back into the world of bits to build computational models that are descriptive of the solution landscape for that particular molecular property or set of molecular properties. And then you can co-optimize new molecules, and you can go round and round this cycle and searching through solution space until you find molecules that have the requisite properties. And as I mentioned, the big challenge of building these sorts of systems is that you have to integrate the world of atoms and bits. In order to pursue this ML-driven active learning process, you have to be able to run around this loop exceptionally quickly. And that's not only an infrastructure challenge, that's also an organizational challenge. And if we could jump to the next video, please. So what you see here is the infrastructure that we've got set up just down the road, in fact, 2 tube stops away down in Bermondsey. So in an old biscuit factory, we knocked down several walls, and we kitted out this biscuit factory with all of the equipment required to run the experimental processes that are involved in testing thousands of new proteins. And I'm going to go into a little bit of detail now into how this system works and why it's so complex. So when you come up with that panel of designs, you have hundreds of DNA sequences that the computer generates and says, right, here are DNA sequences that encode protein therapeutics that we believe will be high performing. The next step there is that you've actually got to make those. You've got to make those in the world of atoms. So we use a mass modular cloning strategy to assemble all of the DNA in parallel. So we then have all of these DNA sequences. They've got to go into a bacteria to be amplified up, to be increased. You then got to purify those. You then have to sequence those, and we do that in-house with nanopore sequencing, so we can get that sequencing turnaround in a couple of hours. And then once we've validated that all of the sequences are correct, those sequences, those DNA sequences, then have to go into a mammalian cell so that they can be produced at high levels. You then have to purify the protein, because these are all protein therapeutics, antibody therapeutics, out of a mammalian cell. And it's only then, once you've got that to that stage in the process, that you can actually functionally characterize them. And the functional characterization then happens across a suite of disease-relevant functional assays, as well as biochemical, biophysical developability assays. So you've got this massive infrastructure and this very long workflow that you have to go through, and you have to seamlessly integrate all of those different pieces, so you have the information flowing through it in a highly automated way. And really the challenge here is how do you run around that loop incredibly quickly at high throughput and generating data that's both really clean, but also you can control for the inherent biological noise in the system. And that's not only a technical challenge, but that's a massive organizational engineering challenge. Because whilst the argument here is, humans are no longer central to the discovery process, as I mentioned, they're incredibly integral to it. So actually building these platforms takes a very multidisciplinary team of exceptional scientists and engineers spanning all different disciplines, from data science to software engineering to protein science to cell biology, synthetic biology, etc. And bringing all of those folks together to work together to build out one of these platforms. Back to the slides, please. Okay, so you've heard a little bit around, I guess, the concept behind one of these systems and the kind of infrastructure that you have to set up in order to affect it. But what are we actually using it for? Well, at LabGenius, one of the problems that we're trying to solve is how do we treat cancer better? And the way in which we're doing that is we want to encode logic into protein therapeutics so that they can selectively distinguish between a healthy and a disease cell, and then selectively kill that disease cell. Now, that's something that's incredibly hard to do. But what we found is by running this active learning process and letting the data guide us through the sequence space, what you end up with is being pulled into areas of design space that you would never have explored as a human protein engineer. So you get these quite unusual designs that, again, don't really make sense to us as humans, but they make sense to the underlying models that have designed them. And we find that these are massively improved with respect to the performance. So we found molecules that have a killing selectivity of over 400 times competitor molecules or benchmark molecules that are currently in clinical trials. These results really are incredible and testament to the power of this underlying process. So what I'm going to do is jump now to the next video and show you this process in action. Okay, so here are the molecules that we're working with. These are the proteins that we're engineering with that system that you saw on the previous video. In this case, this is an example of an immune cell engager. So that's a particular type of protein that's able to recruit one of your white blood cells and use it to kill a cancer cell. And it's made up of different pieces. One piece to bind to a cancer cell, a couple of other pieces to bind to a cancer cell. So obviously, here's in a tumor. If you zoom in to the tumor, what you'll see is a cancer cell, and every cancer cell on its surface has a unique postcode, a unique set of cellular receptors. And the molecule is able to dock here as well as being able to dock onto the immune cell. So it can bind to both the immune cell and also onto the cancer. And then it's able to bring those two cells together and catalyze the killing of the cancer cell. Okay, and the challenge, this is not a new form of molecule, by the way, but the challenge with the conventional immune cell engagers that operate like this is they really struggle to differentiate between what's a healthy cell and what's a disease cell. And the net result of that is you get killing of both your healthy cell and disease cells. And if you're a patient, that means you either don't get the treatment because it never got through clinical trials, or you do get the treatment and you have to deal with all of the toxicity events that go with this. Now, using this active learning process, we can search into areas of solution space and areas of design space where these molecules are able to distinguish between the healthy and the disease cells. So we're able to optimize them in a way that you can't using these conventional methods. And with these optimized immune cell engagers, you can distinguish between healthy and disease cell. And the challenge here is one of the levers that you're pulling against is the affinity, the binding affinity of the molecule. You bind too tightly, you kill everything. Equally, if you bind too loosely, you don't bind to anything and you kill nothing. So here you're titrating or managing the binding affinity of these molecules in conjunction with a whole range of other features that you're simultaneously engineering in to ensure that these molecules are not only highly selective for your cancer cell, but additionally, they're highly active and highly developable. So it's that co-optimization challenge that we're solving here. So we're building computational models across all of those different features in parallel, optimizing across them, using this active learning process to create very novel, non-intuitive designs. Okay, so you've seen the architecture of this system, some of the infrastructure that we've had to build out to create it, and an example of one of these applications for it. But maybe I just want to end on a broader thought here. The reason I'm really excited is systems like this that you see here have the potential to transform the whole of the way in which we discover drugs today. And not only that, this can be applied to the discovery of whole other areas of science and technology. So I'm really excited about this next step that we're taking in reimagining the scientific discovery process and the implications that that will have for the future prosperity of humans. So with that, I'd just like to thank everybody and also make a small plug for a panel discussion that's happening later today with some fantastic panelists at 2 p.m. on the future of computational drug discovery. So if you are free and interested in that as a topic, please do join us then. Thank you very much for your attention.
Thank you very much, James. First question, I caught part of your presentation backstage and was listening to the phrase, and I couldn't get it out of my mind, where you were saying something along the lines of human beings are no longer central to this process. Yet you also mentioned the multidisciplinarity of the teams that are needed to get your vision going. So can you talk us through that tension of, are human beings becoming more important, less important, or just differently important?
Yeah, it's a great question. In my view, this is almost like a Galilean moment for science, in the sense that pre-Galileo, or maybe pre-Copernicus, people thought, obviously, the sun went around the Earth. Obviously, not so much. It's the same in science, in the sense that by reimagining the scientific process, what that will enable us to do is to solve harder problems. But humans are still absolutely integral to that. So you can't build these systems or set up the problem spaces without having incredibly talented teams, multidisciplinary teams of people actually building the platforms. But the platforms themselves operate in a way that's quite independent to the traditional scientific discovery process. And that creates some interesting conversations and tensions in the sense that when protein engineers join Lab Genius, it often takes them a while to get used to the fact that the designs of these molecules are actually computationally driven. And you look at these molecules, and then you try and post-rationalize, okay, looks like this, maybe this is the mechanism of action. But the reality is, unpicking the molecule's mechanisms of action, it may not be something that you can actually understand as a human. So I think it's causing us to redefine our relationship with science and the scientific process.
And does this give you a new opinion about the nature of creativity?
Yeah, so what's really, I guess, important to say is that these systems have an exceptionally narrow intelligence, so they're really good at solving very tightly defined problems. And I think the really creative aspect that you see of certainly the team at Lab Genius is actually how do you set up these systems to be able to solve those problems? Because one of the most important pieces is, yes, the system can look in the solution space, this design space, and find high-performing molecules. But it's the protein engineers and the data scientists who sit down at the beginning of a program and actually demarcate the area of design space that's going to be searched. So I think it's a new form of creativity, a new application, and hopefully a more interesting one as well, in the sense that through the heavy use of automation, a lot of scientists don't actually want to be conducting experiments day in, day out, and they're using a different part of their brain.
One of the questions that I've been hearing from some people in the audience is something around the nature of talent. And as we're getting ready to train people to do the kind of work that you're doing, the sort of future of drug discovery, et cetera, should people have a core function? Or are you leaning potentially towards something that's more multidisciplinary, more polymath approach to knowledge, different skills? Like, what are you looking for when you're building your teams?
Yeah, so I think you absolutely do require a core function. We have functional teams across everywhere of the business, and within a functional team, everybody will be, say, an expert in data science or cell biology, etc. But what's absolutely essential is that everybody within those functional teams is intellectually curious, and that they're able to at least understand at a superficial level what's going across in the other teams. And one of the constant bits of feedback I get from folks at the business is it's that interdisciplinary collaboration and discussion that is driving the creativity and innovation.
And are you seeing that talent pool here in the UK sufficiently, or are you having to tap the global talent pool?
I mean, we're really fortunate in the sense that some of our best hires have come internationally. But I would say it's maybe less around the lack of the scientific depth, but more the advantage of bringing in folks who have had experience of the startup ecosystem before and the biotech ecosystem before, in the sense that within other geographies, that's a lot more mature than it is, say here in London.
Right. What are the blockers that are stopping you from, at the moment? Is it just time or something else that's stopping you from realizing your vision fully? Is there anything that, if there are people here in the audience who could wave magic wands that could help you, what would you say, I need to remove X, Y, and Z, and then we can go for it?
Okay, so this is a really boring answer, but whenever a minister asks me this question, I think this is actually the most impactful thing, which is in the UK, the transport system doesn't work at all. And like, it sounds like a really kind of...
Hold on, are you saying leaves on the line are keeping you from...
It's too hot, it's too cold.
Okay.
It's the wrong day of the week.
So transport infrastructure.
But I'm genuinely serious.
That.
When you have a very multidisciplinary team where folks are coming in from Oxford, Cambridge, London, etc. If you don't have a good transport ecosystem, that is genuinely an issue. I know it sounds like super boring and people want some like whizzy bang answer, but that's...
How do you feel about crumbling concrete or childcare?
I also have opinions on those. Yeah.
I thought you might, which is actually really good though, because often when we have these discussions, we can think it's about money or something very ephemeral, and in fact we need the trains to run on time. So for the... Is it Grant? Who's the Minister of Transport these days? They change so quickly.
I asked the Shadow Science Minister, and the answer was, it's not simple. So
it's not simple. Yeah. It's true. And if you could describe your vision of what success looks like for you and how you're going to know when you get there, tell us a happy story.
So for us, the big moment of success came when we were able to really see in the data, when we were running multiple cycles of this process, these molecules were improving cycle after cycle in a really systematic way. So from the kind of the deep science, molecular biology, synthetic biology, data science perspective, that was a real win for us. The next point is seeing these molecules progress into later stage parts of the discovery pipeline and ultimately into patients. That's everything that the team is excited about.
And how far are you from it, do you think?
Yeah, we're still a little bit away from that, but I think we'll get there over the next couple of years.
Amazing. I'm going to let you off a little bit early, just so that you don't feel pressured to say something in 20 seconds, unless you wanted to say, if you could tell the people in the audience to do one thing to learn about this space, what should it be?
Yeah, I think if you want to learn about the space, probably the best thing to do is acquaint yourself with the deepest problems that need to be solved. I feel like there's a big danger in over-indexing on the importance of one technology or another, but it's actually the real problems that have to be solved that should drive the innovation. So I would look at it like that.
Thank you so much. Dr. James Field.
Thanks.
Cheers. Somehow this day has raced past. We have one more talk before lunch. Thank God. Food is coming. At 12:10, we're going to be talking about neuromorphic computing and AI, the 20-watt problem. So stay tuned. Stick around. We'll be back on shortly. Hello. If, like me, you're thinking of lunch in half an hour, I have a little amuse-bouche for you, an appetizer, a starter for your mind. We're going to have this last session on neuromorphic computing and AI, the 20-watt problem. Now, if you, like me, have no idea what any of that means, don't worry, we've got two brilliant people coming on stage in just a second who are going to sit down between two ferns and explain it. We've got Lawrence Lundy Bryan, if you want to jump on stage with us, Lawrence, and Aaron Kirschen. Hello. And I'll leave you to get started with the conversation. Enjoy.
Hi, everyone. Thanks for joining us. I'm hoping that we'll start from quite a high level with Aaron today around exactly what neuromorphic is, how it differs, and why it's important. And we'll get sort of into the weeds around how it's applied to AI and some of the other potential applications. And ultimately, I hope we'll end up on a sort of, prediction type of timeline-y questions. When is this important? When do we think this is going to hit the market? So I'll let Aaron introduce himself first, and then I'll briefly talk about myself, and then we'll get into it. Aaron?
Thanks, Lawrence. Thanks for the invitation. My name is Aaron. I'm co-founder of Semron. We are a startup in Dresden, in Germany, a little bit south from Berlin. You probably know that Dresden is becoming one of the centers of microelectronics in Europe with TSMC and GlobalFoundries there. We are building or developing AI inference chips based on an own semiconductor technology, and so we are happy to dive into that a little bit deeper later.
Great, and I'm Lawrence. I lead research at a deep tech fund called Luna Ventures, and I publish all of my work on a site called stateofthefuture.xyz. And I've done a lot of work into future of compute, new architectures, new type of substrates, and tried to look at the semiconductor supply chain. So looked quite a lot into neuromorphic and its potential. So I'd like to start extremely high level and just ask Aaron, as the expert building here, what exactly is neuromorphic and how does it differ from what we might just consider a semiconductor or a chip, a logic chip today? How does it differ?
So von Neumann versus or
exactly
in general, okay.
Yeah.
I think at this point you are a better expert than I am in that field. So in very high level, in memory computing versus von Neumann architecture, this was a guy called von Neumann who invented kind of the computer architecture we still use for most of the chips. And basically it's just we have a separate memory and separate processor where we calculate stuff and we have a store stuff, so it's separate, and so we have to move the data in between both places every time we would like to calculate something, and we need data from somewhere. So which is fine. For most of the time it was fine in the last 60, 70 years, but now it turns out that costs a lot of energy, because if you move data, you consume energy. And especially for artificial intelligence, we have a lot of parallel operations. And parallelism means you can do that very efficient, but not if you have to move all the data always in between two distinct places. So that's for Neumann. And in memory computing, of course, as the name says, it's starting to solve that with coming up with devices or circuits which can store and calculate at the same time. So we don't have to move the data between the both places.
So I sort of, in my mental model there is just the co-location of memory and compute. And obviously, the closer you are to the memory and the compute, the less you have to travel in terms of the latency there, as well as the energy you have to consume to shuttle the data around. The other key feature is this idea between analog and digital. And could maybe go into a bit of detail there, Aaron, around all of our computing, or the vast majority is digital computation, which is what we have, digital computers. What exactly is an analog computer? How does it differ, and how does it relate to neuromorphic?
Okay, it's also kind of personal take on that, but let's get first into the big picture. Digital is just a signal with two different levels, so you all know that. I mean, we have 0 and 1. And this is something we can handle very well. and we also could handle that very well in the beginnings of compute. So that's why we have that. Ideally, we would calculate with analog signals because they are very efficient, because we can encode a lot of information in just one short signal or spike, for example, whereas with digital signals, we need a lot of time to encode stuff in that. But on the other hand, analog signals are very difficult to handle because you need to be very precise on that, and you have some impacts on that which you can't really predict or correct after that. And with digital, you all have these. You have all these options to check whether there's an error in it, which came from some I don't know, influences from outside or not, which is in analog way harder, as I mentioned. And that's why we feel like this is now the turning point where the electronic industry is capable of handling the challenges associated with analog computing. If that's true, then the future would be analog.
Right. Right. So the benefit. I mean, we think about the first ever computer was an analog computer, right? The difference engine by Charles Babbage. So it started with analog, with just waves and trying to understand, signals, voltage or temperature or any physical phenomena. But it doesn't scale and it's not reliable in the sense, right? I believe it was after World War II that we needed more reliable computers for planes and for analyzing locations of planes in the sky, and we needed to be more reliable. So you convert things to binary, 0 and 1, it's reliable, more scalable. Why then has there been a renewed interest in 2020 or before around analog computing, and what's changed in the preceding years that makes it viable as a new technology?
Yeah. I think it's mostly about artificial intelligence, and that we figured out that we need to handle the energy inefficiency associated with digital compute.
So purely just we're using too much energy and we're looking for new solutions to use less energy.
Yes, and there's another, a second point, which is kind of more recent, but people thought about that 10 years ago already. I mean, it's kind of obvious for like calculating in an Excel sheet, we need a very high precision floating point. But it turns out, because of parallelism in artificial intelligence or deep learning models, we don't need that high precision in the operations, which is really into the favor of analog computing.
Could you explain that a bit more around the precision piece? So what do you mean in terms of why do we not need high precision, or explain what high precision means in that context?
I mean, an intuitive explanation would be we still would be able with our brain to recognize or recognize people, for example, if we just flip one bit in the picture, like a small part in what we see. If we flip that, or if we lower the color precision, we still would be able to say, okay, we're sitting in an audience and there's some stage in it or something like that. So we are very tolerant to small changes or to low precision or to reduction or even to noise. We are very tolerant. Like if you have a blurry filter in here, we would still be able to understand what's going on. So that means, in turn, that we can get rid of a lot of redundant information. I don't need to understand whether you're wearing a red or a blue t-shirt just to understand that you are human, right? And if you are having a deep learning model, which is the task is to recognize humans, then we don't need this kind of information. If you process it with a classical algorithm, you typically would keep the information because...
So you're saying you're processing a whole bunch of information that doesn't actually need to be processed in order to get to the level of accuracy that's required.
Yeah, actually, if you look at a structure of the deep learning model, which is kind of an algorithm, you have the layer topology with a lot of input activations, and you have like millions of that in parallel. And then you just carry out multiplications on that, sum it up, and put a nonlinear activation over the result. But if you flip one of these activations, it doesn't make any difference. And if you lower the precision of most of the values in that, like from you just cut like the last digit in a value or something like that, it doesn't make any difference. The impact is just zero. So why should we compute more complex than what we need? And that's something we knew for like 10 years at least. Smart people probably longer than that. But now we really see that it makes a difference, especially when we saw generative AI in the last year, end of last year, because it turns out for large language models, it's even better, or they are even more tolerant to a lower precision than classical machine vision convolutional-based models.
Clear. Okay, so let's think that through. So you're saying, we'll tie it back to neuromorphic computing. So an analog generally, which is that it is not able to achieve high precision. It's it's a low precision technology, let's say, and up until now, we're running these neural nets and large language models with high precision computing and architectures. And now the job is to apply these algorithms to low precision architectures like analog and neuromorphic. Is that right?
Yeah, I mean, the funny thing is that NVIDIA and all these kind of GPU manufacturers are also having a default, not the default mode, but they have an integer 8 mode, integer 8 precision mode to carry out those models.
Could you explain that a little bit? What do you mean, integer 8?
So usually, if you have a GPU and you have like graphical applications, you have operations in a floating point precision, which means just a lot of. So how are the numbers called after the comma? I'm not a native speaker. You have a lot of
decimal after the decimal point.
After the point, decimal point numbers, and this is something you can represent with a floating point number, for example. But integer 8 means you basically have like 256 different levels where you can represent a value, but not more than that. And it turns out that you are completely fine with integer 8, and now most people think you are even fine with integer 4, integer 6 precision. So just having like 64 or 128 different states what a value can have on a certain point in an algorithm.
Clear. So effectively, you've just described there an ability, like a technique to be able to turn the high complexity into like map reduced, like less dimensionality and therefore less complexity and therefore less processing that's required. Are there any algorithms at the moment that's using integer 8 or any other type of method to run a compressed neural net or a compressed transformer to be able to run on a neuromorphic chip?
Yeah, there are some. In general, we also have to distinguish between training and inference. You mentioned running that. I assume you're implying also inference with that, just carrying out these models, and so the model can does its job, like the task it is programmed for, which we call inference. For inference, you typically need not much precision. You are typically fine with less than integer 8 for most of the models we have today. There are some we have to go into the details a little bit if we think about quantization, post-training, pre-training, but leave that aside for the moment. For training, we still see that we need more precision, more exact numbers to train the model, to adjust the models for its task. But actually, most of the energy is consumed economically. Most impact is on the edge, which means if you carry out these models, it could also be cloud inference, but training, even though it's very expensive, is not what is a limiting factor here. Since 3-4 months, it turns out, okay, we will also see some scarcity in resources for training as well. But I would distinguish between the discussion of precision with training and inference.
Yeah, that's great. Okay, fine. So let's put aside the training in data centers for one moment and talk more about inference at the edge, which obviously has extreme low power requirements, especially if we're talking about smartphones or IoT sensors. So they have extreme low power requirements, space requirements, as in they need relatively small footprints. So this is where neuromorphic potentially has more application areas. Is that how you see it? And maybe you segmented there between training and inference. Is there other segmentations where you think it's most appropriate at the edge? Smaller devices, larger devices? How do you think about it?
Mm-hmm. Yeah. For me, the bigger picture is how do we get these new type of technologies into the market? So we need an incentive for that. It's not just fine to have like a chip in the market with twice energy efficiency and say, okay, people will take the switching cost and say that's fine. It turns out, especially for cloud, no, you have NVIDIA as kind of a monopoly or a monopolist on the software hardware integration with CUDA. So you get a lot of convenience if you have this monopoly for like developers using that chip, and if you can't match that experience, it doesn't matter how more energy efficient.
Right, 2x is not going to cut it when you're used to CUDA. You're not going to switch to a whole entire new chip, which is the Cerebrus C2 problem at the moment, right? Their new chip, which isn't CUDA compatible. So,
yeah. So yes, you mentioned that we have some features, technological features in first place we have to match in order to make a product, not just a technology. And you mentioned power consumption, of course, that's critical. That's why we're talking about that. But it's also the footprint, the chip area. I mean, it's not fine if you have an in-memory computing architecture, which is like 50 times bigger than a classical GPU. So the big advantage of the energy inefficient GPU is it is compact and it's well understood.
Right.
So to meet that, it's very hard. And if you have in-memory computing, and a lot of companies and startups struggle because of that, and if you focus just on one technical feature like energy efficiency, you will simply fail, or you will struggle a lot. So you also have to meet.
You would think that the market would, we are 15 times more energy efficient than running a Qualcomm W2 or whatever the latest chip is. That sounds like a good value proposition. You don't think so?
I think it's not enough because first of all, if you have 50 times more performance for the same power, you also have to explain how you can decrease the cost. If you have a constant cost per performance ratio, you pay the same amount of dollar per like TOPS, then you would also just end up in like paying 50 times more for the chip if you have 50 times more performance.
Right.
So you also have to change that. So no, or yes, the answer to that is it's not just.
Not just. Okay.
It's not enough.
Clear. And okay, cool. So we're getting somewhere. So we've got a sense of how neuromorphic differs. The features in terms of low power, in terms of density, in terms of like footprint, and all of those features, predominantly for edge. We're talking here about inference, but you touched on there some of the restraints, as in the NVIDIA chips, CUDA. You're betting against Moore's law. It's pretty much I know it's breaking down to somewhat, but what we're saying is there's a whole new chip that I assume requires new algorithms or tweaking of existing algorithms. It requires a new supply chain. Like, talk to me about what are the restraints to this being adopted right now?
I don't think it's about the algorithms. With the existing algorithm, we have enough market opportunity with the features we currently think about or see on the roadmap of like smartphone manufacturers to have $1 trillion opportunity. So we are fine with the algorithms we already have. It will improve, of course, and we will see different types of algorithms spiking and whatever.
Well, hold on, sorry, to just go on to that, because I think it's quite important that when you mentioned spiking. So one of the big questions in the industry is, can you just run the existing algorithms that we know and love on new neuromorphic hardware, or do we need new entire algorithms to take advantage? Your claim there is that actually we should just use transformer models and port them, and that's fine?
I mean, we see that transformer models behave quite well or perform quite well in a lot of tasks. So
quite well.
Pretty well. I want to have the better models than that, but I think we have a market opportunity with these models, and then we will see better models. We definitely know that they are not smart as we expect them or expect them to level with humans, of course. So we will see new algorithms, but I think the biggest challenge is to make work what we already have, and not think about what we will have in like 3 years, because we are so far away or we are so far behind with the hardware that we first have to think about that. We can think about algorithms that are better fit to the hardware constraints, but I think it's a very, very it's not a very reliable path to think like that. Ideally, you have more flexibility in hardware by itself and not just like designing it for a certain kind of algorithm, because the algorithm will change anyway.
Right.
So there will be no point where we say, okay, that's the algorithm we go for the next 100 years.
I
So
see.
we have to think about beyond Moore's law. I know there's a lot of dispute around that, but what we know is that we are hitting a physical limit, even if it's not now, but in like 10 years, and we probably get, when we have like atomic layer, when it comes to like how small the transistor structures can be. And we put a lot of resources on that, billions of dollars to develop that stuff, and we get another 10x in like density of or how much transistors we can put on a certain area.
Yeah.
So, and then we have the problem. If we had just 10x increase in the density, but we are talking now about 1,000 times bigger models, even now, then what can we do? That's something we have to change.
Got it. Okay, so what you're saying there is there's a roadmap, and if you can look on the IMEC website, for example, which the industry agrees that 2036 or 2034 or something, we know for each half pitch reduction, what happens sub 1 nanometer, we know exactly how we're going to get there. So we have a very good understanding for the next 10 years of the sorts of level of performance we can hope for from digital chips. But what you're saying is that's great, and we can continue on that line, but we know at some point there is a hard stop.
I would even say that kind of a lie or a stopgap, or not. It's probably a dead end, I would say. I'm not sure whether we will put all these billions required for this roadmap actually when it's time. I'm pretty convinced it will not happen, because the problem is that the cost will not scale. Simply, it's all about the cost, and the cost is often overlooked because it's not sexy. It's a very, very boring topic, but it's actually what makes the difference.
Perfect for a panel. A very boring conversation. No, please.
Sorry for that, but actually that's what makes the difference between not just technology and product, but product and mass product.
Great.
And we have to have that for like chip products. And so we always think about, okay, how can we decrease cost per performance by a factor of 100 or 200 or something like that. And that's nothing which is even...
What's the driver of cost? Sorry, Aaron. Because, okay, this is really important. What you're saying is it's not just this new magical technology. We need to really think about can we reduce the cost of the underlying of the compute. And you're saying well, it doesn't scale. Fine, we can technically build it, but economically there's no point. You're saying neuromorphic is, but what's the driver of the cost? Is it the energy? Do we go back to that von Neumann bottleneck? Like, why is it that, why can we get 10x less cost? What's the driver?
I mean, the promise of lowering the cost is that you put more transistors on a certain footprint without having more cost in variable cost, more variable cost in production. What we see when we see how that scales with mass costs in manufacturing, semiconductor manufacturing, we see that since I would say 7 nanometer, we don't see any a decrease in cost per, let's say, transistor.
And 7 nanometer is sort of roughly where we are. I think the A100, is the A100 7 nanometer? Oh, no, I think it's 5 nanometer process, right?
There's a lot of marketing involved in that.
Exactly, fine. But roughly we're talking about where we are with AI accelerators at the moment, which is 7, 5 nanometers, 4 nanometer N, I think it is, at TMC. But regardless, you're saying that, okay, let's go down to 3 and 2, but the cost will go up.
Yeah.
Well, we sort of see that with even the lithography machines that are required, the inspection machines. The cost is going up, right?
Yeah.
So what you're saying is you have to address the cost, and the sort of design that you're interested in building is actually the key pitch, the value proposition, as we spoke about, it's more energy efficient. You're saying it's going to be cheaper.
Yeah.
Right.
I mean, I think it's not meant to be a marketing pitch here, right? But what we do is, so far, when we published in Nature Electronics our device, which we use, semiconductor device, which we use at Xamarin to build up a new AI chip, to date we are the most energy efficient semiconductor device ever built and validated for AI inference operation. But even with that, we don't see that as a unique selling point, because it's simply, first, it's a nice-to-have trap, and it's just a great technology. But we founded Xamarin to build a product. And that's why we think about cost, and our USP is we have the lowest cost per performance. And the simple trick about that is that we go the same way as a memory did in 10 years ago, when we saw the so-called 3D NAND flash technology popping up. And as the name states, it's just about we stack memory cells on top of each other. Mm-hmm. So we keep the footprint small. And actually, that's what we all have in our pockets in the smartphone. We already have in a micro SD card, we have like 200 layers of memory cells on top of each other. The good thing about that technology is that the most expensive step in semiconductor manufacturing, which is so-called lithography, is shared among all 200 memory layers. Yeah. That means you save roughly 150 times cost per memory cell, something like that. And exactly that's what we do with AI compute. We just take the memory, 3D memory, and put a device or a small modification in that, so it can not just act as a memory, but also calculate. So we turn a memory in an AI inference chip.
So to clarify, essentially the insight there is stack the memory on top of each other, which we already have with high bandwidth memory. That's not necessarily novel, but you're doing, what is it that enables you to do it now that couldn't be done 5 years ago? I'm sure it's not a unique insight. Let's just stack stuff on top of each other, use less space. Surely it's going to be better. So what changed?
So memory is low power, or memory access operations is low power operation. So if you stack something, you have higher density of something. Essentially, if you have 10 compute layers and you calculate 10 times more on the same, in that you have 10 times a higher energy density. And the surface is roughly the same. In the surface, you need to spread all the heat and the energy. So it becomes worse if you scale something in the 3D dimension, or in a third dimension. And with memory, that's fine because it's low power. With compute, it's not fine because it's not low power.
I get it. So memory could be stacked. That's easy because it uses less power. But with logic, you have a problem because it uses much more energy, and therefore you literally can't stack it because the thermal footprint would be ridiculous, right?
Yeah, and now we are in those resistive versus capacitive discussion, because so far what we did is to compute, basically we were just moving electrons. That's what we did. Whether it's in transistors or in so-called ARM-based in-memory computing stuff, which is analog, it's still that we move electrons. And whenever we move electrons, we create noise, and whenever we create noise, we consume energy. Mm-hmm. And it turns out that's a physical limit, and it turns out that it is too bad to have like meaningful scaling, 3D scaling of compute. So that's something we had to overcome, and that's exactly what we did when we started about. Funny story is, even though we started our journey in Dresden, in Germany, my co-founder and I, we actually met in Cambridge on a study trip, and we started discussing, okay, what can we do to overcome the threshold or the physical limit associated with moving electrons, basically. And then we thought, okay, why not doing it capacitive with a capacitor? Because we have electrical fields then, and they can also calculate in an analog manner. Why not just doing that? Yeah. I mean, it sounds a little bit more simple than it actually is.
Yeah, no doubt.
But it works, and actually it works quite well. But nobody needed that before, so nobody was thinking about that, which is our advantage.
So the demand side arrived with large language models and AI to be able to stack the logic. And okay, so let's sort of try and circle back to where we were, which is that the claim, or I think the renewed interest in neuromorphic here is extreme low power, probably at the edge, and for AI inference, but also for other use cases. I'm very interested in event-driven cameras, for example, sort of cameras that effectively are passive until something happens in the camera in 1 pixel, and then is able to adapt and do processing at the edge. This is this idea of a sensor that is not just sensing, it's doing some processing. So I think that's interesting. You could think about awake words, so extreme low power until you say, hey Siri, or whatever it might be. So there's a variety of use cases, but I want to sort of wrap up on like a final question which has been sort of bugging me for a while, which is, the main driver of, you mentioned a driver of cost is to do with, stacking these devices and stacking the modules and reducing the cost, but also it's just economy of scale, volume. And so the reason why the chips we get today are extremely cheap is because we produce billions of them on an annual basis, and we have these huge markets. But for neuromorphic, it's a challenge because you need to know where the demand's coming from and the size of that market to then put in an order with TSMC to produce X number. And in order to do that, you need to prove the market. But you can't prove the market until you've reduced the cost of the chip. So how do you deal with economy of scale, or what's the answer to getting the demand side to be able to produce it at scale?
You have to go to consumer electronics, maybe automotive or cloud at some point. But as I mentioned, cloud is very difficult to attack because of NVIDIA right now and the software, not the hardware. And with the consumer electronics and even with legacy applications like smartphones or devices, you have like a huge market to produce billions of chips. Yeah, even though you have just a few players like MediaTek or Qualcomm who can do that, if you make it into that, you're basically done when it comes to scaling. And from there, you can go to different applications as well. You can go to cloud inference. You can go to automotive, which is not a very attractive market for a startup, to be honest. But you can also start creating new applications. I mean, one of the reasons VR headsets and smart watches, smart glasses, probably also smart watches, is not a huge market or mass adopted right now is because they don't provide the value we need in order to replace a smartphone or to accept paying more for another device. So we need to add more functionality.
I see.
And more functionality we only get with artificial intelligence in that case because we have a non-deterministic input. We have like gestures, we have language, so we don't have a keyboard anymore, which is in a smartphone. So we have to do something about that and probably can create these kind of mass market if we do something on the compute hardware side.
Interesting. Well, good. I'd love to talk more about that in particular, but I know we've come to time. So with that, if you have any questions after, please come up to myself or Aaron. We'll be wandering around. And yeah, thank you very much for your time. Thank you, Aaron. It's been a pleasure.
Thank you. Thank you.
Thank you.
Thank you both, Lawrence and Aaron. Fascinating chat. I hope you go and enjoy your lunch. To all of you, thank you so much for your patience and dedication this morning to getting smarter and nerdier. You've got an hour now, so back at 13:40. But as a preview of coming attractions, 13:40 will be doing an ode to mitochondria with Dr. Parneet Pal, which is going to be really fun and very cool. The future of energy, advanced fission, adapt or die, data-driven pivoting as a key to product market fit with someone who has a PhD in decoding ancient languages. We've got unlocking the future when quantum meets AI. Then, in the middle of the afternoon around 3:40, we've got personalized medicine at scale, introducing the Halogen Foundation model for neurology and healthcare. Longevity from cells to cities, so the micro, it's the absolute macro. And then that will be us done for the day. So go and eat well, relax, hydrate, get some fresh air. We'll see you back at 13:40. lunch, and we're not standing in the queue at Starbucks as I was. Not that there's anything wrong with that. We've got an amazing lineup this afternoon, particularly for those of you who are interested in issues to do with health and the intersection of health and technology. The first one I'm really excited about. This is called, with a Shakespearean flavor, I feel, an ode to mitochondria. Our speaker is Dr. Parneet Paul. She is a Harvard and Columbia-trained physician working at the intersection of business, lifestyle medicine, and behavior change. Please join me in welcoming Dr. Paul.
The real wealth of life on board this planet is a forwardly operative, metabolic, and intelligent regenerating system. And if we don't comprehend and realize our potential ability to support all life forever, we are cosmically bankrupt. With those powerful words, inventor and architect Buckminster Fuller challenged us to build a world that works for 100% of humanity in the shortest possible time. And he shone a light on what must become our imperative in business, technology, healthcare, and political leadership. I'd like to share the story of one of the most beautiful, sophisticated, and deep technologies that's been honed over millennia and working right this minute in each of your cells, which can help us realize this vision and help us get the next 10 years right. So, once upon a time, 1.5 billion years ago, a life-altering catalytic union came to pass. Now, up until then, Earth had been a very different place. There was no oxygen, no ozone layer, just lots of volcanic activity and thunder and lightning. And in these harsh conditions, the first forms of life to appear were two kinds of single-celled organisms called archaea and bacteria. And over time, some of the bacteria developed the capacity for photosynthesis, taking sunlight and carbon dioxide to produce food and release oxygen. And this created an oxygen revolution. And together, archaea and bacteria stabilized the Earth's atmosphere and created the conditions for new oxygen-breathing life forms to appear. As biologist Janine Benyus has so beautifully said, the purpose of life is to create conditions conducive to life and for new life. The most powerful lesson in sustainability, 3.6 billion years and counting. So back to that catalytic meeting, a particular bacterium caught the eye of a particular archaean. And this bacterium was especially alluring because it had the capacity to use oxygen to break down food and release energy, something that the archaean lacked. And the archaean was clearly smitten because before you could say evolution, it had engulfed the bacterium into its body. And scientists call this endosymbiosis, and they hail it as the ultimate merger and acquisition. The bacterium now had a safe place to live, and the archaean had a steady source of energy. I like to think of it as one of the most beautiful and enduring love stories. You see, that engulfed bacterium went on to become present-day mitochondria in all cells of plants, animals, and humans. Mitochondria, the center of energy, metabolism, and regeneration that has powered the evolution of all complex life on Earth. Now, I trained as a physician, and I'm constantly in awe of the human body. It's truly a wonderland. Whether you're awake, asleep, or dreaming, 14 quadrillion mitochondria power more than 30 trillion cells in your body, and they fuel the miracle of your everyday life experience. Everything from eating a delicious meal, to holding your loved ones, to saving the day at the office with a brilliant idea. Heart muscle cells have some of the most number of mitochondria, up to 5,000 per cell. And this allows it to beat 100,000 times every day, pumping 5.6 liters of blood 3 times per minute through your body. That's traversing a distance of 19,000 kilometers every single day. In addition to being the container for the sweetest of joys, the most profound sorrows, courage in the face of fear, and the fiercest love. Despite being the owners of such sublime beauty, we find ourselves in a peculiar predicament in life and business. In the Anthropocene, this human life has created the conditions for its own demise and that of planetary destruction. Climate change, biodiversity loss, soil depletion, ocean acidification, wildfires, social injustice. Our planetary house is clearly on fire. But so is our body. And this internal personal energy crisis is not just metaphorical, it's biologically literal. And it results from a breakdown of metabolism in our mitochondria. Metabolism is just a fancy word for all the hundreds of thousands of life-sustaining chemical reactions that break down food to produce energy and to build all the proteins in our body and remove waste from it. And when metabolism breaks down, levels of cellular inflammation, that smoldering fire in our cells, goes up. Inflammation is the body's natural immune response to any kind of injury. So think about all the stressors that you inflict on your body as part of your frenzied daily lives, all the physical, mental, emotional, and environmental stressors. And just like carbon dioxide levels in the atmosphere, levels of cellular inflammation in our cells is at an all-time high. Inflammation is the starting point for most of the chronic diseases that you and I worry about for ourselves, our families, and our teams. Everything from heart disease to stroke, to cancer, diabetes, obesity, Alzheimer's, Parkinson's, autoimmune disorders, and all manner of mental health disease such as depression and anxiety. In fact, 3 out of 4 of us at this festival and globally will suffer from one of these diseases during our lifetimes. But here's the worst part. Not only is inflammation the starting point for disease, research shows that even low levels of inflammation affect our moment-to-moment decision-making. You heard that right. Even low levels of inflammation affect our moment-to-moment decision-making. And this is because biologically, inflammation is interpreted by the body as a threat to its survival, and it makes us want to hold on and grab on to whatever resources we might have in front of us in that moment. This makes us more impulsive. We are unable to delay gratification. We resort to short-termism. And we become trapped in this kind of tunnel vision where we become really self-focused. Trust and empathy for the people around us crumbles. We don't have access to our best ideas, and we get stuck in old patterns of thinking and behaving. So think about the implications of this level of inflammation and this internal personal energy crisis for ourselves as individuals, as consumers, as businesses, and as politicians. Rampant consumerism, the desire for unmitigated growth at all costs, loss of trust in each other, in state and institutions, addictions to our technology, addictions of all kinds, social injustice. Is it really surprising then that despite having all the technology and resources at our disposal, we are not moving at the speed and scale required to meet our health or sustainability targets? As individuals and businesses, we postpone our health and well-being for the tomorrow that never comes, and we show up at work every single day with the best of intentions to have the greatest impact. But we're tired, we're depressed, we're anxious, we're lonely. We reach for the junk foods and caffeine to keep us awake during the day, and reach for alcohol and medications to lull us into some semblance of rest at night, all the while holding on to old patterns of behavior, burning ourselves out, and perpetuating the systems that are nothing but a reflection of our inner, degenerative, unsustainable selves. At work, this is reflected in skyrocketing rates of stress, burnout, and illness that account for the majority of our healthcare spend. And even though the pandemic and the Great Resignation, the Great Reset helped to shine a light on the need to address this need for well-being in the workplace, we haven't really seen a significant shift in the levels of burnout and this internal personal energy crisis at work. And this is because we have forgotten to address one of the key root causes, which is biological. And all roads point to mitochondrial health. Now, when it comes to mitochondrial health, I have good news, and I have even better news. So the good news is that we have the science. We know what works. And the even better news is that when we put that science into practice, when we adapt our lifestyles to take care of our mitochondrial health, data show that we can prevent 80 to 90% of all those diseases that I mentioned. And we can start to make wiser moment-to-moment decisions for ourselves, our businesses, and planet. And this is exactly the kind of work that I do with teams and businesses and organizations, where we take the best evidence-based strategies from lifestyle medicine, neuroscience, and behavior change, and use that to make our biology work for us and not against us. And once we start to make these changes in our lives, the connections between personal and planetary health become abundantly clear. We learn, for example, that when mitochondria break down food, the quantity and quality of the energy that they produce determines the quantity and quality of our focus, creativity, and endurance. Now, mitochondria love whole foods grown in microbiome-rich soils because from an evolutionary standpoint, that's where the energy conversion is the most efficient. So think of those foods as the clean, renewable energy for your cells, and junk and processed foods, on the other hand, that's like burning fossil fuels in your cells because they produce a lot of inflammatory byproducts. And but this production of energy is one of the least interesting things that mitochondria do, because just like outer sustainability is so much more than just fossil fuels and carbon dioxide, it's about biodiversity, it's about regeneration, it's about restoration and social justice. So too, mitochondria are much more than just energy-producing cell batteries. Think of them instead as the mastermind that balances growth versus repair in your bodies. So mitochondria help to keep all of our cells within a very narrow, safe operating zone called homeostasis. It's a narrow level of pH and temperature beyond which our cells cannot survive. And to do this, mitochondria regulate up to 2/3 of our epigenetics, the mechanism that decides which one of our genes is turned on or off at any given moment. Now, mitochondria are constantly listening to the way that we live our lives. They're constantly adjusting to the exposome, which is the collective life experiences all the way from conception till the day that we die. And mitochondria are listening. They're listening to the way that we eat, move, sleep, manage our stress, the environments that we expose ourselves to, the time that we spend in nature, how much social interaction that we have. And they take this information and respond to this stimulation by changes in DNA methylation and histone modifications on the genome. And they regulate inflammation levels up or down. In fact, this kind of epigenetic control we now know is at the center of aging and longevity. And this kind of interaction between our outer ecology and our inner ecology makes it abundantly clear that we can't separate personal from planetary health. Now, mitochondria don't work in isolation. They track the movement of the sun in the sky, and in the morning when we wake up and the sun is out, they help turn on our circadian rhythm, this beautiful symphony of gene expression that's optimized for growth. So this is the time to eat, move, and build. And then in the evening, as the sun sets, the music changes, and gene expression shifts to one that's focused on rest and repair. This is the time to sleep and to dream. Mitochondria also run some of the most efficient circular economies inside the cells. They take old damaged DNA and cell parts and convert them into new sources of energy or building blocks for the cell. This process is known as autophagy or mitophagy. They are also in control of a process called apoptosis, which is programmed cell death. So anytime old cells die, they are immediately replaced with new ones. Your bodies have an incredible capacity for regeneration. Just in this last second, 10,000 of your lymphocytes were replaced, and your gut lining renews itself every 2 to 3 days. Now, while doing all of this, mitochondria are constantly conferring and collaborating with our microbiome, the trillions of bacteria, viruses, and fungi that live on and inside our bodies, especially our gut. And the interaction and exchange of information between the gut microbiome and our mitochondria are crucial for our digestion, our immunity, regeneration, and our mental health. Together, they're responsible for the production of many hormones or neurotransmitters, including dopamine and serotonin, which determine our moods and our motivation. The more biodiversity there is in soil and the more diverse the food on our plate, the more biodiversity there is of our microbiome, the better our health. You can see clearly now that to harm the earth is to literally harm the self. So to put it all together, mitochondrial health is truly a fractal of planetary health. And we can also start to see that health is not something that happens at the doctor's office. Health is an emergent property. It emerges from the systems that we surround ourselves with. And so by taking care of our lifestyles and by starting with our mitochondrial health, we can start to show up with greater levels of focus and creativity and innovation. In 2022, the Earth for All report, which was a 30-year follow-up to the 1972 Limits to Growth report, calculated that right now we have all the resources we need to build well-being for all on a stable planet within just 1 generation. The investment required would be just 2 to 4% of our global income. To me, that sounds like a no-brainer, but they left us with this provocation that it remains to be seen whether we as a collective humanity will make these turnarounds a reality. It reminds me of what environmentalist James Speth famously said, that the most challenging problems when it comes to the environment are not climate change or biodiversity loss, they're human selfishness, apathy, and greed. And he called for a spiritual and cultural transformation. In the same vein, in 2022, the Intergovernmental Panel on Climate Change, the IPCC report, for the first time mentioned the need for an inner transition in order to be able to meet our outer sustainability and transition goals. Clearly, we need all the solutions. We need the outer technology and AI. We need to do the inner development work. But we must not forget that in a moment of crisis, and we live in an age of polycrisis, we can't outrun our biology. Our behaviors don't rise to the level of our psychology, they fall to the level of our cellular energy. And so with all due respect to James Speth, I think beyond a cultural and spiritual transformation, we first need to have a biological and health transformation. It's the root that informs how successful all of our other efforts in business, technology, and global leadership are going to be. And yet, as human beings, we're not just simply made of cells, we're made of stories. And for too long, the story around health and sustainability has been a dismal, disempowering one. It's been unidirectional, only pointing to the downstream deleterious effects of climate change and biodiversity loss on our health. It's time to flip the narrative. It's time to take back our power quite literally and shift the paradigm in the other direction. By starting with and taking care of our mitochondrial health, by lowering inflammation and making wiser moment-to-moment decisions, we can make our personal health an asset and not a liability in the sustainability transformation. We can start to move closer to that vision that Buckminster Fuller had of building a world that works for 100% of humanity in the shortest period of time. The real wealth on board this planet is a forwardly operative, metabolic, and regenerating system. And nature is constantly moving forward to the next best iteration of the system, this next best iteration of life. More beauty, more complexity, more diversity. And since we are part of nature, it's imperative that we keep in mind that our health and the health of the planet depends on us remembering where we came from as we move to this next version of humanity. This has been beautifully captured by writer D.H. Lawrence when he wrote, "Oh, what a catastrophe for man when he cut himself off from the rhythms of the year, from the unison with the sun and the earth. Oh, what a catastrophe, what a maiming of love, when it was made personal, merely personal feeling, taken away from the rising and setting of the sun, and cut off from the magical connections with the solstice and equinox. This is what is wrong with us. We are bleeding at the roots." It's time to remember that life-altering catalytic union 1.5 billion years ago between Archean and bacterium. And listen to the clarion call, the song of our mitochondria, calling out to us to take back our power, calling back to us to fall back in love with our biology and to make this next chapter of humanity the most beautiful love story, to once again become the life that creates conditions conducive to all life. Thank you.
That was highly edifying. Thank you so much for that talk on mitochondria, which I think many of us were perhaps underappreciating, but now will not.
Thank you.
Question for you.
Yes.
One of the things you were talking about mitochondria governing was things like in the morning, it's sunny, it makes us want to wake up and get active and move, but then in the evening, as it starts to die down and get darker, we want to rest and sleep and dream. What's going on with night owls? Why are some people more active at night if that's happening?
Yeah, so there's lots of interesting research in that area. So you may have heard the statistic that it's like a third, like the morning risers and the folks who are sort of in the middle, and then the night owls. We're actually finding out that that's not true. So the night owls are a real true night owls are a minority. And most of our night owl behavior is an adaptive behavior, especially in our teens and when we're younger. And so there's a genetic component to that tendency to be a true night owl, but the rest of it is just adapted behavior. So if we wanted to switch that, we can easily do that by shifting the timing of our meals, the timing of our movement, and exposure to light.
So could you turn yourself into a morning person if you aren't a self-described morning person?
You could, yes. In fact, there's very good research that's come out recently that shows that you can do that.
Really? That's fascinating. Other questions that I had was around the role of inflammation and what you were talking about with both the health of the planet and how we treat the planet affecting our body. Made me think about so many people who, for instance, live in London. The air here is so filthy that there's a huge amount of people who've had adult onset asthma. So they didn't have asthma, they weren't asthmatic as children. They moved to London and then they get asthma. Can you go back and stop having asthma if you were to leave London or if we somehow cleaned up the air?
I think we should never, ever underestimate the ability of our biology to regenerate and to heal. Like I said, you have to create the conditions for your biology that are conducive to that kind of healing. So yes, absolutely, moving away would be a great first step, but not all of us have the luxury of doing that. So we could at least try to, use some filters at home if that's available, the air filters. But absolutely, if we were to take ourselves away from that environment, or if that's not possible, because not all of us can just pick up and leave, the other place that you can sort of target for those kinds of sensitivities is your microbiome. So if you strengthen your gut microbiome, which again, because of the diets that we eat and the stresses that we expose ourselves to, when that gut microbiome breaks down and we lose the biodiversity, it increases our predisposition to allergies, including asthma. So that's another step that you can take in addition to moving away from London.
So would you, if you can't move away from London, try probiotics.
From food.
Fermentation.
Yeah, fermented foods, fiber-rich whole foods. Yeah,
Right.
The jury on probiotic supplements is a bit iffy.
Okay.
Yeah.
Well, this is a post-lunch audience, so I think we're all going to digest that information along with your fantastic talk. Thank you so much.
Thank you. Thanks very much.
I'm a night owl with asthma, so sorry those questions were for me. I hope you enjoyed them. Moving on, at 2:10, so quite soon, we're going to have the Future of Energy Advanced Fission. That's Caroline Cochran. She is the co-founder and COO of Oklo, which is developing advanced fission power plants to provide emission-free, reliable, and affordable energy. Sounds good. So, see you in a few. Okay, it's time to get off Twitter, stop emailing, stop WhatsApping, and tune in because we're going to do physics. I need everybody's brains locked on. We've got Caroline Cochrane coming on stage in just a moment to talk about the future of energy, advanced fission. We're also going to have Q&A at the end. So I will be up here asking questions, so don't worry if you don't have any, but if you want to, we're going to have a mic circulating, and you can gesticulate wildly, and we will call on you. Caroline Cochrane, come on over. Good luck.
Thank you. Yeah, my name is Caroline Cochrane. I'm the COO and co-founder of Oklo Inc. Oklo is a company using advanced fission to make clean power plants. What is fission, you might ask? Fission is the reaction in the atom where a neutron splits the atom and creates a lot of energy. Advanced fission is a way we can use that same fission reaction like is used in nuclear power plants, traditional nuclear power plants, and actually use it in a way that we can make small power plants that have inherent safety characteristics and can even use nuclear waste as fuel. So let me first say I'm just really excited to be here. The energy here is amazing, and each one of you, and I suspect, as well as such a large group of people, are thinking about so many different solutions for the things that plague our world and for improving our futures. And so I'm really excited to be here. I'll say, as I was going on my own journey, thinking about where I want to invest my life and improve our futures, I was in undergraduate school, I was learning about energy, I was a mechanical engineer, and I was really excited about being a part of thinking about where I was going to put my life next. I learned about nuclear power in that time period, and like many of you, I was thinking, is that really safe? Is that really useful? Isn't that old? And I learned it's actually quite safe, and it can produce incredible amounts of energy for any unit of input that you have. So I was really excited about that potential. I learned more about it, and I actually decided to work for a year in startups and then apply to graduate school where I got into MIT for nuclear engineering. And I was so interested in that fact, but actually while I was at MIT, I learned my co-founder was there, and he taught me more about how you can actually even use advanced fission to utilize waste as fuel and convert it into clean energy. And it was in those times that we started kicking around the ideas that became our company. And I also learned about, how nuclear energy has actually had the capacity to decarbonize whole countries. So France was able to largely and deeply decarbonize using nuclear energy in the past. At the same time, we don't have to do it the same way it's been done before. So that's how really our company began. One of the metrics, if you can boil it down to one metric, is life cycle carbon footprint. And the Intergovernmental Panel on Climate Change, IPCC, has done recurring assessments of the life cycle carbon footprint of different energy types. And here on this graph, you can actually see several different types and how they compare. And this is a log chart, so hopefully you're familiar with that, but it actually means each line is an order of magnitude larger. So the differences grow exponentially. You can see all the fossil fuels, biomass, et cetera. The life cycle carbon footprint is quite high, right? But this allows us, the log chart allows us to see down into the other energy types like renewables and fission. And even between those, there's some differences here that are helpful to be able to see, but you can see all of them are kind of on that lower end. And when I think about the future of energy, as we're discussing here at this conference, it really has to be about getting down to the lowest life cycle carbon footprint, right? To produce energy which humankind needs and wants, but do it in the least impactful way and the way that saves the most time and space and resources for nature as possible. So that is another thing that just gets me out of bed every morning, but also drew me to doing this in the first place. Another way this can be illustrated is actually a golf ball. So your entire lifespan's worth of fuel to power your life using nuclear fuel would be in the size of a golf ball. So that illustrates the kind of energy density we're talking about here. Fundamentally, the physics of it is that, a single fission reaction produces millions of times more energy than a single combustion reaction. So combustion being used in biomass, biofuels, fossil fuels, et cetera. So when you have that incredible energy density, there's so much more you can do with something, ultimately making it hopefully not only more lower life cycle carbon footprint, but hopefully also less expensive as well. And to illustrate the expense and the materials needed for any different energy type, so we've talked about life cycle carbon footprint, the amount of materials. Here you can see, and it kind of keeps zooming in because you wouldn't even see it if we try to put it on a chart. Fossil fuels, the amount of fuel needed per energy output is huge, right? And then we have to zoom in, and you can see how basically some renewables and fission compare. And even below that is fission in terms of the amount of materials you need to make energy. One of the neat things about what we're working on is not only that, but actually recycling that small amount of fuel and recycling it over and over. And so that's actually the next thing I'll be talking about. But also, when we have lowest amount of materials, obviously here we're talking about climate change and emissions and how do we reduce impact on the Earth. But I think the only way we're really going to get there quickly is if it also makes sense economically. Generally speaking, when humankind gets to these choices of like, well, will I do this thing if it's significantly more expensive, even if it's the right choice, and if you can make the right choice, also the least expensive choice, which is our vision, then it makes the change happen not only faster, but be not a single question really for people when they're thinking about how they want to have their communities be powered, have their businesses be powered, and so forth. So business model is a huge part of that, right? Lowering the costs. If you have the least amount of materials, you also have, hopefully, the least amount of cost. But when we think about the future of energy and how far into the future can we power ourselves sustainably, often I get the question, what about fusion? Well, isn't that actually the fuel of the future? And as soon as that comes along, you'll be obsolete. And maybe this is a little bit of a playful jab. I think there's room for everything. Energy is by far the biggest market in the world. We need all the solutions we can get. But one of the things that's potentially quite interesting to see is this chart here. We can power the world off of nuclear waste existing in the world for over 100 years. So that's what you see in the first bar, is actually over 100 years, just existing waste on the planet, we could power the entire planet for over 100 years. So it's not even that much. You might think, oh, well, it must be a lot of waste then if we can power it. There's just traditional nuclear power plants use only about 5% of the energy in the fuel. And power plants like the ones we're looking at using, which utilizes what's called fast fission, can actually fission the remainder of the energy in that waste. So that is where that energy is coming from. It's actually a small amount of material. We know where every basically atom of it is in the world, but it can power the world. But then you think about the rest of what our stardust gives us here on this planet. Mined resources and everything else as we look forward in the future. What can we do with fusion based on earthly resources, et cetera? And so you can see actually using all of these resources on the planet, using emission-free power, we can provide power for actually longer than we expect the sun to be around. So that's an interesting thing when we're thinking about the incredible power resources we not only need now, but in decades in the future, hundreds of years in the future, and many visionaries and futurists are thinking about what do humankind look like? What does our economy look like? What does our energy look like? Maybe even thousands and millions of years into the future. And so it's a really fascinating thing, but it's also an important thing to recognize is that there's a lot of energy wrapped up in the atom here on this planet that can allow us to spare the planet as much as possible. So it's hopefully an exciting thing to leave you with as we think forward, and thank you again for having me. I think Stephanie's coming out. She was going to ask more questions, I believe.
Apologies for leaving you for one second. I dropped my papers.
I went early.
I carry paper because there's no risk of running out of power or of being hacked. There's a risk of dropping it on the floor. So apologies for that. That was an absolutely fascinating presentation, and it had me thinking about what you and I were talking about before you came on stage, which is the energy needs of generative AI. So, one of the big secrets of generative AI is how much more energy intensive it is than ordinary search, for instance. So if you've got every business and potentially even governments thinking, shit, we have to integrate large language models into our operations because we don't want to be left behind, their energy bills are going to go up. And their water bill is going to go up as well, because it takes more water to cool the entire system, but also the data centers. So my question for you is, if we are truly to use generative AI in a good and constructive way, but be kind to the planet and be energy efficient, do we need to be also thinking about a new energy source? And is this an option?
Yeah.
What are your thoughts?
It's a great question. And with all the discussion of AI, of course, the chair of our board is Sam Altman. He's been deeply involved in AI. And the way he sees it and the way we see it too is that abundant energy is abundant intelligence. They're intricately entwined. And so
what does that mean, though?
Yeah.
That sounds like a very Sam Altman phrase that I don't know what it means.
Yes, yeah, you need a ton of energy, just like you were saying. So when we talk to data center providers who are making huge commitments in terms of decarbonizing, they're, especially around the world, but maybe the closest example I have is in the United States, they are looking for those energy supplies and not finding them, to the point that they may have all their plans drawn up for a data center. They know they need to expand because of the needs of AI. In fact, they need to build whole new data centers because the type of compute needed is, as you know, a much more intensive type, requiring different types of servers, et cetera. They are being told by utilities in those areas, you can't build here unless you bring your own power. So it's an existential threat for data centers in general, but AI's expanse in the broader sense, to have power generally located near where the data centers are. So when we've looked at that, we have small power plants that can run 24/7, which is important. I think a lot of these data center providers have been parts of building up solar plants, trying to buy renewable energy credits, et cetera. But when they think about truly decarbonizing the electricity going to their data center that has to be up 24/7, they need a clean energy source that can do that literally 24/7. There's really not much other than nuclear that can provide that.
So is that an advantage for a country like France that has a nuclear fleet compared to, say, the UK?
I think that it is an advantage in terms of their power is very clean and it's very reliable. And you don't need to refuel it except once every few years for traditional power plants. For our power plant, it's once every 10 years. So the time that you need to have downtime is very low, which is, that reliability is essential for data centers. But is any one country ahead? I don't think so too much, because what we need to do is build more. And so that could happen anywhere.
So this could herald a boom.
Yeah.
If you're in the energy providing business, this is your time.
It's a very exciting time. It's a daunting time. It's an exciting time.
Do you feel, though, that companies are being transparent enough about their energy and water requirements? Like, is that going to be something where we could see, if you're looking at the regulatory landscape, and where we might see the European Union or, God forbid, even the United States get its act together and actually start to say, because we're trying to have a climate commitment, we're looking at sustainable energy, we're going to be requiring companies to report on their energy use, their water use, and their sources thereof. So maybe you don't locate in a hot place like Arizona for your data center. Maybe you're going up towards the Great Lakes. Or here in the UK, are you going up north? As temperatures are getting hotter in the south.
To reduce energy requirements. We are working with some in the south, in Arizona, in different places. But if you have abundant energy, you can even produce water out of the air. You can do all these kinds of things when you have abundant energy. So what I mean by that is, if your energy supply is energy dense, it doesn't need refueling once every 10 years. If the cost is low enough, you can do things like that actually minimize impact on the environment while enabling you to deploy data centers in the least impactful or least socially or environmentally important areas. So we are seeing that. In terms of the requirements on companies, I think we're seeing some of the biggest companies in the world make these commitments maybe in anticipation of requirements, but maybe just because they see their own consumers caring about that a lot. So that's what's driving, for instance, for us, a lot of customers coming to us saying, we want our data centers decarbonized. And I've literally heard them say, well, we actually have customers that they don't just want to hear that we're buying renewable energy credits. They actually want to know the energy coming into our facility, what is the actual carbon footprint of that?
Yep.
I think some of that's being driven, at least in the United States, which I'm most familiar with. The SEC is requiring more carbon accounting now, so that was a recent change. But I think there's also just our customers, their customers are demanding that of them. And so we're seeing some of the biggest companies in the world, Microsoft, Amazon, Apple, you name it, Google, Facebook, wanting to commit to these things, and sometimes very aggressively.
Do you think that will lead to them committing to greater transparency about what it's requiring for them to run these large language models, though? Because so far they haven't been.
I don't know what their plans are for transparency, but it seems like what best people like us can do is, as consumers, make sure that they know that we want to see where their energy is coming from. So that's something.
That's all of you. Get on your social media, start going. What about things that are standing in your way? What's blocking you from realizing your vision at the moment, and how could people help you? And who would you need help from to get it going?
Yeah, there's a long regulatory path. I'd say that's, in general, reasonable, right? Like there's certain industries that are regulated, and it makes sense. So we started that years ago. A lot of people think that the regulator is kind of what keeps it from happening. It is a burden and it's a challenge because the regulators are generally set up to regulate these big old plants. So just to put it simply, they're used to seeing gigawatt-size water-cooled reactors that require whole rivers to keep them cool. And if they don't stay cool, then they're very unsafe, like Fukushima-type issues. We don't require water to stay safe. In fact, we don't really require any safety systems. We're not even water-cooled. We're very small. We're more like 15 megawatts than a gigawatt. So almost an order of 100 magnitude smaller. And so all these things show that there's inherent safety possible. But the regulators around the world, and in the United States too, are figuring out how to understand that so that they can regulate it in a different and better way, or even just regulate it at all, because their old style of application, you might say, is set up in a format to review what they're used to seeing. So that's been a challenge that we've been facing, but it's also one that we're kind of seeing the light at the end of the tunnel for. And so that's probably one of the biggest challenges. Outside of that, supply chain is a big one. And we're kind of growing. As our customers grow, it helps us to build out that supply chain. So
how is supply chain a challenge? Can you expand on that?
Yeah, mainly fuel. Nuclear fuel is not something you can just pick up at Walmart, and there's only so many suppliers in the planet, actually. And believe it or not, Russia was one of the main ones. So with Russia's invasion and so forth, that's obviously something we all want to get away from. It's also part of why our companies focus on using recycled waste as our fuel, so that we don't have to try to buy from different places. We wouldn't buy from Russia, no one really is at this point, but it's a reduced supply chain so that what supplies there are more expensive.
Who are your other people that you could buy from besides Russia?
So there's different steps in the fuel supply chain, but broadly speaking, France is one of them. United States is one of them. There's uranium that comes from Australia, all over the place. So there's a number of places to get raw materials, and then you enrich it, and then you supply it. But all of that we can kind of circumvent by using recycled waste material, which is our focus. So we're working on building up those facilities to have that fuel in time.
And how are you feeling about the talent piece? We focused a lot on that today, about the kind of people that you're looking to hire, that you work with, the sort of training that you feel maybe new graduates, younger students, or even people looking to pivot mid-career to get in on this.
Yeah.
What are you looking for? What would you advise people who find this space fascinating?
Absolutely. A lot of times we have people coming to us from all different spaces and just saying, I want to be a part of something that I see as a solution, and that's, I think, what drives most people who apply to our company. And they're like, but I don't know anything about nuclear power. And it's like, you really don't need to. We need everybody else just like every other company, right? We need business people. We need people who work on strategy. We need people who know how to write. We need people who know how to edit writing, because we write a lot of reports for the regulators. We need mechanical engineers, electrical engineers, you name it. So actually there's finance people.
So it's like any other
lot,
company. There's
yeah,
nothing
a lot
that's
of,
specific,
yeah,
but there must
things.
be some things that you're like,
Yes.
this is the stuff that's hard to find, hard to source. So what about that hard piece?
That's a great question. So when I think about like why it's so hard to find the right people, it's I think you have to have a passion for doing something that hasn't been done before. There's really no roadmap, and for some people that's exciting. For some people that's frustrating. Literally things, contracts that we're writing, reports that we're writing, everything we're doing hasn't been done before. And for some people that's exciting, and some people that is frustrating. And there's no book to turn to do what hasn't been done before. So I think people who come to us and are successful are passionate, they're smart, and they're humble. And I think usually people come to us, they're already passionate about doing something in this space. Obviously, smart people help us to get the work done. And then, it's really important in our company culture to have like low ego, because, hey, it's never been done before. Let's try new ideas. It's really important to innovation to have that kind of camaraderie and low ego kind of atmosphere where it's not like, oh, it has to be done this way, because literally we're all figuring it out together.
I want to turn to all of you. We've got some mics that are here, so if anyone is feeling like they're ready to ask questions and go for it, the floor is yours. I will stand here just to hang out.
Thank you.
Hi. Thank you very much for the talk. I think it was quite insightful. I was very curious when you touched upon using the waste from traditional fission and then using that waste afterwards.
Yeah.
I think three kind of things that I'm curious about is, one is actually how is it done, and then what kind of yield do you get from that? Because obviously uranium has a lot more fission potential energy than its subsequent parts. So if you could go into that, and then also kind of give the efficiency of how much we get back from putting into those waste materials.
Yeah. So it's an important paradigm thing, and this might be part of what you've heard before, is if you recycle nuclear waste, you can do it, and France does it right now, using these kind of big old plants. So they're called large light water reactors. So they're water-cooled and water-moderated, which means water is slowing down the neutrons to get into this nice energy range, because the speed is the energy, right, kinetic energy, and get in this nice energy range where it's perfect to fission the right isotope of uranium that we're fueling those plants with. So you can recycle those back into those light water plants, but they can only kind of eke out a few more percent kind of a thing. If you use that waste material, though, with all its impurities in a fast reactor, which means it's fast, we don't slow down the neutrons with the water. So it's not water moderated. In fact, it's not moderated at all. The neutrons are flying around really fast, and because they have that high kinetic energy, they can actually fission a greater range of the isotopes that are in that waste material. The amount more that you can get out of that, it really depends on how many additional cycles you do, but people talk about using fast reactors to actually fully close the fuel cycle. So you can keep doing that. In fact, there's interesting other things that you can do with it, and some of you might have heard of, like Bill Gates put a lot of money into a company called TerraPower to do something called a traveling wave reactor, which is fascinating because the idea is it actually breeds its own fuel in kind of a wave. So there's all kinds of things you can do there, but essentially the potential is limitless to not only consume the waste, but produce more fuel if needed. So getting down to basically like eking out more than 95% of the energy in the fuel is possible with subsequent recycle cycles. So we look at doing, the fuel is worth it, is valuable to us for many decades into the future. We have it a decade, we refuel, we can keep recycling and keep doing that for many decades in the future. We look at, generally speaking, 80-year use cycle, which is fun for the finance people, but anyway.
We've got time for one really quick question.
Hi, thank you for the talk. I'm a recent architecture graduate, and I was wondering, you mentioned the compact size not needing the water moderation. Could you see in the near future us having reactors, fast fission reactors, closer to urban centres? And then with words like unmoderated and fast reaction, how do you get that market perception? How do you get the populace to agree with living next to these reactors?
Yeah. Well, one of the things that already happens now is small reactors are already near different urban centers. So when I went to MIT, there's literally a reactor right next to my office, right? Like right in the middle of Cambridge, Massachusetts. And so that does happen. Maybe people aren't aware, but you're right. Like how do people get excited about having this in their community? And we thought there's several ways to kind of make that possible, although it's not something we're shooting to do right off the bat. I think it ends up happening almost immediately due to the business offering that we have. So we're not selling reactors to cities that then have to spend money to build, own, and operate them. No, we build, own, and operate it ourselves. They just buy the power. So they tell us where they want us to be. And so it's unlike the traditional business model where there's big power plant, some big utility says, oh, we're going to plop it right here. And then everyone in that community is like, well, we don't want that right there. Instead, it's an opt-in model where consumers are like, we want this in our community and so forth. We have worked with architectures, studios, Gensler, you might be familiar, to design our power plant building. It's a concept. We don't have to use that, but it's been in Architectural Digest. I do think the appeal of the building itself and pointing to it and saying, hey, this is our clean power plant in our community, and being proud of that building and having it as a community center is something we focused on. So,
Caroline Cochran, I'm so sorry that we have to end because I feel like we
you.
could spend easily another hour interrogating you. Fascinating presentation. Thank you so much for your time.
Thank you so much. Thanks, Stephanie.
Good luck. Thanks to all of you. Good questions. Our next one is going to be at 2:40, so in about 4 minutes' time. We're going to be doing something called grabbing people's attention with these titles, Adapt or Die. Data-driven pivoting as a key to product market fit. What on earth does this mean? We will find out from Dr. Roland Decourt in 3 minutes and 30 seconds. See you soon. Adapt or die. You'll be hearing about what that is in just a moment. We're going to be having a speaker come on stage whose background is quite fascinating, so I just want to signal to you who you're about to hear from. His name is Dr. Roland Decote. He is the founder and CEO of Decote Future Energies, which uses groundbreaking AI to extract health data from sound. Now, if that sounds trippy, get ready. He's got a PhD in ancient code breaking from the University of Cambridge, so feel free to ask him questions about that too. I'm going to get off the stage so that he can come on and you can hear more.
Hello. This is on. Hi, hello, CogX. How are we enjoying this Festival of the Future? My name is Roland. I'm the founder and CEO of Decote Future Industries, and my company builds novel artificial intelligence to extract health data from sound. Now, this year's CogX theme is how do we get the next 10 years right? But hidden in that theme, implicit in that theme, is the question, what direction do we set for the next 100 years of tech? Because the reality is that the direction that we set at this early stage, especially for AI, will have long-term implications. It's easy to forget just how fast things can move after a major technological shift like the one we're currently experiencing. There are only 66 years between the invention of the first airplane and the moon landing. 66 years between the first heavier-than-air flight and us conquering not just air, but the atmosphere and Earth itself to reach for the stars. So it's difficult to underestimate just how transformative AI will be over a similar 66-year period. Now, it's naive to assume that as we're all embarking upon this journey together, we'll get it right the first time. We'll need to have the courage to consistently reconfigure and constantly question ourselves and the direction in which we're building. It's easy to get swept away by the status quo, by the current tech, or at least the current manifestations of it, and let it lead us rather than the other way around. And in that way, we actually forget what we're building for. So that's true for us as a society, but it's especially true for a high-growth business, and that's what I'm talking about here today, is I'm going to take you through the journey of my company, hopefully as an illustration that the greatest power a founder or a company can have is the ability to consistently and continuously question themselves and reconfigure themselves. And that means accepting uncertainty, not ignoring it, and taking the reins despite of it. It means listening to the data that the market is sending you, listening to the data that your R&D is sending you, even if it seems to question all your strongest held beliefs. It means engaging in data-driven pivots, which is what the talk is about. Now, my father was born with a congenital heart disease. There was a hole in the upper chambers of his heart, and essentially what would happen is blood would flow through from one chamber in the heart to the other. This wasn't picked up on for about 38, 39 years. Either his parents had been told at his birth and it had been observed, but they never told him, or they had just never seen it. Either way, he lived with it for 38, 39 years until he would have, and I was 11 at the time, he used to have these moments of extreme distress. He would not know what these were coming from, but he had an inkling that it might be his heart, so he went to the doctor. Now, the doctor listened to his heart for about 10 seconds and said, all is fine, just go, you're okay. He went to another doctor a couple of weeks later. They said, listen to his heart for about 10 seconds, said, all is fine, you're good to go, just go. Ultimately, it was my mother who insisted, no, we're paying for a proper kind of, a proper thorough look at all kind of aspects of your physiology, and we're going to pay for a private clinic to do that, that they discovered, oh God, you have this very serious condition. We need to have you in open heart surgery as quick as possible. Now, I still remember to this day that my father put this floppy disk on the mantelpiece. Why a floppy disk? I don't know. I'm pretty sure we had USB drives at the time. Maybe just like to be retro. But on that floppy disk was a letter from my father to me, my mother, and my brother in case he would make it. Now, he made it. He did essentially have to quit his job. He did, and to this day, kind of, he is still dealing with the complications of it, but at least he's alive. Now, the clincher in all of this, the main takeaway, is that had anyone listened to his heart for longer than about 30 seconds during the whole 39 years of his life, they would have picked this up. But no one ever did, because our healthcare is punctuated. It's not preventative or predictive, it is only curative. Now, I have a rather unconventional background. I first went to Cambridge when I was about 15, joined some lectures. Then at 16, I got the scholarship. At 17, I started living full-time in the colleges. And I did my undergraduate master's and then ultimately PhD in a very weird subject, which is ancient code breaking, where I used modern cryptographic methods and modern mathematics to decipher ancient codes. However, whilst I was writing up that PhD, this problem, this thing that had happened to me when I was 11, continued to kind of live rent-free in my mind. And I thought, surely it can't be this hard. Surely there's just lots of different sensors. We know an ECG sensor, we know an IMU sensor, we know temperature sensors. You can easily get them off the shelf, attach them to the human body, upload that data with Bluetooth low energy into the cloud, done, right? Solution. Why has no one built this? Obviously, I began building it and very quickly realized why no one was building it. And the main reason for that was that you need continuous skin contact. If you have to have sensors on the human body, it has to be on something that you're continuously wearing. Generally, the only thing for us, that's clothing. Now, integrating sensors into clothing, one of the things I really quickly discovered is none of our clothing actually fits us that well. And there's not enough continuous skin contact to be able to accurately upload data into the cloud for it to be kind of on a medical level. So the next problem we had to solve was fairly simple. Solve the problem of fit. So I started building a rather complicated metal contraption, later called an exoskeleton, that allowed any piece of clothing to fit any human body size or shape. You basically pushed a button and it went zip. I started building this. This took about 1.5 years, 2 years to then integrate the sensor array. And it was around this time also that the MOD started hearing that I was building this. They got quite interested. Ultimately, long story short, they endorsed us. The UK Army endorsed us. DARSA wanted to invest. And I was at this stage where I realized, this is really cool. I have a company here, but I've not achieved what I set out to achieve. My father would never have worn a military Spec Ops exoskeleton. So back to the drawing board, I thought, and I didn't accept kind of the DARSA funding, and essentially what at that time I did, and this was just when my company, we were selected for Techstars 2020. At the time, I said my company was essentially just still a one-man band, just me. But then I hired my absolutely excellent and brilliant CTO, Erica Bonda-Riva, and we started essentially trying to create an in-between version, a less complicated version of this exoskeleton. Now, at that time, in international media, there had been multiple articles about apps being developed by the University of Cambridge, MIT, and a couple of other universities, specifically to detect COVID using only your voice. By essentially you coughed into a phone, and it would tell you whether or not you had COVID. It would diagnose that. When I first heard that, I thought, I don't quite believe that, because I've just built these really quite complex exoskeletons, knowing how high the bar is to get to a level of diagnosis. So I really need to know about this tech. And Erica was actually one of the people who was building this tech at the university. Now, very quickly, I realized that, yes, as always, it was slightly exaggerated in the media in the sense that it couldn't diagnose yet. It wasn't at that level, and there were some flaws, like if you came from Italy, you would thought to have had COVID, because at that time, most people who were in Italy had COVID. So if you spoke Italian, that was sort of, dooming you in that app. But there was very clear potential there. And one of the things that I thought of, one of the things that we kind of realized is actually, if we use a sound-based solution in these exoskeletons, instead of actually using the proper full metal side to replace those sensor arrays, sound would be a perfect match because it allows no skin contact, and actually even more revolutionary, sound is just a single sensor that can do lots of different metrics. So instead of focus on COVID, we went to focus on heart and cardiovascular. So went to focus on respiratory, we went to focus on things like even mental health, or actually we can even do blood kind of glucose monitoring, but that's a story for another time. Now, whilst we were building that, the idea was, okay, we will build an in-between version between our exoskeleton and this sound-based as non-invasive as possible solution. And that was Mark 1, who's with me here on stage today. I had to drag him all the way. So this is an in-between solution between our current one and the past one. I had to drag him all the way on the underground, which was a bit of a pain. There was one person who asked me, so what's in that? And I said, oh, it's a prototype exoskeleton. He's like, yeah, whatever, and walked off. Like, okay. But essentially, Mark I, we deployed in care homes and in the care sector. And we had customers who were willing to pay for it. We were able to deploy it. But very quickly, one of the things that we realized was that everyone wanted to deploy it in their own way. And all the larger companies we were talking to, all the tech giants and so forth, they wanted to use just the tech. They weren't interested in the shirt. And it was around this time also that I realized actually what the data is telling me here is either I really focus on one market, which is the care market, and we limit ourselves to that, but then will I again have achieved my mission? Because my father would then only ever have been picked up on once he ended up in a care facility. And will that also allow us to have the market size and the company size that we actually were hoping for? Now, that's when we decided, and here's some of that evolution, that's when we decided that actually the best approach to this is not to offer customers a Sainsbury's ready meal of essentially an end-to-end solution where we package it in a very specific way, but instead to let the customers themselves decide how they wanted to deploy this kind of revolutionary new technology. And that was essentially what we ended up doing, is building an engine where anyone can send sound in, and we extract health data out from that sound. Obviously, depending on where the microphone is in relation to the body, we can do different types of metrics. But that was essentially one of the main changes, the latest primary big pivot that we did, is where we went from essentially hardware company to an AI first and purely AI company, where we would license our tech to third parties. Now, as soon as we did that, things kind of exploded. So we got lots of different partnerships that, some of which I'll announce tonight. We had lots of the tech giants reach out to us. In the end, we ended up with 2 of Microsoft's execs on our board. And I'm extremely happy to announce today, for the first time publicly, that we have 3 new key partnerships. One, which is we are working with Google to integrate into Android. Second is we are exploring with Microsoft integrating into their AI systems, such as ChatGPT. And third, we have partnered with Apollo Hospitals, which is one of the largest healthcare providers in the world, for massive clinical testing in order to validate this and ultimately, together in partnership with also some US-based clinics, go for FDA approval. Now, throughout this journey, there were 2 main moments, really, where all the forces working upon us were telling us to stick in the lane that we were, to basically go in the direction that we were going. The first was after graduating Techstars, when we had also already just turned down the DASA funding, we were offered a VC investment. But the problem was, at that time, we weren't certain yet that we actually knew what the final solution was going to be to our problem. We weren't sure what exactly the solution would look like. We just had built this and we were testing it, but I didn't feel we were ready to scale. Had I accepted money at that time, the VC likely would have and wanted metrics, and we likely would have a company right now, which is a defense-based exoskeleton company. And it would have been fine, but we would not have achieved the mission we set out to achieve. Similarly, and that second point, when we were at the stage where we were deploying it in care, we had customers who wanted to pay. It all seemed like a good company. But again, I had to go back to the mission and realize actually the data is telling me that if we really want to have the impact that we set out to have, we cannot limit ourselves in this way using hardware for one specific subsection of that market. So as a founder, generally what will happen is your friends and family, your investors, your mentors, and especially your team will always favor the status quo. It's generally up to you as a founder to make sure that you don't become arrogant, that you don't start thinking, I know what the direction forward is, because you don't. That's the definition where we're doing something really new. Because once you become too arrogant, you stop listening to the data that's coming from the R&D and the data that's coming from the market, then you are losing out on the opportunities. It sounds very strange, but actually the best way to avoid mission drift is often to pivot. And not pivoting, like had happened with me 2 times, would lead to mission drift. Now, I started with the fact that the theme of CogX is how do we get the next 10 years right? There's a sad and slightly dark thing implied and part of that as well, which is that not all of us are going to be here 10 years from now. In fact, there's a lot of people in this room over 35, and 1 in 3 of everyone over 35 in the next couple of decades will die of a cardiovascular disease, likely a preventable one. But not if my company succeeds in its mission. That is our hope, that is our aim at DFI. And whilst it sounds grand, that is genuinely what we want to keep as our North Star. And I think it is companies that prioritize their mission over the manner of their execution, the method of their execution. I think that that is the secret for a successful startup to really thrive. That was me. Thank you very much.
Thank you very much, Roland. That was a fascinating chat. I have some questions for you. So you have talked about some wonderful announcements today about the future of your company and some partnerships and some plans that you're hoping to do to take your technology and embed it and expand it into different use cases. So first, as a potential recipient of this technology, is there an element of consent? So if sound can indicate my health status, what happens if a tech company or some other company that I'm interacting with that is just simply using your technology could know things about my health that I myself don't know and that I haven't consented for them to discover about me? How does that work on the ethical question for you?
It's one of the biggest kind of ethical concerns, and one of the reasons why from the very beginning of the company we want to make sure that we set a very kind of clear ethical framework of how we do this, because otherwise you can very clearly see the kind of use case where someone puts a phone in the middle of a table during an interview and they figure out that you have some kind of condition that you actually didn't legally have to disclose to them, and then they make a decision on the basis of that. Yeah. So the actual use of our tech kind of only should happen, and we can very clearly kind of obviously legally ramify that and kind of navigate that by saying it must only happen in these kind of circumstances when there is mutual consent, but obviously some people can use it for bad. Yeah. And that's why the way in which we're actually doing it is we're not allowing a licensee or a third party to be able to access our black box and get things out. They would have to send all the data, they would have to have an agreement with us, send all the data directly through us, and then only then will we be able to kind of send metrics back to them, which means that generally we will only be dealing with very large corporations, and if they break the law by doing something like this, of course, then we can go after them for that.
So there would never be a risk of this, for instance, being embedded in like an Amazon Echo that people are keeping in their houses and in their shops and in their companies, and then you could be like, oh, I went over to have dinner with my friends Bob and Jane, and they discovered that I have Parkinson's, and I didn't know that myself.
100%. So actually embedding in things like Amazon Echo or Google Assistant is exactly some of the things that we are looking at. But one of the advantages, one of the things that can keep you safe here is that the actual, as I said at one point in the talk, the distance of the microphone to your body also creates a natural barrier. So only with your consent will you place a microphone actually on your body, which is when we can do complex cardiovascular and other analysis. If it is just you're in the house and you're walking around and they're analyzing your mood using an existing kind of AI, that you can already do today, sadly. So I think for us that big barrier is the proximity of the microphone to your body. So yes, there will always be chances for abuse, but it is quite, it's quite limited.
So at the moment, the best way for this technology to work is for it to be as close to your physical self
yes,
as possible. So you would
depend.
probably know and hopefully be consenting to this.
Hopefully, yes. So, and if not, then there's something seriously wrong, right?
Right.
But there's metrics we can pick up away from the body, but that is similar to metrics that are already currently being gathered, like, for example, voice data, using that for mood analysis, or, the cuff detection and things like that. So there is potential for abuse, yes, and that's one of also the reasons, one of the earliest things we wanted to do was set up this ethical framework, and we started talking with Dr. Julian Huppert, who used to be the MP for Cambridge, to kind of make sure that we have this external robust framework of how we internally at least use it. Yeah. But yeah, down the line, one of the things we don't want to do is it to fall into the hands of, say, for example, hostile governments who then use it to monitor their citizens. There's potential of abuse, as with, I think, any application of AI, but also potential to do great good.
What about for things like health insurance companies in the United States that will sometimes deny people coverage and leave you with a medical and financial emergency?
Yeah.
How would you make sure that, not everyone gets to live in a country with socialized medicine? How would you do that so that...
Two things for that. One, for health insurance, one of the things that actually insurers are often happy to pay for is things that are predictive or preventative, because it means that their costs at the end are a lot lower, are a lot less. So they actually have a vested commercial interest in trying to find out what's wrong with you as swiftly as possible, which also will help you because of the fact that you will then not develop this disease further unnoticed. When it comes to them, for example, it's a bit like that black box that you can have when you're driving a car, where you can have, and I do foresee a future where technology, or potentially my technology, is used in a sense where you can sign up for wearing this device, and as a result, say, for example, the costs of your premium will be lower because they can monitor you on the go. But that, again, would need to be entirely on the basis of consent.
But is it really consent? Because if you can't afford healthcare and the only way to get cheaper healthcare is to agree to be surveyed in this really quite detailed way, is it really consent?
Well, the current way in which it happens is you have to go to a doctor of the actual insurance agent, and you have no clue who that person is. You have not chosen that individual. They can ask a range of questions, and they don't actually disclose that data to you afterwards. So at the moment, and similarly also when you said with the punctuated element, at the moment, in order to have anything close to continuous monitoring, you would have to either be extremely rich, like you say, where you would have to go into the doctor and you even have a personal physician, like this called custodian physicians and so forth, and then you'd be followed up on. Our technology is the first time that you actually put that in the hands of everyone, because the costs of a microphone is negligible. In fact, everyone here in the audience at the moment has a microphone in their pocket. So in many ways, what we're actually doing, multiple ones, in many ways, what we're actually doing is we're democratizing, we're allowing access to this kind of predictive and preventative healthcare that normally the vast majority of us now wouldn't have access to. In fact, the partnership we have with Apollo Hospitals, we're working specifically in rural areas of India where people normally don't have access to clinics whatsoever in order for this to essentially allow that first stage of triage to happen. So I think, yes, you can say there's an extent to which if, as with anything that is commercial, you will limit things if someone has to pay for it. But the reality is, if now the bar in order to pay for it is so high, and we lower it all the way down to make it accessible to almost everyone, then I think we are doing the opposite thing of what you were describing.
And I'm intrigued, is there any relationship between this decoding of the body, which is the work you're doing now, and your doctorate research in decoding ancient languages?
It's all pattern recognition. And I think that's true for most things. It's true for running a company as well. It's essentially trying to figure out from a huge mass of data, those little elements that you think are significant, then running them through patterns, trying to find recurring patterns. And that is true with data-driven pivoting. It's true for AI. It's true for ancient code breaking. I think a lot of kind of that thinking is the same. So in many ways, the answer is no, but in, I think, the fundamental way, in a way that most matters, yes, that's kind of how I got there.
So if you had to decipher health, you're going through sound at the moment. Do you have other venues of R&D that you're contemplating? So it's not just going to be sound, it could be other ways of reading the body.
So there's existing startups. Say, for example, there's an Israeli startup that does video-based analysis of your face. And for example, if you start sweating, they put that in hospital rooms so that if a patient starts sweating, they know that they have a certain type of condition, and they do heat maps and so forth. The answer for us is no, though, because the unique thing about sound is, as I said, it's one sensor multi-metric. But also unique about sound is the fact that it's so low cost. But if we can, as we are now currently doing, have a microphone in everyone's hands, and it's one sensor multi-metric, we can actually even reuse existing audio that we've previously recorded to add new metrics. And in many ways, what we can continuously keep doing, if the person, again, decides to do that, they can, over time, we can expand the types of metrics that we look at. So at the moment, it's cardiovascular, we're doing respiratory, doing coughing, but you can also look and listen to abdominal sounds and figure out whether someone has stomach cancer. You can do things like use voice analysis, which already so many companies are doing, and add in kind of mental health detection. There's so many. In fact, we have a list of about 45 metrics that we know that we still want to build out, that there's no point for us to ever change modalities, because the exact strength of the company, the reason why I wanted to make sure that we scaled and not just stayed within a single sector, is because it is that one sensor, one modality, multi-metric kind of solution.
Does this change at all as the human body ages? Do our sounds change as we age?
Of course, yeah. Everything about the human body, sort of, as we age, has a slightly different physiology, will result in lots of different kind of reactions, how things kind of, how you look and also how you sound.
That's amazing.
Yeah.
Do you have any limits? Like, have you tested on babies at all?
So actually, neonatal, there's academic studies that have done that. That sort of some of them are being done by our current CTO, but in her academic role, there's a lot of. I'm personally really excited about kind of prenatal and neonatal care. I think that is one of the best applications for our technology. We've looked at essentially the end of life cycle,
Yeah.
but I think the beginning of life is one of the, and also even for things like fertility, a lot of people who struggle with fertility will have to measure their temperatures every morning. They will have to kind of continuously keep track of their physiology. But this essentially allows them to do that for them. And here's again where when we say kind of, is it to some extent creepy that Alexa would be listening to us? Well, it's just like Google is listening to me now when I say, hey, Google, so that it can respond. If you consent to it, one of the things we could do is, if we indeed integrate into your existing home devices this kind of monitoring, it might be a lot easier for you in your fertility monitoring to be able to just say, use your Alexa or use your Android phone to
Right.
do all of these things.
Oh, bang on time as well. An amazing presentation, hopefully a fascinating Q&A. It certainly was for me. Thank you so much.
Lovely to meet you.
Take care.
Shall we carry on?
We'll, I think somebody's going to come and bring him out. Feel free. I'm nervous that it's reading my biofeedback. Obviously in stellar health, stellar health. So we have, our next talk is at 3:10. It's called Unlocking the Future When Quantum Meets AI. Can you tell this is like at school, it's just getting progressively more and more challenging as the day goes on. There's an exam. If you want to qualify to come back for the lectures tomorrow, you're going to have to pass the quiz. I'm just kidding, there's no exam. Thank God, I would be the first to fail it. We are going to be joined by Dr. Nadia Carlston, who is VP of Product at Sandbox AQ, as she explores AI and quantum's transformative capabilities in fields such as healthcare, aerospace, finance, and more. So back in a flash, relax for a bit. We'll see you soon. soothing music. It was like a little Zen meditation, 3 minutes. I don't know about you, but nice pause, right, after all of that. Get ready to have your brain blown. We're going to be talking about when quantum meets AI. So as though artificial intelligence weren't challenging enough, we're going to be adding in the quantum aspect for it. So I expect to see things floating around in the air by the time we're done. We've got a fascinating speaker today. This is Dr. Nadia Carlston. So I mentioned that she's VP of Product at Sandbox AQ, and she'll tell you a bit about that and what she's doing. Quantum security, quantum sensing. What is this? We will find out. In addition to her commercial skill set, she has also led commercialization initiatives at the US Department of Homeland Security, effectively bringing new technologies in cybersecurity and machine learning to the market. She's got a PhD in engineering from University of California at Berkeley. Please join me in welcoming Nadia.
Thank you all for coming. It's a really pleasure to be here on the DeepTech stage. I've been told that this is the nerd audience, so I feel like I'm in the right place at least. But really looking forward to talking to you all about these two topics. So before I get started, how many of you have heard of quantum? Okay, so that's everybody. How many of you have heard about this little thing called artificial intelligence? All right. And how many of you actually have a good sense for how the two of them come together to do something that's practical? Okay. Fewer hands up. So that's really what I want to talk about today. So both of these technologies are fascinating in and of themselves. They are both have a huge potential for being disruptive for many different verticals, for many different applications. But I find that it's really the convergence of those two technologies that's super exciting. So that's what I'm going to focus on for my talk. And I'm also going to focus on a little bit of the healthcare application and how this convergence of quantum and AI can actually provide a big impact. So my name is Nadia Carlston. I lead product at Sandbox AQ. Sandbox AQ is a company that spun out of Alphabet Google about last year. And our goal is to really bring quantum and AI to solve big problems that are impacting society. We have several different products. Our products are focused on three main areas: quantum sensing, as well as security and quantum simulation. So obviously, both quantum and AI are very big parts of those product lines, and I'll touch on that in a little bit. So if you've been paying attention, and you all have because you raised your hands when I asked about quantum, you know that quantum is a huge topic these days. It's thought to be a huge paradigm shift. I fully believe in that. Prior to Sandbox, I was at Amazon heading product for quantum computing initiatives. So I fully believe in this thing called quantum. But I think where the disconnect with a lot of people is how does it actually do something useful? How does it actually impact any sort of applications? So the way to think about quantum is really doing computation in a way that's more efficient. And that's not all of computation. It's just certain problems that can be done more efficiently on quantum computers. So just to give a quick background so that everybody's on the same baseline, when we talk about quantum computing and we contrast it with classical computing and what you think about as normal computers, the big difference is having bits versus qubits. And so with bits, it's basically zeros and ones. You can think about it as an on and off switch. You can only be in one of those two positions. Whereas with qubits, you can actually be in a state that is a combination of both 0 and 1. A very simplistic way to think about it is to think about flipping a coin. And while you're in that process and the coin is still up in the air, you don't really know if it's going to be a 0 and 1. It's really a combination of all the possibilities. So that's a very, very rough way to think about what superposition actually means. The other big concept in quantum is this thing called entanglement. And so what entanglement means is that two different qubits, two different atoms could actually be entangled so that the actions of one has impact on the other one, even if they're separated by very long distances. So this can be quite weird to wrap your head around, but it basically means that you have a system of two things that are very highly coordinated, and that can be very useful because you can look at one thing and be able to determine what the other thing is doing, even if you can't see the second thing. So when we talk about quantum advantage and what quantum is going to bring to technology generally, what we're talking about is how both superposition and entanglement are going to be able to power these quantum computers in a way that's more efficient than what we have in the traditional world. And one thing to keep in mind is that this isn't just a better way to do traditional computation. So when we think about quantum, we often talk about exponential advantage, and this is because we're not trying to just double or even triple the processing power. This is really trying to go from polynomial scale to exponential scales in terms of efficiency. And of course, what that means, the computation that would generally take tens of years, maybe even hundreds of years, would be reduced to weeks, maybe minutes, and really make possible the type of computations that are completely outside the realm of possibility. So that is the goal. That is the big hope for quantum computing. The big question is, when is this going to happen? So it's almost impossible to have any sort of discussion about quantum without having a conversation about timelines and when this will happen. So there are a few things that are driving that timeline. And one thing to note is that quantum computers that exist today are still very, very basic. So most of them are great for exploration. They're great for learning about quantum systems. They are not powerful enough to do any sort of computation that's going to have a commercial advantage or a practical aspect at any sort of scale. So what researchers and engineers like me have been working on are different ways to build qubits, right? The different ways to harness nature, different ways to build qubits from electrical circuits, for example, in the case of superconducting qubits, just different approaches to solve two issues. One of them is how to make these qubits better, how to improve fidelities, which is how accurate it's going to impact how accurate your computation is at the end. And then the other thing that we're trying to solve for is also how to scale from a few qubits to many number of qubits. And one thing to keep in mind is that you actually need both. You can't just have thousands of qubits of low quality, and you're not going to go very far with just one very high quality qubit. So it's trying to optimize on those two axes that gets very, very difficult, and that is really the main driver of the timeline for when we will have a large quantum computer. The holy grail in quantum is creating these things called fault-tolerant quantum computers, and that means that even though there's going to be errors in a computation, because quantum computers are very susceptible to the environment, we can actually correct as we go, and the computation at the end is still going to be correct. So this concept of quantum error correction is where a lot of the field is focused on right now, and rightfully so, and it's really the key step to have fault-tolerant quantum computers, and in turn, having a fault-tolerant quantum computer is going to determine when we need to start worrying about some of these big things that quantum computers can do. One of the things that has dominated the conversation in a way is the impact of quantum computers on security. And the reason for that is, you may recall I mentioned that quantum computers can do certain types of computation more efficiently. One of the things that they can run more efficiently are algorithms related to breaking encryption standards. So everything that we currently do, every day you are using the internet, you're doing transactions, all of that rely on your ability to send data in a way that's encrypted, in a way that's secure, send it somewhere else where that is going to be decrypted. So the fact that the standards that we're currently using for encryption would be threatened by quantum computers obviously is something that a lot of people are worried about. But the good news is there are new algorithms being developed. There are new encryption standards being developed. And this is what this category of post-quantum cryptography really encapsulates. And so when we talk about timeline, again, that also is a big driver for conversation, because now you have people on the one hand that are building quantum computers as fast as they can, and then people on the other hand that are trying to adopt these PQC algorithms as quickly as they can before quantum computers get there. So there's a little bit of a race of trying to develop both technologies at the same time. So I'll talk about AI very quickly, just the same way that I baseline on quantum. So unlike quantum, where it's really about doing things exponentially faster because of the different way of processing, with AI, what we're trying to do is mimic the human brain in some way. We're really trying to get away from programming answers and really get to spaces where machines are using that pattern of learning from data and being able to make predictions based on their learned behaviors. So as probably many of you know, there are many different categories within AI. It's a little bit unfortunate in my view that LLMs, very interesting things that are being done in the AI space that don't really get a lot of voice these days. But at Sandbox and in my work, we're really more focused on things like machine learning rather than LLMs. It's really not about generating data or generating information using LLMs, and much more about using machine learning to make better predictions, to make better diagnostics, and to just help us more generally with cleaning up of data or trying to get insights from data. So what I'm really focused on in my work, and the area that I find really fascinating, is how these two topics come in. And one of the areas that I'm really excited about, we've talked about quantum computing, but there's also this other thing called quantum sensing, which is slightly different. So they both leverage quantum mechanics, they both leverage quantum systems, but the big difference is with quantum computing, you're using these quantum mechanical systems to process information, to do computation. With quantum sensing, you're using the quantum systems to make measurements about the world that's around us. And you can use quantum sensors to measure many different types of properties. You can use them to measure magnetic fields. You can use them to measure electrical fields. They can be used to measure gravity, and a lot of people are working on that. What we have focused on at Sandbox are measurements of magnetic fields because they have a lot of different applications. The image that you see there is actually something called a diamond vacancy center. And what's being shined on it is a green laser, and it's being reflected red. That's why there's the two colors. But these diamonds have very unique properties that make them very good quantum sensors. Incidentally, they can also be used for quantum computing, but we are using them as quantum sensors. So where does the AI come in with a quantum sensor? The quantum sensor is very good at detecting things that is around it, so picking up a lot of signal. But then what you get is a lot of noise also with that. It's very hard to figure out what is the thing you're trying to measure in all of this data that you've gathered. And this is where we found that machine learning and having really good models that have been trained on the surroundings and have been trained on the different spaces and technologies that you're looking at can be very useful because it helps you get from that raw data that's very noisy, it's full of things that you don't care about, to having something that actually gives you an insight about what you're looking at. So to give you something tangible as an example, one of the things that we're looking at is detecting magnetic fields inside the human body. And so some of you may know that we all have magnetic fields inside our human body. They're very weak, but they are detectable. And if you have a magnetometer that is sensitive enough, you can actually pick up what the signal is, and looking at that signal, you can also use that for different diagnostic reasons. What we've been looking at primarily is how that can be used to make measurements with people's hearts. So right now, the main way to diagnose heart attacks or cardiac problems more generally is EKGs. So this is where you get little sensors that are measuring your electrical field, and you get that chart, and it tells you whether things are good or bad. The problem with that is electrical signals, as they travel through the body, actually encounter a lot of resistance from tissues, whereas magnetic fields don't have that problem. So
care that we're going to be joined by Dr. Roland Tegeter. So hang on for just 2.5 minutes. We're going to do a bit of a swap, get him ready, relax, and I'll see you shortly. Dr. Roland Tegeter is a CEO of Halogen, the first multimodal foundation model for neurology and healthcare. Halogen is the result of a decade of work from leading UK institutions encompassing neurological data, brains, behavior, cognition across multiple modalities and domains. Please join me in welcoming Dr. Tegeter to the stage. Good luck.
Hello, folks. Can you hear me all right? Good. First of all, thank you very much for staying in the audience, because I have something very exciting to speak about this afternoon, which is relating to human brains. So welcome to all you human brains. I have interest in all your brains, and you will see why that is in a minute. The subject I'll be talking about is foundation models in medicine. Who knows what a foundation model is? Everyone. Everyone will know large language models, which have conquered the interest over the last couple of months. What we have done starting about 4 or 5 years ago is to apply the technologies behind large language models, foundation models, but going way beyond text and applying it to medicine, in particular to human brains. We have taken a very large number of human brains with a significantly wide range of information about them, from scans to patient data and other kind of modalities. We have looked at the structures of brains, we have looked at the functions of brains, and we have looked at the behavior of brains, so we cover the whole gamut of what we humans stand for. And we have packaged that all into one generative model. And that's what, for the first time, I'm actually announcing today, that we have that. So you are here in CogX, you hear it from me. This is the first LBM, the first large brain model, which is part of the class of LCMs, which are large clinical models. They are going to transform fundamentally the way healthcare is going to be delivered and the way in which we are going to use data to infer behavior and information about patients. The first model of this kind we have produced. Now, you may say, why do we focus on human brains? This slide tells us why. It shows you disability-adjusted life years from the World Health Organization between 2000 and 2019, showing which diseases have been most horrible to mankind. And everything in red on this slide somewhat has to do with the brain, but we undercolored it. Because if, for example, you have diabetes and you have this latest drug from Novo, it's a brain mechanism that ultimately transmits that signal. So many of these diseases all hang together ultimately into brain as well. So this was the right place to start. The way in which this works, this large clinical model, is similar to what you might know from your large language models. You can ask it questions, and it comes back with answers. And I'm going to give you a few of them so you understand the power of this and how this helps transform healthcare. Here, you pass in these information screens on the left, and you ask Halogen the question, what can you tell about these brains? And it comes back with information about it. We can tell with great accuracy sex, age. We can say whether this is normal or abnormal. We can pinpoint where it is normal or abnormal. And that is important from this example because we have trained this model not just on healthy brains, but also on unhealthy brains. And this combination of pathology and non-pathology is critically important, and we are the first to do it in this comprehensive manner. Here's another one. You take a brain and you ask it, can you age it, please? Age the brain by 10 years. Or change the sex of the brain. Now you might say, is it a party trick or is there more behind it? And there's a lot more behind it because there are many, many studies where we don't have the right balance of male and female patients, or where we don't have the right balance of age groups inside the sample space. So our accuracy of testing the efficiency of compounds goes down. But we can age the brain, we can make it younger. And so this plays an important part in making medical testing much more efficient and much more equitable. Here's another one. You pass into it a whole bunch of diseased brains, and you ask a functional question that pinpoints to a certain structure in the brain. Take these things, figure out which part of the brain is responsible for what in this case we call phonemic fluency. Phonemic fluency, if I were to ask you here, is what goes like this. I would say, give me as fast as you can words starting with the letter S, and you would just rattle it down and we count over a period of time. That's phonemic fluency. And voila, it comes back and tells you what it is. This goes into treatment, where you can ask a question, I have this patient here, how likely is that patient going to respond to a particular kind of treatment? So our model doesn't just have pathologies and healthy brains, but also treatment plans and treatments and their outcomes, so that we can find the information that links one to the other. And here's one that is not particularly sexy, but it is probably the most immediately useful and quite revolutionary thing. We can pass it a scan on the left and ask it to transform this scan, there clearly is a spelling mistake there, to transform this scan from having been scanned by one machine to being scanned by another machine, or from one type of system to another type of system. This is a huge deal in medicine. They have a thing called traveling heads, where if you do a clinical study, you have to pre-configure the machines in 5 hospitals, and they send a traveling head through to make sure they're all cross-calibrated. No more. With Hologen, we can move between images, we can transform from one type of machine to another, and therefore create a form of operational independence from the machines that are taking the images. So, that is what Hologen does. It's just a small sense of how much we can get out of these large clinical models, of which this one is the first. How do we make money out of it? And this is where it gets super exciting. We don't just promise that we can do better drugs. It's far too far out. We have to do something that is valuable now. And our first go-to-market is standardization. This is essentially a universal brain scanner. We can, with standardization, do the second thing. We can unlock an enormous amount of data that were collected in the past, that sit at pharma companies, in hospitals, at clinical research organizations, and elsewhere. We can unlock them because we can standardize them to today, and we can feed them into studies in order to find out which compound is going to be better for which phenotype of patient. This treasure trove wasn't unlockable. Now it is. So we standardize. That's how we conquer the world. We unlock data. That's how we feed this monster that lives on data. And that's how we improve the system. The last step here is equally important. You will have seen that in large language models. There is no such thing as just one model. You have a big model at the top, and then you have an ecosystem of specialized models coming from below. With a large brain model like this, we can provide an enormous increase in the speed and go-to-market for more specialist AI downstream. This is meant by AI for AI, or AI as a service, so that people don't have to retrain all their models from start, and they get models that have been balanced for example, equity, male, female, black and white, and so on and so forth, they don't have to worry about this because it's already done at the level of our system. What we are now facing, having produced this model, shown its efficiency and its importance, now we have to do what everybody has to do in this game of generative models, and that's scale. So we are about to dramatically increase the compute power. We are very fortunate to have been able to use Cambridge 1, and thanks to the NVIDIA Corporation, which sadly is no more in Cambridge. But we were fortunate to have that, and so the compute power requirements that we need are going to be monstrously going up. We're expanding very rapidly. This is how the game is built in commercial terms, and that's where we're in right now as we roll out this model. And I leave you with one parting shot, and that's the only thing you take away from my talk, apart from coming to me afterwards and wanting to write a check, is how central foundational models are in medicine. If you think that you got blown away by large language models, just wait. This is coming around the corner. But I will try to distill it in this way so that you see just how naturally medicine and foundation models go together. And the reason is this: no two humans here are the same. Therefore, I cannot do science as I would do as an engineer and say, I repeat the experiment so many times and then hopefully, I find what's common. No one is the same. So it's not possible to do conventional science. As a matter of fact, all good medical people know that all medicine is just intelligent guesswork because it's so complicated and no one is the same. So I need a technology that delivers best possible information and action in a world where nothing is the same. Nothing can be repeated. Everybody is unique, and yet there's common structure. And that's why foundational models have this natural link with medicine, and that's what they were kind of born for. And so Hologen delivers exactly that. Last comment for me, I use this word intelligence, not in a sense to spur some philosophical debate, but I use it in the etymology sense, which means intelligence, intellegere in Latin, means to read between the lines. Or if you slightly translate it differently, to connect the dots. And that's what these foundational models do with this very complex space of medical information that we can now apply to all of you. And in doing so, we can make sure that we don't treat you just as a number. Medicine with foundational models can begin to look at the individuality of everyone whilst benefiting from the knowledge about all. That's what medicine can do with this. And Hologen, with its foundational brain model, is the start. You've heard it here. Thank you very much.
Thank you, Dr. Tegeter, for that fascinating announcement. I'm sure I'm not the only person in this audience who's going to have questions on this, so I want to make sure we have time for other people, but I will take the privilege of asking the first, if I may. Now that we have this tool, how do you see the path forward? What are the problem sets that you'd like to work on, or the big changes you'd like to do?
Yeah, you see, we're not promising that we revolutionize drug discovery. We're not promising that we can now predict things better than before. That will happen. But it's very hard to validate, and from a commercial point of view, that's not the way to go. We are going to first make sure that we get as many data in the most curated way into the system as we can. And secondly, unlock, as I mentioned, the existing data that lie dormant. So we get the variety of who all of us are in their individualities. That is extremely valuable. Data are valuable. Uncovering these data is valuable. So that's our very, very first thing, and that will deliver specifically in better ways to do clinical studies where we can get away with fewer people, lower cost, higher compliance with the testing. So very humdrum, very basic, but extremely beneficial and also useful to us because it gives us more data.
And who would you say, therefore, would be the first people who will feel the benefits of this? Is it researchers and clinicians? When does it trickle out into the general public?
Well, the first benefit will be that the cost of doing trials is going to come down. Everyone who has to look at brains as part of clinical trials will want to do it with halogen as opposed to without halogen. It will bring costs down. It will increase speed to market. It, as mentioned, reduces the testing group and the complexity around this. So the trickle-down effect will take its time, but it will translate in the form of faster delivery on tests and trials, and most importantly, it drives the agenda of personalized medicine, because this is behind personalized medicine. Nobody is the same, therefore personalized medicine is at the very center of what we do. So that is how it eventually will trickle down. But we're not a B2C company. We're not delivering to doctors. We're a B2B company, and therefore it will take a while before it trickles down to the consumer.
And are there any limitations within how we collect data, cleanse it, utilize it, or even regulate it, and what you'd like to be able to do? Are there sort of things that you're like, ugh, we're not quite where I want to be yet? Can you talk us through them?
Yeah, I think the most important point here to mention is privacy. And data privacy.
Okay.
This is a big, big deal. These clinical models, they rely on huge amounts of data. But we obviously need to respect patient confidentiality and data privacy. What we're facing here, if you give me just 20 seconds, and this is the other message you need to take away from this afternoon. What we're facing is that some parts of this world can collect data with impunity. You go to China, you get everybody has data, but it's completely open. We in the West have our standards. We value our privacy. So they can get ahead with a huge amount of data and start mining this, and we can't. So if we don't find a way to manage that privacy aspect within the generative models, we are at a disadvantage. But here's the good news. We know how to do it.
Talk us through how would you do it? How are you squaring the circle?
Now, we know how to do it because you need for that certain technologies, cryptographic technologies that come into play and that are important. There's a concept of differential privacy within medicine that doesn't apply here. Don't want to go into it. So we need to innovate on the way in which privacy is handled, and that's part of the game of what we're playing.
And is that going to involve patient consent or something else? Is this like something
no, it would not
involve ethics boards?
No, it would not involve patient consent.
It would not?
No.
Okay. What would it involve then?
It's anonymization technique.
Right, so it's just purely on the crypto side.
It is on an anonymized basis with a certain twist, yeah.
Okay. That sounds exciting. I'm also wondering, are you worried, therefore, about competition from a company in China that doesn't have to operate with the same privacy constraints that you might?
I always worry about competition. That keeps us fit. So I don't mind that there's competition, and we'll see how important competition is now in the LLM world, the large language model world, right? So yes, Google might want to do it, other people might want to do it. However, unlike text, where I can go to the internet and just get a huge amount of text, you need to have serious clinical, professional domain competence behind this. And allow me to mention that we have that. We are working with the top 2 universities here in London, have done so for the last few years, which is University College London and King's College London, the 2 hotbeds for this kind of stuff. So it is not possible just to go and, cook up some model and make it happen. The domain competence is huge. So I'm worried about competition, and I'm not worried about competition.
Are there any advantages in countries that have a national healthcare system where you might be able to draw, for instance, on a data set of a whole country versus something like in the United States where it's more federated?
Yes, certain countries are way advanced over us here in the UK in terms of the ability to move data around and to have access to data, again, to be balanced with privacy. An example is Israel.
Israel.
Yeah.
Can you talk us through that a bit for those of us who don't know?
No, just briefly, the way in which data are handled, electronically movable, what they can be used for and so forth, and the can-do attitude in Israel is just off the charts. And so it is a good place to work there. And there are other countries where it is similar. The UK is somewhere in the middle. I'm trying to convince the powers that be in the UK to take this a lot more seriously.
I guess if you can make the value case, which in this country is often about cutting queues and reducing costs.
Yes, I can say this only one more time. You've heard it here today. This is the first large brain model. It's UK made. This is a UK thing. And UK can lead the world if we commercialize correctly. Now, if we scale correctly, now. That's what we're doing. And it also means that government and the NHS have to understand the data limitations, and they have to be overcome. Sir John Bell, Sir John Simons, who published the policy on the government strategy on biotechnology, they're aware of it. And the dialogue is not going fast enough. We will lose out unless we do this and push this. We'll lose out to people like China and others.
Is this a topic that you feel could be raised at the UK Global Summit on AI on the 1st and 2nd of November?
I'm happy to go anywhere to raise this topic. It is so central to delivering the benefits of what foundational models can do in medicine, for the very reason that medicine is not like an engineering science. And therefore, the technologies didn't exist, or previous technologies were dealing with medicine as an engineering science. It is not. We are different, every single one. This technology is made in heaven for the fact that we are not engineerable bodies. So anyone I can talk to make understand that we are in this race for data and this race for standing by our values, which are privacy, confidentiality, and that kind of stuff. And what we need to do this, to enable our kind of models, book me in. I come any place.
Let's talk afterwards. We'll get you booked in. I want to make sure, were there any questions from the audience? We've got a mic, thank goodness. A couple in the front here. We've got this gentleman here, this woman here, and there's a gentleman there. Sorry if I'm not seeing you. Yep. So be tight. Go for it.
Thank you very much. Amazing stuff. So about the brain model that can transform the MRI images to different Teslas or different manufacturers, how is the accuracy is doing there, and what happens when the model generates something that is false?
Yes. Very, very briefly, the model is capable of super resolving. So because we have information about so many brains, we can, if something is not quite resolved in an image that was actually taken, we can super resolve it because we have this additional prior information in the model that gives us that information to fill in where something wasn't quite resolved in the first place. So we're capable of super resolution. On the second point, which is also coming up in large language models, the idea of confabulation and getting it wrong. Here's the problem. Medicine is always guesswork. You are never fully right. You may be right if I give you a medicine that doesn't work for him. So we just have to make sure that this guesswork is best informed. And that's what this does. We will get it wrong, just like your best medical consultant will get it wrong. But we will get it wrong less often, and we can demonstrate that.
One last question, please.
Yeah, I'll make it short. You showed us all the different kind of diseases there, so I don't know like for how long you've been actually gathering all those data, but what if something like COVID comes around, something completely new, something like long COVID? Is your technology actually able to come to a solution faster? For example, how to battle long COVID and stuff like that?
I hope so, yes. I haven't studied long COVID. It comes down very briefly to two things. It comes down to abnormality detection, which means by definition saying something about what you don't know to start with. What we do have is this ultra-high complex representation of the information that exists. So connections that one wouldn't make are in there. So abnormality can be seen in relation to these sometimes very abstruse connections, which other people wouldn't see. Because they're in there, I can see a divergence from it. So that's why we are hopeful that it would be useful in cases like long COVID, but we haven't had a chance to test any of it.
Okay, thank you.
I wish we could continue this conversation. I'm sure we'll all be following the progress of halogen and indeed of you very closely. Thank you so much.
Thank you very much. Thanks for your attention.
Thank you. Well done, everyone who has been on the DeepTech stage with me throughout the entire day. Have a little stretch and a little breathe, because we have our last panel coming up at 4:15. It's an interesting one, actually. Not that they haven't all been, but it's a fun note to end on. Longevity from cells to cities. 6 people are going to be up on the stage, 6 fresh brains for us to interrogate. I will leave you with that in a bit of suspense, but worth sticking, if you can, to the very end. See you soon. Hello. People who are networking in the middle of the room, I love it, but you're going to have to sit down because you're going to want to hear this. We are on the last panel of the day, and it is a very impressive and fascinating one, I'm sure you will agree. It is called Longevity from Cells to Cities. Now, we're going to be focusing on the latest science and technology that's going to show us the importance of psychological and behavioral aspects of aging. With me on the stage, I'm going to call out their names, so let's hope they come out in order, is Tina Woods, who's going to be moderating this event. So please join me in welcoming Tina Woods. Making a shy, demure entry onto the stage, Aubrey de Grey, Alexi Strigan, Eleanor Davies, Peter Ward, and Lynn Corner. Now, Tina's going to be moderating. I'll jump out later. Without giving lots of bio, I want them to have the room and the space to themselves. Over to you, and I'll be back with you later. Enjoy.
Thank you so much for all of you to be here for a session on longevity from cells to cities. So I'm Tina Woods. I wear a few hats, but the hat I'm wearing today is in my role working with the National Innovation Center for Aging on the Quantum Healthy Longevity Innovation Mission. Really to improve the health of people, the planet, but also the economy. So why are we doing this, and why are we doing this mission, and why are we all here today? Well, there's a burning platform, and actually there are quite a few burning platforms for why we're here today. We're seeing actually in some of the richest countries in the world, including the US, life expectancy has actually started to fall. And actually in the UK, we have a widening gap in healthy life expectancy, the years lived in good health, between the richest and poorest citizens of about 20 years. We have, as many of you will know, we have a health crisis. In fact, it is so bad and so severe that the economy is being dragged down. And obviously, we see our NHS in crisis. So somehow we need to reduce demand. We have to make people healthier, reduce sickness, and also understand how we can delay the impact of our aging demographic. But we have to stop seeing the solution as just fixing us when we're ill and when we're sick. So today we're going to be exploring the colossal developments that we're seeing in the science of longevity, the technology behind longevity, and from cells to cities, and see it very much in the context of how human flourishing is affected by the so-called exposome, the wider environmental factors and the determinants of our health that are deeply, deeply affected by our state of mind, our psychology, our behavioral tendencies and habits, and really sort of look at this new emerging concepts in the health space around health resilience, and really to look at how we can really deliver improvements in health span and lifespan. So I've got an amazing panel here, and we're going to start first with a longevity legend, Aubrey de Grey, many of whom will have seen him. He's been in this business for many, many years, and we'll talk about some of his work recently and what he sees as the future. Over to you, Aubrey.
All right. Thank you so much, Tina. Thanks for coming. I guess I'm going to talk about why it makes sense for us to have this panel in the first place at a meeting like this. And I'll talk a little bit about what I do and what you can do to contribute to all of this. Of course, there's a lot about AI at this conference. And a lot of people are thinking, well, who cares about aging anymore because we're all going to die in the next decade anyway because AI is going to kill us all. But those of us who think that might not be the case are still interested in making sure that we don't die of the same thing that nearly all of us have died of in the past century or two, and of course more and more of us in centuries before that. So I want to talk about the next decade, longevity until, let's say, 2030. And the main thing I want to communicate today is that things have really changed in terms of how we can think about the problem of aging. The fact that aging has now become a tractable medical problem, something where we have enough knowledge about what the problem is and about the technologies that we might be able to bring to bear upon it, that we can actually formulate a plan. An actual, and not just formulate, but actually implement a plan for doing something about it. Now, of course, You all know how important aging is. I know there's a lot of investors here, so I thought I would spend a couple of minutes talking about the economic aspect. This is a good way of describing the economic aspect. Here I'm just using for illustration the statistics that I was able to pull down from the USA during the period between, I think it's 1960 through to 2010. This is just a 50-year period during which the US economy grew, that's the red line, by a large amount, obviously, and the amount spent on healthcare in the US also grew by a large amount, that's the blue line. If you look at those two lines and nothing else, then you may not be terribly scared. But if you look at the green line, you'll be terrified. The green line, of course, is the proportion, the red line divided by the blue line, the proportion of the US economy that's spent on healthcare. And in just 50 years, it went up from 5% to 18%. And of course, it's continued to rise since then. So, you know, just from an economic perspective, even forgetting about the humanitarian imperative, this is absolutely terrifying. And the main thing I'm known for scientifically is that 20-odd years ago, I pointed out that there was an approach, a strategy for doing something about aging that people were overlooking. Essentially, if you want to define aging, there's many ways to do it, but a perfectly uncontroversial definition is the three words on the bottom line here: metabolism, damage, pathology. Metabolism means simply the network of processes that the body uses to keep us alive from one day to the next. It has side effects that accumulate over time, changes to the molecular and cellular structure of the body that are progressive and that the body is set up to tolerate a certain amount of. So that means even though those changes begin even before we're born, nothing really matters about those changes for a long time. But the body's only set up to tolerate a certain amount of that. So eventually you start to go downhill, and that's the pathologies of late life. That's all that aging is. It's really just the same as aging of a simple man-made machine like a car. You know, the body is set up to tolerate a certain amount of damage, but eventually there's too much. So if the goal is to separate metabolism from pathology, in other words, to allow us to continue being alive without getting sick, then there's various ways that you could try to do that. You could try to separate metabolism from damage. You could try to separate damage from pathology. That's what I'm calling the gerontology and geriatrics approaches, respectively. And those have both been spectacular failures. I pointed out 20-odd years ago that we could instead do preventative maintenance. We could just periodically eliminate some of the damage that the body had accumulated. And I figured out that this actually made practical sense. I was able to enumerate a certain number of categories of that damage, which seems to have been fairly exhaustive in the long run, and to enumerate corresponding damage repair approaches, which have all gone quite well, actually. You know, most of these things were actually quite conceptual 20-odd years ago, but now not only have they progressed in academic laboratories, they've actually got to the point of being spun out as startup companies, not only by the various organizations that I've led, but of course by other people as well. So that's all wonderful. It's a great start. And where we are now is at the position where at least some of the easier of those rejuvenation treatments, those damage repair treatments, are working well enough, at least in the laboratory, in like laboratory mice, for example, that we can combine them. We can actually start putting them together in the same mice at the same time and asking whether we actually see synergies. And so my newest organization, LEV Foundation, is doing exactly that. This is just a summary of the big experiment we're doing right now, which is taking 1,000 mice and giving them various combinations of treatments and trying to get them to live a long time. And the key point is that we are starting this combination of treatments in middle age. So the typical mice that are used in these experiments live about 2.5 years. We're starting when the mice are already 1.5 years old. So that's actually of some level of relevance to the people in this room, rather than to people who are not yet born, which is actually what most experiments that people do tend to be focused on. So that's what we're doing. But I wanted to spend the last, like, 1/3 of my time here, I've only got 10 minutes, on what actually matters to you as a consequence of all this work, this progress that's been made over the many years that I've been working in this field. The key thing right now is we have a very an explosively burgeoning private sector in the longevity space. Companies that, some of them have got even to the point of being unicorns, but most of them are still small, but there's a huge number of them, hugely growing investor interest in this area. There is, however, still a lot of, a long way to go. And so I just wanted to highlight a few of the points that matter in this regard. First of all, if you're a traditional investor, especially not early stage or slightly later than that, you may be thinking, oh, it's all about IPOs and exits and so on. And there's a lot of over-impatience in this field. There have been a few, shall we say, overly hasty IPOs in the longevity space that have crashed and burned. There's an enormous amount of volatility, not just in publicly traded companies, but the fact is it's an early sector. It just is, and so one's got to treat it that way. One's got to take a lot of shots on goal, diversify a lot, and a huge amount of this depends on people like me, people who are doing the research, people who are the credentialed, respected experts in the actual technology, because we are the people that investors ultimately look to trust in terms of how soon there's going to be commercialization, how soon there's going to be profits, and so on. And a lot of what I have been doing lately is trying to encourage my colleagues, well, bully my colleagues, to be perfectly honest, into being a little bit less timid in what they say publicly. Because now is the time when you can. I've been saying this for 20 years. I've been saying that, my colleagues need to talk about time frames, talk about how soon we actually have a good chance of making a difference to how long people stay healthy before they start to go downhill. And there is still an enormous amount of reluctance among my colleagues to do that. But the fact is, we've got to do it in order to reassure people like you, whether you're investors, whether you're potential customers, whatever. But especially investors, and especially people in government or people who influence people in government. I'm all about trying to get a process going where the community of experts come together and say, listen, boys and girls, we are actually close to being able to bring aging under genuinely comprehensive medical control, and the more we invest in the effort to do so, the sooner we will succeed in doing so, and the more lives will be saved. Let us remember that 110,000 people die of aging worldwide every single day. That's like 30 World Trade Centers. That's very easy to get out of bed for me to try to fix, and I want everyone else to think the same. I'll just end by mentioning I read a book a long time ago that is still fairly useful in terms of educating you on the technical side of this, and that's my email address and my website, our website, so please get in touch. And that's it. I have 6 seconds.
Thank you so much, Aubrey. That's wonderful. Over to Alexei from Giro.ai.
Thank you. Thank you, Aubrey. And I wanted actually to start from saying why talks like that are very important. About 10 years ago, I was a young person, not really knowing what to do with my life. And I was actually listening to Aubrey debate with some other guy, and I don't remember the other guy, but I do definitely remember Aubrey. Why I do remember Aubrey? Because he put very, very simple thought in my mind. We can do something with aging. It is very important. We can do something with aging. We can do something with aging already today, and we will be able to do much more tomorrow. So I'm Alexei. I identify myself as a bio-entrepreneur. And I'm a part of the company called Giro.ai. Our mission is to make humans non-aging species. How do we do that? We use physics of complex systems and AI to identify the root cause of aging, the most upstream mechanism of aging, and to develop drugs or other interventions to actually stop or at least decelerate the aging process. So we have several targets and several drugs in our pipeline already, though that future, when you will be able to take a pill and age slower, we should wait for about 5 to 10 years for it. Hopefully it will be faster, but we can do something today. Also, why we are good at understanding aging as a company. Pfizer already struck a deal with us where they basically used our expertise in aging to find drugs against age-related diseases. That is interesting. Today, pharma is not interested in aging, but it will be in 5 to 10 years. Please mark my words. So again, this question, why it is important. We need a lot of people in the field. The biggest conferences in aging are visited by only 600 to 1,000 people. And we need not only scientists, we need all sorts of people. So please, if you're interested, join the field, contact me, contact someone from this group. We'll help you navigate through this very important field. Now to the question of what we can do today. To understand how aging is unfolding in humans, we did a lot of approaches to how to measure aging in human data sets. So we found aging signal in electronic medical records, in DNA methylation data, in proteomics data, but very interestingly, we also found that longitudinal locomotor data, step data, is actually very cheap and readily available biomarker of aging. And we already use it to measure aging of people and of crowds. So already today, we might do something like this, where we can split the city into districts and see which districts is aging faster or slower, which districts was healthier, but suddenly has become less healthy. It can help prioritize distribution of public funds. It can prioritize assessment of what actually works today. Shall we build a park? Shall we do a promotion-like trial? Shall we help people and install an app? So here are my contacts. Please feel free to approach me. We provide the technology I described as an API, and this API is already used by our colleagues and I would say partners in longevity crime from Humanity. And I'll pass my microphone to Peter Ward.
Thanks, I don't think I need that. Thanks, everybody. So I want to, let's give them a clap. Come on. I want to give you guys a bit more health span. So I want everyone to stand up, okay? And if we can get some music playing, that would be even better. So music maestro. I want us to dance. Come on. Let's jump up and down. Let's do it. Come on, let's get some energy flowing. Come on, clap. Woo! Hold on, we're at a rave now. This is great. Okay, stop. Now, I want you to stay standing. I want you to close your eyes. I want you to take a deep breath in. And hold it, and then out. Do one more. And out again. Now, keep your eyes closed. I want you guys to remember a recent experience where you were having fun, maybe at a rave or something like that, and think of all the most incredible people and experiences you had. Now, anchor that experience. Open your eyes. Turn to the person next to you. And stare into each other's eyes. I want you to do this. I want you to do this for a few seconds. And just think of how much fun you could have with this person if you were in that environment right now. And I invite you to, if you feel comfortable, to release a great hormonal release of oxytocin and endorphin, just give each other a hug.
That's
All right. I just gave you guys a whistle-stop tour of what humanity does, but rather than me talk, I've already prepared a video, so video maestro.
What these guys have built already is incredible. Humanity is transforming people's health, and I cannot wait to see what's coming next.
There are very, very few people who can build awesome products in consumer and health tech. And Pete and Mike are two incredible individuals who can do just that and more. That's why I invested.
Cancer, cardiovascular disease, Alzheimer's, and even diabetes are primarily caused by one thing: aging.
The problem is we rent our health, and then when the repair bill comes due, we wish we had invested in it.
I lost my dad to a severe stroke in his early 60s after he became type 2 diabetic.
I lost a loved one to late-stage cancer. I felt completely helpless, but that's all about to change.
Your genetics is not your destiny. Aging is measurable and reversible.
We aren't helpless. For those of us still lucky enough to be alive, there's a science to longevity. There's so much we can do to live longer, healthier, and happier lives.
Which is why we built Humanity. Humanity takes the cutting-edge science of longevity and places it in the palm of your hand. At its core, it does two things. One, it monitors your rate of aging and biological age, and two, it guides you to slow it down and even reverse it. Under the hood, it uses AI to analyze your movement, heart rate, blood biomarker, and lifestyle patterns captured from your smartphone, wearables, and Humanity app.
It's like the Waze traffic app, but for your health. People have never had a concrete feedback loop to let them know if what they're doing to be healthier is working.
Humanity is that feedback loop.
We are giving that superpower.
Humanity's founders have already scaled their direct-to-consumer platforms to over 1 billion people. I believe Humanity is poised to be even bigger, democratizing access to these insights to the world.
The digital health and AI market is growing at a staggering 20.7% per year and is expected to reach over $1 trillion by the end of this decade. We are witnessing a confluence of cutting-edge research in aging science, AI, and a societal shift towards health and prevention, culminating in the perfect moment, a moment that demands action now.
Our mission is to give 1 billion years of health back to humanity by the end of the decade. To achieve that, we need to be highly collaborative and radically inclusive.
We are no longer helpless.
We're no longer helpless.
We're no longer helpless.
We are no longer helpless.
We are no longer helpless. We have the team, track record, and relentless drive to accomplish our mission.
But we need passionate investors and advocates like you to help us get there.
Join us, and together we can help all humanity live healthier for longer.
Perfectly timed.
So there's going to be a QR code up here. If you want to find out more how you can join the mission, be part of giving humanity 1 billion years of health, then just follow the link, and I'll happily speak to you afterwards, but very much looking forward to the conversation.
Thanks so much, Peter. Now, Eleanor, over to you on Vida DAO, doing amazing work at Vida DAO.
Wow. So, hi everyone. I'm Eleanor Davis. I'm dual flow student at Vida DAO, and hang on. Here we go. So, as Peter's just shown us, and also everyone who's just spoken just now, we're all coming at longevity from a variety of different angles, and it just goes to show that you don't necessarily have to be a scientist in order to participate in the mission to end death, or So anyway, I'm going to be talking a little bit about advancing longevity research via decentralized communities, and this is where VitaDAO comes in. So traditionally, science has been the engine of our civilization, but the engine is becoming rusty. And it's not about the what in terms of innovation. There's plenty of that. We're seeing so much of this at CogX today. It's about the how. And this is really where decentralized science comes in. So, for instance, ivory tower syndrome and misalignment of stakeholders and incentives. So in terms of getting an innovation out of the laboratory and into the market, from bringing a molecule to market, there's a whole value chain of stakeholders, from government officials, from FDA approval to EMA approval, to institutional capital, to patients. And so currently we're seeing a huge misalignment across these stakeholders. Not only that, it's high barriers to entry, so people who are interested in participating in scientific research, whether they're interested in it, excited about it, or who see a future career path, it's often very difficult in order to find a path in. And then thirdly, bleeding edge research is currently operating under archaic infrastructure. So we are operating under infrastructure, for instance, technology transfer offices, and bringing innovative cures, potential blockbuster drugs into market. It's largely very difficult in order to get out of the laboratory, just because of the incentives that are completely misaligned, the percentage of ownership. There's no real forward thinking as to how to bring this out, how to be innovative. So this is where VitaDAO comes in. So VitaDAO is a decentralized autonomous organization. It is a bio-DAO. And what a DAO is it's a community-led organization, which basically is similar to a company. However, the governance, instead of being top-down, is bottom-up. So the difference with VitaDAO is that we are an umbrella. We're all under one roof raving. So we not only focus on the science, but also the community. So everyone is able to join. So there's a education, information side under community and awareness. There's also the deal flow side. So we fund and build early stage, bleeding edge longevity research. And then thirdly, there's the network states side, where we're looking at creating a special economic zone, or a pop-up blue zone, with agile regulatory framework in order to bring molecules to market more quickly, almost like a governmental sandbox. And so it's different in this way in that community members get more skin in the game. So decision-making is conducted via token voting. And what it means is that those who are interested in longevity, those who fund longevity, get to decide as to what moves forward. So currently, to date, we have funded 20+ projects, of which 7 are academic spin-outs. We're actually the first decentralized science organization to spin out 2 biotech startups. So that's Matrix Bio and Artem Bio. And we're really a thriving community of 9,000+ community members and growing, of enthusiasts, biotech operators, investors, government officials. And so with that, I would like to thank you. And I don't have any contact on here to join VitaDAO, but we are vitadao.com. And I'll go back.
Thank you so much, Eleanor. Lots of questions I have after our Q&A. Amazing. So last but not least, we've got Lynn. Before we kick off into Q&A, and do think of some questions, by the way. I've got loads of questions, but if there are any coming from the audience, we'll try and get to them as well. But over to you, Lynn.
Thank you. Hello, everybody. My name is Lynn Corner. I'm the Deputy Director of the UK National Innovation Centre for Ageing, established by UK government to help businesses to make the most of this amazing opportunity around longevity economies, and also the Director of Voice, which is a large international network of citizens, consumers. And at the end of the day, this is what it's all about, making people, everyday people, happier, healthier, and helping them to live better for longer. We have chapters in pretty well all continents now, US, Canada, UK, Singapore, Taiwan, China, because this is such a shared agenda. Longevity affects everybody, no matter where you live, no matter who you are. And we have the pleasure of working closely with Tina on this mission-based approach to help us to really think radically and bolder about how we can cut down the silos of longevity and really join up all this fantastic knowledge that everyone has talked about, but that is currently working very separately, to think how we can join up, how we can leverage the existing, how we can actually be better together in terms of joining these data sets. And we have a strategy of aging intelligence, because we have so much knowledge that we already know, but how can we better use that knowledge, break it out of the ivory towers and actually bring it into people's everyday lives? This matters to people. There are two global challenges. There is the healthy people and healthy planet. Currently, even that is working separately. And so at the heart of our mission is kind of a focus, if you like, on the exposome in terms of how we can take a quantum leap forward in terms of linking health and wealth and actually utilize all this data that is currently locked in different places and really kind of join up that kind of environmental data as well to health data. And if you think about it, you know, so much that matters in terms of looking at kind of pollution levels in cities, that matters to people's health. How can we actually join this up so that we are making this quantum leap forward and really accelerating what we can do to make people's lives healthier and happier? At the heart of what we're doing as well is kind of looking at, as we cells to cities, actually looking at longevity cities and actually looking at how we can really stimulate the development of local test beds for healthy longevity, really kind of take the everyday touch points that are in people's lives. Why cities? Well, 80% of the world's population lives in urban areas. We are already innovating for the 2 billion people over 60. That is a massive agenda that is happening now. So this is not about older people. This is about saying that actually a child born today, we're looking to kind of extend their healthy longevity and actually looking at cities, looking at how we can shape the environment and understand the enormous amount of data that we are collecting from everyday lives and how we can better utilize that, realign incentives and metrics to really help people to prevent a lot of the age-related conditions, as we've heard from humanity, and really take that step change in actually leveraging people's healthy longevity. There is so much that we can do now. And if we can actually leverage all those data points, imagine the difference that we can make to people's lives in every corner of the globe. So the City of Longevity is an initiative launched by the UK National Innovation Centre for Ageing, working closely with Tina. And what we're trying to do is to really kind of help cities, which are that kind of canvas, if you like, where most people live, to really kind of leverage the data that they have. We have a toolkit we've developed with Stanford in terms of the Centre for Longevity to really help to build this kind of way that each individual city can understand the formula, the actions that they can take on an everyday basis to really kind of nudge behaviors and habits. And at every touch point in citizens' lives, they can help to kind of bring through these healthy longevity habits and behaviors. So then through this, we can build this repository of really smart data, but all the time we're using it to kind of really nudge behaviors and habits and really help people to make the most of this incredible opportunity of healthier, longer lives. We're launching a challenge, looking for this investment in terms of how can we help by adding 1 healthy year of life within 5 years to 100 cities. This is in line with kind of humanity's vision of kind of affecting billions of people around the world. So the message really from us is that we need to take a step change. We need to be bolder and better in terms of addressing this. This is no time to work in silos and separate projects. The more that we can take this mission of joining up, really adding bring intelligence to healthy longevity and aging. This matters now to current people, but it also matters to future generations. And so taking that quantum healthy longevity from cells to city is urgent. And if any more information on any aspect of this healthy longevity innovation mission of the UK National Innovation Centre for Aging, get in touch.
Thank you so much, Lynn. That's great. So I hope our colleagues at the Department for Science, Innovation and Technology are listening. Michelle Donnellan spoke about the ambitions for the UK to be a science and tech superpower. And I think breaking down the silos, joining up the dots, the huge opportunity that we have with aging and longevity research right from cells to cities is such an exciting area. So I hope you're listening over there. But listen, I'm going to ask, I've got a few questions for all of our individual sort of panelists, and then we'll have some shared sort of, obviously we're going to open into a conversation about some of the things that we've learned about in these presentations. Do think about a few questions. If we've got time, I'll definitely ask some questions from the audience as well. So I'm just going to start first with Aubrey. So, we often talk about, getting longevity into the mainstream discourse, how are we actually going to reach the masses with all this amazing science and technology. You had a fantastic conference in Dublin a couple of weeks ago, or actually 3 weeks ago. There's been more and more longevity conferences. It shows that there's a huge interest. Investors are starting to look at this. So where do you think is going to be the next frontier, and where are the gaps that you're looking at with your organization?
Yeah, I think the longevity movement is following a rather standard trajectory of any new movement. We're at the stage now where, as you say, there is a big exponential expansion in the number of people who are interested in it, as reflected, as you say, by the number of conferences there are and the number of exposures in the media and so on. But I think the other thing that what we're seeing that is typical of such situations is that the interest, the enthusiasm and the money are all very unevenly distributed. There is a great deal of focus on aspects of this movement at the technological level that are, let's call them the low-hanging fruit, the ones where people can see that we are not very far away from revenue and profitability and all that. But this is a divide and conquer problem. We have to do a lot of different things at the same time to the same people in order to get the real benefits from, in terms of postponement of the health problems of late life. And some of those things are a lot further away from individual, proof of concept and profitability. And those things desperately need to catch up. And at the moment, the opposite is happening. There's not enough money going into those things. They're not going fast enough. The other aspect, of course, that is very much lagging, albeit it's beginning to change, is the attitudes of the decision makers in society, politicians especially, in terms of updating, modernizing the regulatory environment so that treatments of this sort, which are not the kinds of things that were imagined when the existing regulatory framework was put in place, can be taken forward in a manner that is more rational. Even individual therapies of the sort that we're talking about, whether it's gene therapies, cell therapies, are just, the system is not fit for purpose for those. Yeah. And it's much worse than that when we start talking about combination therapies, which is what's going to be necessary.
Really good points about regulation. I know that the UK government are looking at a whole raft of agile regulatory reform measures, which technically should open up actually innovation in this space. So we're obviously keeping a key eye on that as far as the mission is concerned. But I'm just going to turn to Alexei, because I think what we're really seeing, certainly from the recent longevity conferences that I've been at, is that there's this increasing recognition that we're getting more and more data. Obviously, Giro.ai have done some fabulous work, modeling, looking at all the concepts around resilience, homeostasis, and really looking at the data. So just tell me a little bit about that, and where you see the real frontiers are going to be in terms of really elucidating where we need to focus next in terms of understanding humans as a complex system.
Well, first we need more data, of course. Collecting everything from people, I think, would be a good idea, and collecting everything about you is a good idea today. And even though we got our hands on quite large data sets already, it's still not enough. The interest lies in longitudinal data sets as well. That's what we would love to get our hands on as well. And the usual problem with the data sets, and actually what UK is now doing a good job with, are how well are they curated and how much phenotypic data you get in these data sets. And UK has done UK Biobank, which has been great for us. It was very important for our research. But now it's doing a data set which is order of magnitude larger, and it will mean great things for longevity.
Fantastic. And I know, so for example, I mean, you mentioned the UK Biobank, and I mean, of course, one of the big ideas around the mission, for example, is this concept of a federated world testbed for health, being able to federate and access, data from all these different biobanks and around the world as well for data diversity and all the rest of it. So really, really fascinating. And I'm going to turn to the concept of, because I know I was really fascinated, because one of your recent papers in Nature, it estimated that on the basis of the data that you've been looking at, human lifespan is the maximum achievable human lifespan is about 138. And you also really explored this new concept around resilience, people's ability to withstand stress and factors in their environment. So I'm going to turn to Peter actually now, because a lot of the things that you're doing with humanity are really, really tapping into us as human beings, our motivations, our triggers, like our state of mind, when we're actually engaging with our health. Just tell me a little bit more about that and ideas around this concept. Some of the audience may not have heard concepts like biological age, which is really starting to get into the mainstream press now. And we've seen Netflix, I don't know how many of you have seen How to Live to 100, but they talk about the blue zones. But a lot of it is about behaviors in people's lives, daily lives, and making it so easy you don't even have to think about it. So tell me a little bit more how humanity is trying to get that right.
Yeah, thanks, Tina. I think, as we heard from some of the speakers, I think we can always do with more data. We can definitely get more people involved in the longevity community as investors, supporters, and so on. But if you look at the macro, you can see that, even with AI, everything's becoming ubiquitous. Language learning models are all going to become open source. So building an LLM company is probably not going to be a differentiator because everyone else will have access to the same. And data will become actually not necessarily valuable because you'll be able to create synthetic data sets that can mimic real life data. And essentially, it's more about what we can do with these AI and data sets that really makes a difference. If we can have all this like quantum knowledge, but we don't actually change our health or we don't cure these diseases, then what's all the point? So very much, we're focused on the application layer side, which is how do we take this breakthrough science and this longitudinal data, be open and collaborative, take the learnings from the likes of Aubrey as our science advisor or Alexi as our partner, and the National Center for Aging, and Vita Dower, in fact, is one of our investors. So it's all about being open, collaborative as much as we can, so we can raise all ships. But our focus is very much on how we can actually get people to change their health, and can we measure that improvement in health? You mentioned biological age. So we're all chronologically how old we are based on our birth certificate, but we all age differently based on the exposome, the lifestyle and environmental factors, much more so than our genetic predispositions. And that affects the way that genes turn on and off as a function of our lifestyle and environment. So what we do today, what I got you guys to do today for a minute, is the sorts of things that triggers these pathways, these systems in the body that helps us rejuvenate and extend our health. And we need to find pathways to get those types of interventions into the hands of everyone, which is what we're trying to do with humanity, which is in everyone's smartphone. And the idea being it doesn't have to be complex. Simplicity is the art of sophistication. So it's about how can we build more platforms like humanity that means anyone can do this. I wish my parents could have done it when they were alive, and I hope many of your parents and loved ones can use these types of tools too, because we all want our loved ones to be around healthy for another 10, 20 years.
And wouldn't it be wonderful if all of us shared our data for research? That would help all of us, wouldn't it? For all the startups and all the rest of it. So
through
that's
open
again
data
something
frameworks and using synthetic data sets, absolutely.
So So thank you, Peter. So I am actually going in order, but we'll have a conversation in a sec. So my next question is actually for Eleanor, and of course, all of us, except I think Lynn, were at Zuzalu, which was a pop-up city experiment, for want of a better word, in Montenegro that took place over a couple of months. So we were all there. It was this sort of an interesting convergence of AI and crypto and longevity pioneers all meeting together, really looking at this utopian sort of what is this longevity of the future longevity city of the future going to look like. What were your key takeaways, Eleanor? What do you think we can apply, I guess, more in the real world, so to speak?
Yeah, great question, Tina. Thank you. And there's actually another Zuzalu that's going to be coming up next year, and I hope to see more of the innovators here at CogX there. But what were the key takeaways? So first off, there is an ability to create a sandbox, a special economic zone, and an ability to cooperate with governments, especially new emerging governments such as the one in Montenegro. And there are stakeholders who are interested in utilizing more agile regulatory pathways in the interest of a better global health population, because this really does have knock-on effects, not only on people, rate of aging, health span, lifespan, but also on the economy, as Aubrey alluded to just earlier. The second takeaway was that there really is such a huge interest, actually, in terms of bringing everyone together for the same cause. And also, we're using different technologies that are emerging, such as blockchain technologies, such as AI, LLMs, LHMs. And what if we can together, collectively, look at the different ways of how to bring novel therapeutics, for instance, from laboratory to market, and also integrate more holistically health interventions, and also engaging everyone from young to older, and making it cool as well. So a couple of takeaways there, but yeah.
Yeah, I mean, I think what's really fascinating is you kind of described almost like, creating a system from scratch and actually really working around people. And governing ourselves in a way that really delivers on humanity. So I think that's a really interesting concept that I think is one to mull over and factor in. And I'm going to, and actually what you also mentioned, which is interesting, and I think a few people have already mentioned, is this whole issue around regulation and the system, and actually what are the barriers and how we unlock the barriers. So, so that I think might stimulate some more questions, in particular maybe from the audience. But I'm just going to turn to Lynn before we open up a little bit more. So with the work that, I mean, this is about real people, right? I mean, Zuzalu was, in a sense, slightly artificial in the sense, we're all, committed enthusiasts, so to speak. But with your work, how do you take this out to the common man, with the work that you've been doing at Voice, and obviously with the way that we're recruiting cities for the Longevity Challenge? And what do we need to do what are the things that seem to be working to really connect with people?
It's a great question, because I think it's come up a couple of times in kind of conversation about, this is all about people, it's all about families, it's all about communities. And with Voice, what we do is we mobilize that community in terms of valuing the wisdom, the experience, the knowledge, the ideas, the imagination, creativity that's just in everyday people, in our families, and actually mobilize that to kind of join with kind of science and businesses to co-create, co-develop the products and services that people need in their lives. And I think it's really important that we don't forget about what makes people tick, what makes them happy, actually focusing as much on kind of the psychology of aging and how that affects the biology, how we can join it all up. What makes people happy? What gives them hope? How do we kind of make sure that people are optimistic about the future? And that means kind of joining up all this amazing longevity science with kind of, with jobs, with people's communities, with where they live and how they live. So again, kind of a call to action in terms of joining up so many things that we look at separately. and saying actually just about joining it all together. But this mission, this kind of ability to kind of live for longer, I think you put it well, Peter, in terms of democratizing healthy longevity. We've got to take it out of the labs, and we've got to make it accessible, cheap and easy for people to be able to kind of grasp and know what they need to do.
Yeah, it needs to be easy, cheap, and it needs to make us feel good and happy.
Yeah.
I mean, that's a real motivator for human behavior, isn't it? And I think dancing has come up a few times, and even Peter got us all to dance. So, but listen, I'm going to open up. Are there any questions from the audience? Yes, we've got one over there. So if we can hand over a microphone.
Test. Hi, fantastic panel. And yes, Zuzalo was also amazing. And I think on the stage here is a lot of optimism around longevity, and rightly so, because there's a lot of very exciting things happening. But I do want to just bring it back down to earth a little bit. And this is quite a controversial question, which I've never had properly answered by anyone in the space. And I think you guys are perfectly qualified to do so. What do you guys expect to do with, in my opinion, the inevitable social unrest that comes with the advancements of these technologies, in particular, continuation of the gerontocracy, collection of data, the anti-religious connotations with expanding the lifespan, and generally the concentration of these therapeutics in a small portion of humanity first, before it is then distributed to the rest of humanity. So,
right. Let me challenge your premise. You say that this is inevitable. I don't agree. I think that right now, in the decade or so before such therapies arrive, and they're available to anybody, people like those of us here on stage and other thought leaders in this community have the opportunity, and therefore certainly the duty, to educate the people who can, I like to say, anticipate the anticipation. In other words, people who can alter the policies of governments around the world, and not just governments, but the economies, so as to mitigate, and in fact perhaps almost abolish the social unrest and turbulence that you describe. I believe that that can be done, that the sheer the astronomical economic benefit that will arise from the arrival and the dissemination of these therapies will be so enormous that the rational thing to do, purely from a mercenary economic perspective, even forgetting anything about the humanitarian imperative and so on, will be to ensure that these things are equitably distributed, even though that will entail a great deal of front-loading the investment.
Yeah, and I have a great example on the last part of your question, which I really love. Antibiotics, when they were developed, they were so expensive that they had to be extracted from the urine of patients just to give to next patient. And now they're cheap. It's a natural way of technology to be developed. First, it's expensive. Then within 5 to 10 years, it's ubiquitous. So the last part of your question, I don't agree with. The first part, Aubrey already answered.
Peter, do you want to?
Yeah, I mean, I'm so in line with your point, though, that we should be not having this for the privileged few, but for the mass majority. And so I think one of the ways we can avoid some of that potential social unrest is just how you would avoid the problem of if the rich get richer and the poor get poorer. We need to come up with solutions that benefit everyone, and that's what I think we need to do more of.
And let's not forget, we're not just talking about drugs either. There's a lot of stuff that we can all do that's freely available for everyone, so which we're not doing. So that's also a point to be made. But Eleanor and Lynn, any comments on that?
So my point would be that in terms of the involvement of VitaDAO and the decentralized autonomous organization type of model, is that democratization is a part of the cause, and there's no kind of concentration of wealth or power in terms of how the DAO operates for delivering on its mission. And it also ties into what Pete was just talking about as well, with giving access to everyone. And I think that kind of brings me on to what Lynn would probably
I think it's about kind of an open debate on trust and data sharing, everything on that spectrum. We've got to do more as a community to make sure that it is shared, it is open, and there's some fantastic organisations and businesses already doing that. So, again, hopeful for even these big societal challenges, if we can kind of create the framework with which to either regulatory environment through to kind of that kind of open public dialogue. I think that's what's essential if we're to progress.
So I see a clock ticking away here, but I was also told we can go slightly over time if we have any more burning questions from the audience. So we've got one at the front row. Yes. Oh, and there's probably more than one. But anyway, we'll go to the gentleman here who I saw first. But we can.
Hello.
Hello.
Hi. Coming at this from the perspective of AI, we're seeing a lot of the rate of discovery and the capability of drug discovery is accelerating with generative models like AlphaFold and a lot of the things that we've actually seen pitched today on the stage. I know, Aubrey, you've talked about engineering the body and some of the possible processes that we'll need to adopt to slow aging or potentially reach longevity, escape velocity. I was wondering, further than ingesting drugs, or will all of the rest of the components we'll need to adopt into our lifestyle be lifestyle choices, or are there other therapies that we haven't discussed that involve engineering the body?
Yeah, not very much of this is going to be dependent on lifestyle. I mean, certainly, I think it's a good thing to behave the way your mother told you to, and generally, not accelerate your aging and not hasten your decline. But by and large, the things that we are going to be developing, these damage repair interventions, rejuvenation interventions, will be largely independent of differences between people, whether in lifestyle or in diet or in genetics and so on. They will all have, differences in terms of how intensively, like how frequently and how thoroughly they need to be applied given different people. But it'll be essentially the same therapies because we all accumulate the same types of molecular and cellular damage. It's just that there are small differences in how rapidly we accumulate them.
Alexei, maybe Peter. Yeah.
Yeah. So I want to comment on the first part of your question about generative AI. I actually think older AI technology like deep learning, machine learning are more important to that because we need to find the mechanism. We need to understand why aging is happening. So yeah, and with lifestyle, I also comment, papers show it's about 10 healthy years you can have with lifestyle, and you absolutely have to do that, but with more radical interventions that hopefully will come faster than slower, it will be decades.
Peter.
Yeah, I think AI is helping us accelerate understanding what patterns work for us individually, as opposed to looking at general population studies. So I think the difference being that whereas we used to rely on a study that tells us that it works for 70% of people and we think, well, that means it works, we can now start to understand whether it actually works for you and to what degree it works for you. And that's very much where we see a huge opportunity. But I think it's really worth emphasizing that the hallmarks of aging, which some of you may have heard, which are the kind of 10 hallmarks that the kind of scientific community kind of come together and say, yeah, they're the systems that really we need to sort of affect if we want to increase health span, lifespan. And they're things like mitochondrial dysfunction or removal of dead cells, senescent cells. What people don't necessarily acknowledge is that doing things like exercise is a natural senolytic. It's a natural mitochondrial reactor that essentially creates mitophagy. When you fast, it creates autophagy. And these are all cellular repair mechanisms that basically give your body, a regenerative repair feedback loop. And whilst we may not be seeing that so obviously through blood tests and so on, these are the systems that are creating the slowing of aging mechanisms that we are seeing. So I just really want to emphasize that so that we all do not kind of get too trapped into the idea of a wonder drug in the next 1 or 2, 5 years, like what everyone thought metformin was going to do, because actually if you just do all of the things that we think we know we need to do, like hot and cold exposure, good diet, fasting, exercise, sleep, meditation, and so on, 80% of the value for the extra 10, 20 years will be there. And then that will help us to get to longevity, escape velocity, and still be in a position where, yeah, we can take an injection with some pluripotent stem cells and then just come back to the same age as I am now when I'm 60. Great.
Thank you. We have time for one more question, but thank you, Peter.
Out of curiosity, which, in your view, is the best test currently on the market that will give you a good assessment of biological age?
What is the best test on the market for biological
Today,
age?
yeah.
Good question.
What's your question?
I'm obliged to say it's Girosense, which we developed, but because it's most scalable and useful on large scale. But other than that, I don't know.
Peter?
I'd say the number one thing is to monitor yourself as much as you possibly can, and so that means get your blood tests, look at the different biomarkers in there. If you look at Peter Adier, he talks about, ApoB, lipoprotein little a, all these things are good to cardiovascular health. But then there are a bunch of us like ourselves where we put in a paper to Nature where we're actually going to give you a biological age based on just 4 to 6 analytes, so it's more inclusive. You can go the high end and do a full body MRI or get a DNA methylation test. But again, the key is, one might tell you, like the glycan age test tells me I'm 20. I like to believe that, but I think maybe that just means that in one of my systems, I'm healthy, but maybe in another system, I need to do some work. So I think monitoring yourself in general, digital with the movement and heart rate, bloods, DNA methylation, full body MRI are all good if you can afford them. And then that way you can start to see what seems to be working for you and what you can change.
So suffice it to say, there's a very healthy debate going on in the longevity community about all this in terms of aging biomarkers, clocks, what combinations, what works best. And that's the new frontier, actually really understanding, what works best and what actually also matters most to human beings as well in terms of the interventions that are going to affect our lives. So it's a very healthy debate. So watch the space. But we do need AI and all these new frontier technologies to help us work it out. I don't know, do we have time for one more question? Is that allowed? One more question, I think we're allowed, yes. Sorry, I'm just going to the chap with the beard. Sorry, and I've just seen...
There's no microphone.
And we need a microphone. Sorry, I hope that's okay to ask.
Comes.
We were told that we were allowed to go over a little bit because there's nothing after this session, so...
Thank you all for your answers to my earlier point. Just on your last point there's a healthy debate about biomarkers and other such things. Is there a healthy debate openly within the longevity leadership community about the things that I just mentioned before? Because I do think that they are going to be the thing that holds back longevity from its general acceptance, is the general misunderstanding and unacceptance from the population outside of this community. So is there active, healthy debate around the distribution in particular, the concentration of these therapeutics, but generally how you integrate with the everyday society who are going to, in my opinion, as I said, in my opinion, produce some social unrest around this topic?
Well, I mean, we need to work to make sure that there is no social unrest or to minimize that unrest. But honestly, I think that focus on the fear of such unrest is part of the problem, because at this point, society is actively holding back the arrival of these therapies by this constellation of arguably unfounded, or at least minimally founded, concerns about what this would do. We've spent millennia making excuses for aging, trying to pretend that it's a blessing in disguise, convincing ourselves that, it would be terrible if we didn't have aging. And we've done this for, psychological crutch purposes, but it's time to abandon that. It's time to actually remember that we are now within striking distance of bringing aging under control, and that therefore, the more that we cling to the irrational excuses that we used to make in the past, the slower things will go and the more lives will be wasted, the more lives will be lost. We need to look beyond that and be brave.
And I think it's fair to say that the stakeholders it's become much broader. So there's a lot more discussion with a much broader range of stakeholders on this whole debate, and actually looking at solving the real societal challenges of today. So that's certainly what we've seen, and certainly all the work that everyone here is doing. So, I think.
No.
I'm not saying it's not going to be a problem. I'm saying that we can make it not a problem, but that the fear that it will be a problem is itself a problem. We're working on it. We're trying to talk to governments. We're trying to educate people. Tina's spent the past 20 years doing that. So have I.
There's a huge committed group of individuals who are very, very focused on equitable access to healthy longevity for all. The longevity dividend of all this wonderful science and technology has to reach the masses and has to be shared equally and fairly. That's what all of us here today are very, very committed to. And I would say there's a growing community, and we can only see this from the huge number of very committed top scientists, entrepreneurs, industry leaders, all backing the mission. So I hope that answers your question. I will turn to one more with the lady in the front row, and then we'll probably close, if that's okay.
Yeah, and I invite you to join us.
Yeah, join us.
Yeah, join us and pose these questions. Like Alliance for Healthy Longevity initiatives, they are working with US government to make the thing happen. And like, we need to do it in the best way possible. So,
and this is why Lynn is working with the Citizens Network, the Citizens Voice Network. We have to involve everyone also in the decisions and the solutions. So we're going to be in Suite 216 after this event. So come and speak to us there, and we'll chat with you more and just get involved. So yes, that would be great. So I'm going to just because I know you wanted to ask a question, and I feel that everyone should be given a chance if we can. So.
Thanks so much. Yeah, I thought you missed it. But hi, nice to meet you. I'm really interested in health, especially mind and diet. I think, Peter, you mentioned like sleep, exercise, mind, but food. But I think mind is also important. Like, unless you have like a really good mind with like intention to be happy, I don't think you can be healthy even though you have like really good food and exercise. And then the AI aspect, it's really interesting, everything becoming digital and then everything being tracked. And then I think it had some kind of a benefit, but at the same time, I feel like it's a little bit...
too much.
Yeah, I believe that it's going to be too much, 100% by 2030. Even like studying data, and I think collecting data is really important. But imagine like in 5 years, everything about you is being tracked, and then you have no education and no awareness because everything is on the device or on the phone. Yeah. So I just want to ask, like, how optimistic do you see? I know you're gonna try to solve the problem, and then you're gonna try to make it better, not going to rely on AI too much. But how optimistic do you see? And then how do you, like, which direction you trying to go to live with AI in terms of being healthy, to relate to mind and the diet?
So I think if we're hearing you correctly, I think there's this whole question around being tracked and being over-tracked, and I'll let my colleagues speak to that because there's so much effortless data capture without you even realizing, but then you need to consent to it, obviously. But I think there's this whole question about your mind and, how can AI and all these technologies really understand how the mind affects our health as well? So is that sort of where you're coming from? And I'll...
Yeah,
okay.
Yeah.
So I'm gonna hand over to Lynn and to Peter and to Alexei.
So it's a great question, and I think back to the citizens, if I kind of always put on that kind of citizen hat, this is all about kind of smartly using the data, the data that AI can generate in order to help citizens and cities to make those informed decisions. I'm really optimistic in terms of if we can sort of go back to kind of thinking through these longevity cities, how can we get policymakers to smartly utilize the data that they have at their disposal to build environments where people can actually actually nudged their behaviors. Because in order to achieve longevity, you've got to adopt behaviors and habits over a very long period of time. So we've got to try and encourage that environment to be able to kind of nurture that. In terms of the mind, I think you've hit a really important area. I think it's the last frontier. In many respects, we are launching actually next week at the UN Science Summit an international kind of strategy on brain capital and brain health to try and get kind of people to invest more in understanding people's brain health and their happiness, their optimism, hope, all of these concepts. And there is certainly so much more to do. I think what we've identified through the discussion today is that we know a lot already, and I think the points I hopefully made was how we can actually drive and leverage that existing data using AI and using all the tools at our disposal in order to kind of make sure that that science is out of the labs and into people's lives. But also, through this process, we can identify what we also now need to know. We do have gaps in our understanding, and that's fine. But how we accelerate that kind of knowledge and understanding is going to be the next sort of 10 years. And it's linked to kind of taking citizens with us to really help people to understand what they need to do, and also creating kind of environments through policy, through city initiatives, which help people have the circumstances which they can make healthy choices. So on kind of every level, there is just so much opportunity, but this needs international collaboration. So in terms of the detail of your question, I'll leave it to others to answer, but for sure, the only way we're going to take that quantum leap forward is through kind of strong international collaboration to be able to leverage the best of what's available.
Thanks, Lynn. Peter and then Alexei, and then we'll stop there. But.
If you guys have been to some of the other talks on AI, you might be scared to death that we're all going to, destroy ourselves and the world will end. But that's because we are obviously hitting one of the most revolutionary technological advances of our history. And if we don't come together and collaborate and create policies and ethical approaches and systems to manage that, then yes, there are risks. Tech can be used for bad or for good. And so I think that I believe that humanity is inherently good. I think that we want to bring the best out of each other, and I think we need to build the systems and the institutions and the policies and train the models to be in accordance with that. But the interesting thing I'll conclude on is what you said about mind, because emotional health and purpose and having consciousness to connect with all of us for the greater good, I think is the highest form of self-actualization and community activation and what brings fulfillment and happiness to humanity. So, we should be harnessing technology to accelerate that collective consciousness and actually help people to feel much more fulfilled and emotionally healthy. And I think there's a huge advancement in understanding mental health and well-being, so much so that I think we can just accelerate direct to end user sort of solutions to bring about that change much faster for the greater good.
That's the next frontier, absolutely. And Alexei, just because you're doing amazing work with digital resilience markers and all sorts of things.
Yeah, and it's mental health is very important for longevity. My student did actually a study, and people who are bad at mental health, they don't want to live more. It's kind of obvious. So one can argue it's even like more upstream to solve mental health than aging. But we as an aging industry, as longevity industry, are already stretched too thin. We will focus on that. But I respect all the mental health people. There are some of them in this room I actually know. So I think it's super important. We absolutely need to do that, because if you're in depression, you don't want to live, you want to die. So.
It affects our biology. You can measure stress in blood. Yeah. I mean, this is all possible now.
We see this, like most of the same biomarkers are related to depression and mental health than to aging. And people in depression live less, so why bother? They just die.
So it's a really, really important question, so thank you for asking that. So I think time is really up now, but as I said, we're all going to be congregating in Suite 216. If you've got the pass to get up to Suite 216, you can find us there and we can chat some more. But really thank you all for attending, and thank you so much to my amazing panelists. Thank you so much.
Thanks to all of you.
I hope it was okay.
Yeah, it was great.
We went over time.
Yes. Longevity, So many meanings. Thank you so much.
Thank you.
Okay, so thanks to everybody for spending time a little bit extra with us and for sticking with the deep tech stage all day. We've talked about biotech in the morning, health in the afternoon. A preview of coming attractions for tomorrow. We're going to be looking at quantum, atoms, and semiconductors, and climate tech and sustainability tech. So come back for more tomorrow. Leave even more enlightened. On that note, I wish you a great evening. Thanks very much.